right, good morning, everyone. Welcome back. Hope you guys had a great night last night. Got to explore Sacramento a little bit. Today we got another great day of talks. We also have a concurrent event from 10 to 3:30ish over in the Klamath Room. It's a community science workshop, so if you want to poke your head in there, it's going to be kind of a training session, kind of brief overview of how to design monitoring programs, QA, how to turn data into information with some short kind of presentations on some basic visualization software, as well as a little bit on water quality standards and water quality indices, and then kind of an open discussion platform for people to ask us questions. So that'll be going on in the Klamath Room, so we encourage you guys to attend that too if it interests you. A couple of logistics. You weren't here yesterday. If there is a fire alarm, just please calmly exit the room, down the stairs, out the door to Cesar Chavez Park on the corner of 10th and J. Just we can meet there, and then once we get the all clear, we can come back in. The facilities for restrooms are on the left. If you need refreshments, there's a cafe downstairs and some eateries as well. There's also some great posters and vendors outside. I encourage you to all network and talk with them during the breaks and the lunch sessions as well. You'll see behind me, we put up some of the resulting work from the datathon yesterday. Feel free to also during breaks come up and peek at those. Those are what the teams put together. They came with some great projects in a short amount of time, so it was a really cool event. With that, our first speaker, the general format will be the same as yesterday, but we'll have about a 15-minute presentation with an opportunity for Q&A. Our first presenter has a vendor table, so he's elected to use all of his 20 minutes, and then if you have questions for him, you go out to the planet.com table and ask him questions there. So with that, Orestes Herodotou from planet.com.
Bring your satellite to work day today. So, up there. All right, good morning, water worlders. So the first person that can yell out what season and where this image is, come see me and get some swag after the conference here. So, any guesses? Where? Sacramento. Yeah, Sacramento, you got it back here in the corner. Perfect. That wasn't that hard, right? All right. So this is my first waterboard, so it's been really exciting to meet a lot of people and see what goes on here in Sacramento and learn about all the different efforts going around the state. And my talk is called Space Hydrology, Monitoring Water from Low Earth Orbit. We haven't actually discovered a ton of liquid water in orbit, but this is more focused on the ground. Just a disclaimer, I'm going to be as woke as I can be, but my presentation might be a little bit offensive to any flat earthers, so just letting you guys know. So my name's Orestes Herodotou. I'm a software engineer on the Planet Analytics team, and I work on automating machine learning models and at scale that work on our satellite imagery. I love sailing in the bay, and I'm also an anti-plastic pollution crusader, so shout out to the datathon today. And I'm not a remote sensing expert, so go easy on me on some of the more technical aspects of some of this work I'm going to show. I've got lots to cover, so I'm going to try to breeze through some things, so feel free to ask me questions afterwards, and I'd be happy to go into depth. I'm going to do a little introduction on Planet. We used to be called Planet Labs, but now we're all grown up, so we dropped the labs. I'm going to cover some details on our imagery, talk about how our platform brings all of our processing together, and then look at some of the research impacts. And what I kind of want to show is that we're really entering a new era of remote sensing. It's sort of a golden era and a renaissance in the space sector. So I'm hoping to demonstrate that there's a lot of opportunity to use these remote sensing opportunities for environmental and economic challenges that face the state, and I hope that planet imagery can maybe contribute to solving a lot of these issues. So Planet is an integrated aerospace and data analytics company. We were founded in 2010 by some ex-NASA scientists from NASA Ames, and we're headquartered here in San Francisco. We've built the largest constellation of satellites in the history of mankind, and we've launched over 20 missions on all kinds of rockets from the Soyuz to the SpaceX. In 2017, we did a launch with 88 individual CubeSats like this one on an Indian rocket, and that got us to our goal of being able to image the entire Earth every day. So we cover the entire Earth's landmass roughly every day since 2017. So our motto is really, if you can't see it, you can't fix it. So we want to try to bring visibility and transparency to all the different dynamic changing parts of the Earth and be able to sort of aid in working to understand the impacts that humans are having on the planet, and then put that understanding towards addressing the UN Sustainable Development Goals. This is a picture of our 3 different types of satellites that we operate. The main satellite we're known for is called a dove. We picked that name instead of the usual like eagle eye or hawk sort of bird of prey messaging that you usually see with satellites, and those make up what we call the PlanetScope constellation. We also have the Rapid Eye, which was a company that we acquired a few years back, and SkySat, which is our high-resolution sensor. And in addition to operating these satellites on orbit, we also have about 30 ground stations around the world. We have an automated mission control that takes care of communicating with the satellites, and we have automated publishing pipelines that handle enormous amounts of imagery that we download every day from space. So this is the Dove sat in a little bit more detail. It's what we call a 3U CubeSat format. It weighs about 4 kilograms, and this is what our daily imaging constellation is composed of. We have about 120 of these in orbit right now, and they've been consistently developed in a process that we call agile aerospace. So every 6 months or so, we're updating the configurations and improving the image quality and the different parts of the design, making them more effective. Each dove is covered in art. I've actually gotten to draw and sign one of these, so I'm the first like Polish Cypriot guy that's gone to space basically from that. They're at an orbit of 475 kilometers, and this is an optical imaging sensor that covers the red, green, near IR wavelengths. This is a comparison between what a PlanetScope image typically looks like versus a Landsat 8 scene to give you kind of a sense of the scale of the resolution, which is about 3 to 5 meters per pixel. So the other 2 sensors are called SkySat and Rapid Eye. Rapid Eye includes a red edge band and has a really deep archive of imagery. The SkySat can do 1 meter resolution to sub-meter. We have about 14 of them in orbit. And the idea here is that with the monitoring constellation of PlanetScope, you're able to kind of detect course change around the world. And then if you see something interesting, you can task the SkySat satellite to get a really high-definition view of that. We've also done video and stereo reconstruction for elevation with the SkySat, as well as like some really cool off-nadir shots that you can find on our website. So this is a comparison between SkySat and PlanetScope in San Francisco. So you can see, you guys can see that's a much sharper, this is at the same zoom level, but you can go in and get a lot more detail with SkySat. And neither of these sensors really are to the level where you're looking at people's watches or reading people's phones, so don't freak out. They're really meant for that overview to understand more widespread change. So our imagery products are generally published as what we call a cloud-optimized GeoTIFF. These are like your regular GeoTIFF files that are pretty standard in the industry for raster data. But they allow ranged HTTP reads, which means you can pull out just the data that you're looking for. So that might be just the bands or just a certain area of an image, which makes for really efficient workflows. And we publish a lot of different processing levels. For example, like a 16-bit analytic image for a scientific workflow, where you need all 4 bands and you need to have a higher data quality. We also radiometrically correct images directly for you, so you can just kind of download a surface reflectance product from our website and skip having to do that work yourself if you feel like it. So our platform handles storing and publishing our imagery, and then we have a bunch of different APIs and tools, including graphical user interfaces for people to interact and download our imagery, as well as we serve web tiles. And you can also you can also access our imagery from third-party providers like QGIS or ArcGIS. And a lot of our customers will integrate directly with our APIs and create their own sort of value-added solutions. So they'll get like a notification that something new got published. They'll download that image straight into their workflow and then do whatever processing they want for their specific application. Some of the other solutions that we offer are our analytics platform, which is fairly new, but we're going into limited availability very soon this year. And that is our automated machine learning derived products. And so one example of that is an automated building and road land cover classification that we can do at whatever cadence, be it daily or monthly for larger areas. Our platform also allows you to kind of bundle and crop different imagery assets for just the areas you want. And like I said, get notifications on your specific area of interest. So you're not spending a ton of time like going through these millions of images trying to figure out which one you want. We also publish global base maps, which are mosaic composites. We have quarterly and monthly cloud-free time-lapse mosaics, and we also do custom mosaics. And they're also available with like OGC compliant web mapping services, so not much magic to get them into your web app or into your portal. This is one of my favorite parts of the talk, is talking about our open data projects. We are part of the Charter for Space and Major Disasters, which sounds really scary, but it's basically the foundation under which anytime there's a disaster, the UN asks us to contribute imagery for public consumption for volunteers and humanitarian organizations. So we have a whole section where we publish that imagery as fast as we can get it. And there's a team of people at Planet that basically is trying to stay up to date on if there's a big hurricane that's going to come out, get ready and try to find the first cloud-free images of some areas, and you can see flooding or earthquake relief efforts be really affected by that, as well as last year here in California we published a lot of these images that dealt with the fires. We also have an education and research project or program that is open to academics at universities, as well as students and other scientists. And that gives non-commercial download access up to 10,000 square kilometers of data per month. So it's a pretty nice free data plan. So if you're affiliated with a university or you're a student, I would love to see what you can come up with some of our free data. And you can just apply online to get this. So I'm going to switch into some of the hydrology highlights here. These are some use cases from around the world that show how planet imagery is being used in relation to asking both scientific and economic questions around water usage. And I think there's some really interesting stuff here that is definitely applicable to California. And one big theme that I want to keep in mind here, and I mentioned this sort of remote sensing revolution that's going on right now, is that we're finding that a lot of people are merging different data sets, bringing UAV and aerial imagery together with planet or ground measurements and other imagery from different satellites together. That's a really big theme here. And at the end, I'll talk a little bit about an effort to make that even more a flawless process. So the first example here is about commercial vineyards. It comes from Israel, so I was kind of like, what's up with these guys in the Holy Land always turning water into wine? It seems like something I like to do. But basically, this paper talks about using spectral indices calculated from planet data to measure the grapevine stem water potential, which can then obviously lead to much better cultivation practices. Usually this is done using like a UAV or electric probes, which is really time consuming and has limitations on how far you can cover. So this kind of greatly increased their sustainability and efficiency in their fields, in their test data. And they were saying that they could apply this to like a global model as well. The next example comes from river morphology. So what they did here was basically combined aerial imagery to measure these sandbars in rivers in Saskatchewan, Canada. This is from Robert Strick at the University of Brighton. And then they did the same thing in planet imagery and compared how much the positions change from those different images. And they were able to conclude that they could make reasonable estimates of the bedload sediment transport from just using the satellite imagery. So that really opens up the potential for global estimates of the bedload sediment flux for large and inaccessible rivers where you can't go in with like a boat or sonar, or you just don't have time to cover that. Or you just have like sparse rates there already. The next example is from Greece, Dimitris Poursanidis from the Foundation of Research and Technology in Hellas. This is basically a bathymetry study using pretty traditional methods of calculating water depth with multispectral imagery, but was applied with PlanetScope data. And what the authors found was that they were able to predict depth with a RMSE of about 3.2 at a depth of 10 meters, and at a slightly lower precision down to depths of 25 meters. And they concluded that the imagery was suitable for use in navigation because the results that they calculated were compliant with the International Hydrographic Organization requirements. So, they're offering a way to scale up temporally and also in availability this bathymetry mapping. So you can imagine applying this and getting really up to date to the daily or weekly all over the world. This is a really interesting study from Sarah Cooley of Brown University. So in the Arctic regions, a lot of freshwater lakes influence carbon dioxide and methane emissions. And as their shorelines change and become more variable, they have a greater flux of greenhouse gases. So, there's hundreds of thousands of lakes in these areas, and basically what these researchers did was use our planet imagery to monitor the shoreline change and then derive some of that flux on the greenhouse gas side. Just something that you probably would be completely unreasonable to do, over a time scale with aerial imagery or traditional methods. So again, just showing that expansion of possibilities using remote sensing data from space. This is a pretty interesting one. This is ship-based detection from Catherine Rice at the Naval Postgraduate School. Using a deep neural network, I believe they use the VGG 16 architecture for this. They're able to not only detect vessels with a really high accuracy, about a 0.83 recall and a precision of 0.85, but they're also able to classify types of ships and even fast ships by looking at the wakes. This has a lot of implications for, like illegal fishing or transshipments, security, commercial shipping numbers, as well as like dock management. And we also offer at Planet now, part of our analytics platform is port ship detection globally. So this is a project that I've been working on too, kind of on the other end at Planet, and it's been really exciting to be able to see that we can, with a really high consistency, be able to measure wherever ships are around the world at any time, especially when they're doing something illegal and they turn off their AIS beacons. This is one of my favorites, the Global Coral Atlas. This is a project funded by the late Paul Allen, co-founder of Microsoft, and also with the National Geographic Society. And basically, they've started mapping all of the world's corals with planet imagery, and they plan on having all of the world's reefs mapped by 2020. So they've got an Atlas website already up, and just really important resource for our oceans, obviously, And it's just great to see that someone's actually endeavoring to really map the whole world's resource like this. And that's really the data sets that we're trying to kind of put together with our imagery. Well, the last two are sort of related. They use this same processes to get to their conclusions. Basically, leaf area index is not something that you can typically calculate from a RGB near IR satellite. You want to use the shortwave infrared bands, something that Landsat 8 has. The researchers Rasmus Holmberg and Matt McCabe were able to develop machine learning methods that basically took these took the Landsat 8 and calibrated it to the planet data so that you could fill in all the gaps with the planet temporal revisit rate and the higher resolution that we offer with the Dove imagery. And they created a model called the CubeSat-enabled Spatial Temporal Enhancement Model, or SESTEM. And they have these, and so you're able to do this sensor interoperability. This last one also now calculates evapotranspiration using that method, since we have the leaf area index from the last process. We're able to use that in the Priestley Taylor Jet Propulsion Laboratory retrieval model. And this work was done by Bruno Aragon in Saudi Arabia, where they're trying to grow crops essentially in the desert, and they're quickly depleting their groundwater sources. So just a really great study on being able to show that even with this CubeSat data that might lack some of the spectral characteristics generally needed, with the sensor fusion approach, you're able to still measure evapotranspiration and therefore more accurately monitor water losses in agricultural processes. A few additional highlights here. There's some seagrass change detection, suspended sediments in tropical rivers, shoreline change, and measuring river velocity. These are all coming from our academic program highlights, and you can read more about them on our website or ask me, and I can get you links to the different papers. And that kind of concludes the that part of it. I'm running really low on time. This is the last slide here. So given the theme of that data interoperability, there's been a lot of effort from players in the industry and led by Planet to work towards creating data products that can work really well with each other off the shelf, so that individual scientists aren't responsible for cross-calibrating every single time someone does a project. So there's at the USGS in Menlo Park is the second analysis ready data workshop. And there's some links here that you can go to read about the last one. There's videos from that conference, as well as a sign-up link, or just ask me later about it. But if you're into remote sensing and this isn't just for satellite imagery, but for any type of aerial imagery or LiDAR, et cetera, definitely check this out this summer. It's going to be a great conference. And with that, I'm just going to leave. This is a quote that I really like, and I think really stands for what everybody in this room is doing, and what we're aiming to do by having created this global time-lapse data set. So thank you, and yeah, let's make water happen.
So there actually is time for questions. So if you have questions, raise your hand. You got a mic running.
Questions? I had some resolution questions as far as actually looking at spatial versus temporal in greater depth, and kind of what the goals of Planet are on the spatial resolution. You know, right now it's pretty far pan out, like you're saying, it's not people on their cell phones, but I'm curious as an industry expert, what sort of timeline until we are grappling with that? I mean, that has exciting implications for water science and other sciences, but it also obviously has ethical implications.
Yeah, we don't have, we're not like developing a super zoomed in sensor or anything at this time. We're definitely always trying to improve the spectral characteristics. We have some really exciting tech demos kind of coming along in the future. But I think the focus for us isn't that we're not like really trying to look at that scale of things, and it becomes sort of unfeasible, or a lot more difficult at the rate that we're trying to do it temporally. I can show you a little bit a video of the way that our constellation works and the orbits work that lets us be able to do this, but there's not really a goal of trying to monitor individual people or see where they're at. But it is a really serious question, and I think it's one that we need to stay engaged with to answer, and that everybody should be thinking about. And if you look at facial detection in China, or how it's being used there to give you get like a ticket if you cross the road, not on a crosswalk. That's a serious concern. Really, what we're trying to do is give that transparency to the world. So, if a country, for example, is acting malevolently, for example, there was the Rohingya refugee crisis last year was going on, and military forces were coming into villages and clearing people out. We're able to see that, right? They're also maybe able to go now see where people are at, or where their enemies' military installations are at, or a company might be able to see where their financial assets are concentrated for their competitors. But really, it's giving that transparency to the Earth for both sides. And so we don't do any like exclusive licensing on our imagery too. That's kind of one of the things we're the way that we structure our plans. So we don't want to like just give that transparency to one side. Hopefully that answers your question a little bit.
A lot of satellite imagery stuff.
Very.
Wait, sorry. Somebody was asking me a question in the back.
So I'm curious, I see lots of opportunities for like these larger scale collaborations where you could look at things like global sediment production or regional freshwater storage opportunities. Are you guys involved with helping to coordinate different researchers to answer these larger scale questions at those large spatial scales, or do you kind of leave it to every researcher to kind of independently pursue, or do you play any role in helping to kind of coordinate the different efforts that are going on?
We don't have like an official role coordinating any efforts, but that's part of why I'm here, and what I'm excited about personally is really getting this. A lot of people haven't ever heard of our data set, so trying to get the word out that this technology is available. We're happy to connect people as well through our academic program, and we have had like some events around the world bringing together some of our academic partners. We're also working to work with institutions to make that data available to the entire institution directly, and I think that will kind of increase the amount of people being able to collaborate on some of this data. The other thing I will mention is that there are concurrent efforts as well, in the interoperability space, in just kind of defining the data and being able to catalog it, and making that available in a searchable, indexable way online. There's a project called the Spatial Temporal Asset Catalog, or STAC, and some people at Planet are also kind of behind that. It's an open source project, but we're heavily involved in defining that specification. And we think that having sort of these open source standards around this imagery and where it is, what's available, you're doing a lot more like reproducible research by providing access to that. Great, thank you.
Get
Stuff out of your way.
You just go. right, and again, he's got a table out in the mezzanine, so I encourage you to go out in there and talk to him and see that video he was talking about. Up next is going to be our trash and microplastics section, which should be really exciting. Our first speaker is Mr. Walter Yu, previously of Caltrans. I'll let him introduce his new position. Still Caltrans? Sorry. Come on. And Gary Conley. Sorry, I didn't know you were both here.
Okay, start us off. Okay, hello everybody. Walter Yu with Caltrans here in Sacramento, out of our headquarters office. I was formerly, while we were developing this presentation, working with our environmental division, working with our trash control efforts, and so that's statewide. Since then, moved on to enterprise data governance manager, so moving on to other things, but still involved with data. And with that, Gary Conley will come up.
Sure. Hi, Gary Conley with Second Nature. So I'm going to kind of set it up, and then Walter's going to knock it down as we do. And I turned off the slides. Okay. I'll just try every button until I get the right one. Okay, so Second Nature, Caltrans are, oops, a little closer, collaborating on a project to try to make trash data collection more efficient throughout the state. Lest we forget, this is the size of the problem. We have a trash gyre swirling around in the Pacific Ocean, about 88,000 tons, coverage the size of Texas, somewhere between California and Hawaii, and one of the important sources of trash to that gyre is urban stormwater. So in order to try to prevent trash from getting into the storm drain systems, 2015, we have come online the trash amendments. There's basically two ways for cities to come into compliance. Either you can install devices that have spaces no bigger than 5 millimeter to capture all that trash before it gets in there. Of course, you can't install those devices everywhere for logistical concerns and local flooding risks, et cetera. So where you don't install those devices, you have to rely on other institutional controls, whether that's street sweeping, education outreach, increased trash pickups. But we need a way to verify those things are actually doing their job. And so that's where these visual assessment methods come in, which is on the right side of the slide there. So pretty simple. There's just visual proxies walking around on a road, and those are connected to estimates of trash loading in volume per area. Set of colors up there going from green to purple, green being good, purple being the trashiest. The challenge with these methods is that trash on city streets is pretty variable over both space and time. So it's really dependent on the sampling design to ensure that we get the information that we need out of these methods, right? What we need is to be able to characterize trash conditions to a degree of confidence that's acceptable, and to be able to detect changes over time as we go forward. This, we're supposed to be eliminating trash inputs to storm drain systems within the next 10 years or so. Just to put this into context, here's some data from the city of Salinas. The left map shows those actual trash visual assessments. They're called on-land visual trash assessments, or OVTA. And then on the right hand, it's the quantified uncertainty associated with that sequence of measurements taken from 2017 to 2018, quantified as a Bayesian credibility interval. These data and methods are all just published in a journal article last month. Come talk to me afterwards. I can give you the link if you're really interested. But the punchline here is that those areas that we see that are the trashiest are also those areas that we have the lowest degree of certainty. So those areas that we need to know the most about, we're the least sure of. These methods, they're also embedded in a stormwater platform called 2Inform that cities throughout the Central Coast are using to satisfy their MS4 trash permit requirements. And now about 25 cities also in the Chesapeake Bay are using these same metrics to satisfy their requirements. But What's most important here is that it's actually difficult to get the type of coverage that we need to gain that acceptable level of certainty. So we need sort of an intuitive sense of what kind of coverage we need. These are the same data from that same study, and the graphs show the degree of spatial association from one trash condition measurement to its neighbor. And what we see, first of all, if we break it out by the different stormwater drainages, as we see in Salinas here, we see some heterogeneity, or you can be that the strength of that association might be between 60 to half a kilometer away. But most importantly, we see that the significance of that spatial association, or autocorrelation, we say, tapers off pretty severely, so that if your measurements are definitely more than 2 kilometers apart in a city like Salinas, well, you're probably missing some pretty important information. So we're getting the picture here now, right? We have high variance in the data, few measurements, certainty is low. If we have a lot of measurements and the variance is low, the certainty is high. So what we need to do is figure out a way to get greater certainty for those areas that have high data variance. Trouble is, it's expensive to walk around doing these trash assessments, so we need to figure out a more cost-effective way to do that. Fortunately, trash is sort of a unique pollutant. We can see it lying around on the ground there. That's great, and our machines can see it as well. So the terms artificial intelligence and machine learning are pretty fashionable these days, but really they're not very different from our more common basket of statistical methods that we use, right? We have a pile of data. We want to understand it to the degree that we can make some predictions in those areas that we don't have data. Not so different from regression analysis, principal components, ANOVA, things that we're all kind of more familiar with. In implementation, it's a little bit different because we need a lot more computational power than we now have access to, and we need a lot more data that we've just become more and more expert at managing. So it's really a problem that's pretty built for application of these tools. So I'm going to pass over to Walter to tell you how we actually do that, and also what we do when the trash AI becomes self-aware and decides to have its own ideas and become our benevolent robotic overlords, right?
Right.
Okay, I'm not sure if we figured that out yet. No.
Thank you, Gary. And as I think Gary pointed out and set it up the problem, we at Caltrans have to meet the statewide trash amendments, as do everybody else within the state of California, permittees. And so our challenge has been the manual portion of the visual assessment. So we have to go out and drive with a clipboard. So we started thinking about, as we're doing some analysis, thinking about AIs, it's come in vogue, how to use that to our advantage. So kind of a quick primer, one of the things we came up with, and you'll see that up on the slide, is object detection with computer vision. As you all have kind of come and know, image recognition is becoming very fashionable. And so it started out with classification, right? Like photos of cats and dogs, which is which, and then they moved on to object classification, which is what you see right there in the image there. That's just traffic counts, basically taking, detecting objects in a photo. They're getting better and better with the technology, so it's went from still images in video, and so it's already in use. So Keep America Beautiful has a reasonably large project on GitHub using Google TensorFlow, which is one implementation of this technology. Underlying, there's different algorithms that run it, but basically they scan and sweep an image and turn it into numbers, analyze it statistically, and give you back a score. What we can typically call a confidence interval, 0 to 1. Kind of as Gary was saying, just being confident of our results and making it more quantitative in nature, just because trash assessments right now are quite subjective. You're walking with a clipboard and you're scoring and you're comparing notes, and for us, we're driving, which it makes it even more challenging. Next, another already in use, as illustrated in a point, is just autonomous vehicles. We're heading in that direction, but guidance systems, object detection, again, plays a big part of that. At Caltrans, we're also using it for asset inventorying. So when we collect our LiDAR imagery, detecting objects and signs within our imagery, so it's already in use within our agency. Google Images and Facebook tagging, as you all are, again, whether you know it or not, it's image recognition and face recognition are becoming ubiquitous technologies. And so as that comes more mainstream, we'd like to leverage that. So our current process for OVTAs is basically we're using a protocol B according to the BASMA, which is the Bay Area Association of Storm Management Associations. We're using protocol B with a vehicle-mounted camera on a GPS, which takes photos every 1/10 of a mile, but we record every 1/2 a mile. So what you see there in upper right is an example. So we have the camera mounted, and it just points rear. We drive in the slow lane. Again, you know, the people, our staff or consultants that go out there to do the monitoring, they can only see what's out the window at one snapshot in time. So again, it's subjective, right? If you're driving hours on end. Human error, subjectivity, and I like to compare it as like almost being like a baseball umpire. You're trying to see things fly by 60 miles an hour, and you know, again, trying to reduce that human error and subjectivity. So we like to, you know, transition into basically, and I'll get into this, is using some image recognition. And on the bottom right there is just some basic object detection to, again, help us automate that task, remove the subjectivity. And then also this translates and plays into our asset management and resource management. So as we collect these scores, we're already loading it into our geospatial database for mapping for compliance requirements. But as we, you know, really fully automate this process, we could basically drive, do our field data collection, do our image recognition, and then plot those into geospatial data. So we're kind of end-to-end doing field data collection and digitization. So implementation, I think trying to make it, and disclaimer, I'm not an employee of Microsoft or spokesperson, but we did use Microsoft Computer Vision, what you see on the right-hand side there. We selected it because it's the most approachable. I did do some work on TensorFlow, and we've experimented with different technologies, but Custom Vision was just very nice to integrate with, and what you see on the lower right there is just a dashboard. So Custom Vision is, you know, free with a trial. It's powered by Azure on the back end, so joke around the office is that there's no excuse not to use it because we have Outlook, so we should be able to just log in with our GOT accounts and fire away. Of course, I got crickets, but you know, on with the show, right? So the benefits with Custom Vision, and URL super simple, customvision.ai. So you know, when you get back to your desk, fire it up. They got a free trial. Their documentation is really good. First foremost, there's no coding required. So, you know, we're looking at different technologies right now. We're also trying to pilot a study with Second Nature. And so as a part of that, we're looking at different technologies. But for now, Custom Vision, it's easy to share the model. So the workflow is that you're going to go ahead and upload some photos, train them, and then you'll have a trained model. And with that, you can share it. And that's the, you know, the reproducibility portion of it and being able to share. And then, as I said, being hosted on Microsoft Azure. And so, you know, it plays nice with most ecosystems, plays on the Microsoft platform. It's cloud-based. And so the examples I'm using are with Google Street View. But again, you can upload, and this applies beyond trash. So it could apply to aerial imagery or satellite imagery. And Microsoft also has plenty of examples using satellite imagery, trying to detect rooftops, or Kaggle has some competitions with trying to do ships in the bay. So those are common use cases. And of course, relatively low cost because it's hosted on Azure. So some next steps, you know, we're again doing a formal study with, you know, with Second Nature and with our one of our A&E consultants, Michael Baker, to more formalize the field data collection, our methodology. Also refining the model. So initial training we got with about 50 to 100 images. We got about 80% accuracy. So we'd like to improve and refine that. And then also we'd like to explore this as a part of the trash monitoring work group, which we had our, I guess, our first meeting yesterday, and wish to explore different protocols or different ways to implement these technologies. And the demo is on GitHub, so we'll share this out. But again, this speaks to the strength of this technology, is that you're able to, once you have your model trained, you can download the files in basically any flavor. You could do it as mobile, you could do it as a Docker image. And so this shared as a Docker image, but it also has an endpoint so you can share with your team. And with that, I'll turn it over for questions.
So these efforts are awesome. I'm curious how enforceable and how much of the cleanup you're actually able to do after starting to detect these levels of trash.
You can talk about cleanup.
Sure. So obviously this was focused on technology, but on the other hand, kind of shameless plug for Casca conference this year. We're going to talk about similar things, but kind of at a larger scale. And so this ties in with our maintenance forces. So on the back end, we have a full database for deploying and managing our maintenance forces. And so this ties in with that. So we have our geospatial database, and as we know where the high trash areas are, we can more quickly deploy our forces there. And so we create a feedback loop. We're going to send out our crews, do the cleanup, do an assessment in between, score it, put it into the database, and then compare it with what we're actually picking up. And then now that we have the visual assessments in between, it again reinforces that loop. Whereas before we were trying to estimate, we did an initial survey, and then we were using mostly the trash collection data, but now we'll put the two together. And then that way we can deploy our forces. And again, I think the proof is in the pudding, right? If we go out and do our visual assessments, then we can hopefully see that the trash level is dropping. So, and that's also our roadmap to compliance. So this is helping us. It's not our kind of go-to. We're still going to do our visual assessments, but this would help automate part of that process and reduce the error.
It sounds like this data set will be really useful for other groups that are also having to keep up with their compliance, since the areas that you're monitoring are going to overlap with areas that they're also managing. I'm wondering, what's your plan for sharing that information with them and with the broader community?
Well, I can talk about the data. I'm not sure it's clear, but what results from this study, the algorithm itself is going to be open source. So if anybody wants to actually use it on their own imagery that they collect, they'll be free to do so. In terms of the data collected itself, the cities all own that data that they're collecting. So I understand what you're saying. It could be really valuable in terms of like understanding how we can have data interoperability for different types of trash data that are being collected, but it's going to have to be a coordinated effort with local jurisdictions to be able to have those data available, whether it's Caltrans or a city or a county. I think, yeah. Yeah, it's a great question. I think the best venue to talk about is probably the regional stormwater monitoring groups. BASMA, we have one on the Central Coast, Mr. Swimp, Southern California analog. All those groups are good places to bring this up. I'm not, like I say, it's a great idea. It's just sometimes people tend to be sensitive about those data that are being used for compliance, just like their water quality data. Sure.
That's a very good point about open source. We actually, as we're piloting this study, we are doing a part of it internally for our own use, but we were thinking ahead, and that's why I shared the portion that I did using Google Street View, and that gets the starting point. Another good place is the trash monitoring work group, of course. We'd be happy to explore options, and we definitely don't want to be closed source in that effort. I've also shared this work with Code for Sacramento, so I volunteer with Code for Sacramento, which is part of Code for America. Shared the technology, and also Microsoft makes it very easy. They've been very open that they've generalized the algorithm behind it. So whereas in TensorFlow or other technologies, it takes hundreds of thousands of photos to get reasonable accuracy, Custom Vision does it with about 50 to 100 photos, and they're very transparent about it. Microsoft Research has white papers about the technology. It's basically a very generalized artificial neural network. And it's meant for consumer-facing usage. So again, encourage everybody that's looking forward in this area, looking to trim down some of your OVTA time, or at least to QA some of your work, to take a look at it, just because of the low cost, ease of use, and just ability to share. So yeah, I think we open up that avenue. I think also Keep America Beautiful. They have like a couple thousand images available up on GitHub. You just look them up on GitHub and you'll see the repository, and it's done in TensorFlow. They've shared the model. So again, it speaks to the power of this approach where it's reproducible, it's transparent, and you can then collaborate also with people not just on your team, but a larger community.
Is there also efforts to fairly specifically identify the pieces of trash? You know, is it people walking by and just throwing a lot on the street, or is it a neighborhood that just is leaving a lot of trash out? Because those management efforts are going to take more than just constantly going out there.
I think this gets into, I think especially in the Bay Area where we obviously have, that spearheaded our effort and, obviously rippling into statewide. I think it kind of borders on that, I guess politically or sensitive data. I think we just look at it as a standpoint of kind of a needs, right? So if we're looking at trash, and actually maintenance treats it like another objective. So they have their kind of regular level of service checks. And so they have a full program going, checking all assets. So they treat trash that way. And so we try to treat it the same. We try to look at doing assessments, being objective about it. Though, yes, we probably could. There's really two levels, areas that are high as far as location, but also within each photo. So we're actually doing an object detection. And as far as we're picking up, I think we'll start to, as we install devices, trash characterization, studies that we're doing with this automation, I think we'll begin to understand more of it. I think right now we're in a triaging phase of, okay, let's get the requirements, let's meet the compliance, let's get all set up. And as we scale, I think we'll get that data and be able to make more sense of it. So,
I think that's definitely one of the primary uses of this once it gets going, for sure. I mean, the compliance is one side, but what do you do as a jurisdiction to solve the problem, right? That's the other information that you get. And right now with OVTA, I mean, we have that information, right, in the platform that we have folks using. You have hotspots that would tell you which neighborhood you might want to focus trash mitigation efforts. It's just that you're only doing these assessments 2 to 3 times a year. So there's a time component that you're probably missing information that we could fill in with the automation, have basically fill the same function of informing cities for where they should focus their efforts, but on shorter time frames so that they wouldn't miss that information.
And this is Greg speaking from behind everyone, sorry. I'll just add that there is a trash data hackathon that we're going to do again. We did it last fall at SFEI's in Richmond office in October, I think it was. We'll probably aim for the same time for those of you who are passionate and interested in helping us move the ball forward on all this. I encourage you to follow the Twitter account that's associated with the hashtag for this event, so it's CA Water Data Dive. And we'll announce it more formally then. But one of the projects that my staff is working on is a trash tracker that's a street sweeper, computer vision, analog project, as some of these others that would have the potential to do, because of the, it's a little slower, a little different than some of the other methods of collecting the data. It may have the ability to also enhance the object identification. And this is what we did Datathon work on yesterday and prior, was then how do you bring that together with literati data, with other data, there's all sorts of really interesting stuff happening. So if you want to track the topic, follow us, and thanks.
and I think dovetailing on that, again, we'll be at the COSCA conference talking about similar topics. I'm always happy to talk trash, talk data with you guys. So look me up, Walter, you LinkedIn, Caltrans, pretty easy to find. And yeah, so thank you.
One last plug, I'd say also join the trash monitoring work group through the California Water Quality Monitoring Council. We're always looking for new members to the energy, so please reach out to those. And also, the kickoff, Karen Mogus kicked off yesterday and asked the council members to stand up, and there weren't any in the room yet, but we have some now. So I'd like to introduce Grant Sharp, who is our council member who is representing stormwater, and he also represents Casca. Peter Vroom, who's right here, and he represents water supply and aqua. And then there's also Jared Voskuhl in the back, who's represents POTWs and CASA. So if you have any questions, and you can see me, there's also our booth out there. Unfortunately running around and not there to man it a lot, but there's some information out there, and feel free to reach out to me if you want to join any of the work groups. That'd be great. Next up, Tony Hale from SFEI. Come on up, Tony.
I will. All right. Can you hear me? Let's see. Is this working? How's everybody doing? Everybody looking good? All right. Well, thank you for giving me the opportunity to speak to you today. I am here on behalf of a group of people. I'm working on a project that is funded by the Ocean Protection Council, the California Ocean Protection Council, in partnership with the State Water Resources Control Board, co-led by the Southern California Coastal Water Research Project and Shelley Moore, specifically, along with myself and my other team members, Pete and Lorenzo from the San Francisco Estuary Institute. So what I'm talking about today is actually just a piece of a broader project. But that piece focuses on remote sensing and machine learning. You'll find a lot of complementarity between what I'm going to be talking about and what Gary and Walter talked about. But I think also there'll be some new kind of angles on things, hopefully. And so the kind of main point here is that combining remote sensing and machine learning, you at least have potential for real breakthrough. And the project, as I mentioned, is designed to establish a library of standards that are really of known accuracy, precision, repeatability, and practicality for monitoring trash. So this project that we're doing is validating those methods. But then we're also looking at new and innovative methods specifically tied to unoccupied aerial systems or unoccupied aerial vehicles and machine learning. And so that's what we're talking about really today. I don't know if this was really legible to you, but I'm going to be kind of skipping through some things that Gary and Walter already covered, but the problems are common to both, that trash monitoring is really highly dependent on space and time. That is, being able to cover a broad area is very challenging. Being able to go out multiple times because trash is so ephemeral, it moves around, and so being able to kind of capture that a kind of synoptic view of the landscape is very challenging. And also achieving accurate volume estimates from qualitative assessments, so the rapid trash assessment methods, is a course conversion. And so is there anything we can do to refine that further? And then, monitoring is very time intensive. And Gary and Walter have come up with some really creative ways to try to address these challenges, and we think that we have as well. So the target audiences for what I'm talking about today, it includes local stormwater agencies, local monitoring programs, municipal, county, regional organizations, as well as statewide monitoring programs and citizen science groups. So it's really meant to embrace a lot of these different demographics. And specific to our project, the UAS task objectives are to identify the circumstances under which we can deploy unoccupied aerial systems. And you'll notice that I'm saying unoccupied aerial systems as a genderless term. It's synonymous with sometimes called unmanned, but we're trying to be a little bit open there. And also, we want to determine the optimal machine learning algorithms for identifying trash in the environment and determining trash levels in a given area. So when I'm talking about these kind of drones or unoccupied aerial systems, we found that using off-the-shelf inexpensive equipment, we can achieve quarter-inch image resolution. This is flying at 100 feet. So just by way of illustration, you have the above clip of the same area from Google. It's combining, what that's illustrating is two things. First of all, it's coarser resolution, but also it's a specific moment in time when you had tidal inundation, and you might want to see the same area at a specific moment. This is a wetland around the San Francisco Bay near Richmond. And you might also want to see a certain season. And so you can see you have finer resolution and it's a particular moment in time, particular season. But also you can go from being able to see things from a distance and really zoom in to, what used to be dots becomes ducks, and that's at a quarter resolution. You can zoom in even further. So what are our initial findings just from the imagery as we were flying over areas that had been inaccessible for the large part? There are a number of places where you can't traipse, you can't kind of walk across a wetland, but you can fly with the right permits. You can fly across a wetland. And so we found that what looked to be, pristine from the land view, looking out over this is Corte Madera Marsh, it turns out, you could spot quite a bit of trash just kind of nestled among the vegetation. And so these little dots there are noting the trash. And zooming in, you can see a tire, you can see, a bottle. And so part of the opportunity here is to deploy these, low-flying drones to be able to illuminate areas that have either been inaccessible and might be sinks for trash, or just being able to expand what can be walked in by a small group of people. And then taking that imagery and using machine learning to kind of further expand things, we can develop these algorithms to detect trash, just presence absence, and that's kind of along the lines, unless I'm mistaken, of what this first pass of what Walter and Gary were doing, but then also to address the question posed earlier, to do some speciation to kind of apply some basic categories to the trash as well. And from there, we can also calculate volume. So taking the detection of trash as objects and then making some judgments of volume. And we can also then calculate the trashiness level of the landscape. And we think that it's most effective to use machine learning to identify, is it effective to identify specific categories of objects, calculating volumes, or determining those qualitative levels? Well, we think, and can we achieve an acceptable level of accuracy and precision using these new tools? So we have some videos here, some of which are, can we just play that one? Is that playable? So this is just an illustration of Pete Gohanan launching a drone at the Corte Madera Marsh. We had a DFW spotter there. That was the other gentleman in the image. And he was there to determine whether we were disturbing the wildlife. And from the kind of sound of bees flying there that you heard, he determined that no, there was actually, you can't see it in that particular image. Thank you very much. But there was a heron just about 20 feet to our left that kept feeding while we were flying. So that's really satisfied them. Some of the challenges, though, of flying a drone in our current moment here is flying over open water is challenging. Not just because, if things go wrong and the drone, loses power, you've lost it to, sinking into the water, but also because then the results are kind of hard to stitch together into an orthorectified image. So there are challenges there. Monitoring over creeks is another habitat we're interested in, but those with real heavy canopy are difficult to kind of peer down through the canopy. Flying near buildings, you can't really fly over dwelling units. Flying in heavy shadow where the shadow is so dark that you can't really peer through it, and flying in inclement weather. Airports are an exclusion zone, right? So there are rules that prohibit you from flying near airports, and there's a kind of sphere of influence around the airport that you can't violate. And then acquiring permits is currently, it's a bit of uncharted territory, so every time you talk to a different agency, they have a different policy for issuing permits, and it can be very time-consuming to get those permits. Now, mind you, a lot of people don't bother to do that. There are a number, certainly, consumers, home flying, people who fly their drones for personal use, they're not getting permits a lot of times, and that sets a certain expectation and standard which we wouldn't want to follow on a professional level. So among the things we want to do is to adhere to the rules, to follow the rules for getting permits, and to always seek those. So with machine learning, we detect trash and we estimate those volumes. I'm going to skip through this because Gary and Walter covered it so well. But so the promise here is using this flying imagery machine, we can build a synoptic snapshot of the landscape, and then be able to refly again to build more temporal density at that low cost. And that's partly because with a lot of other methods, you might send out teams to be practical and capture the landscape, whereas you can send out 2 people, a pilot and a spotter, to do a much larger area than a team would be able to cover in a day. And we can also refly using the exact same flight plan to capture that landscape and see change over time. And we can also, because we can fly more space, we can see greater diversity across the environment. And you know, while we're using this imagery for machine learning, this can continue to be a library for people to go back and look at. So we are going to be sharing our imagery, and so that imagery. So just to kind of connect to talks before, Orestes mentioned STACK, and so the STACK framework is something we're looking very seriously into as a way to structure some of the imagery sharing we're doing. But our imagery, because we're collecting it ourselves and we're always trying to be as open as possible, we will be sharing both the machine learning algorithm and the imagery. And then you know, being able to collect the imagery for trash, but then also, you know, squeeze as much value out of that imagery as possible, being able to get structure from motion to have kind of what you might call, you know, a poor person's LiDAR, and to be able to kind of characterize different stream channels in different ways, as well as to vegetative condition monitoring. You can do a lot of stuff from the imagery beyond the trash, so it kind of adds even more value. So some of the initial findings. I'm going to share with you, you know, kind of by way of it seems like a tangent, but we did an experiment in collaboration with the California Tobacco Control Program, where they really wanted to, you know, as we were showing our early findings, they wanted to know what kind of tobacco-related trash we could spot from the sky. And so what you're seeing here in the image, believe it or not, tobacco trash isn't what it used to be. You have a combination of e-cigarettes. You have a lot of these, what are up at the top called juices, which are the kind of flavorings that you would put into e-cigarettes. Of course, every, you know, e-cigarette using adult loves, you know, cherry flavor and bubble gum, because these aren't targeting children. So, you know, when you see these, I must say, just as a sidelight, it's pretty scary to see all of these products. Then they're finding their way into the environment, a lot of times because kids are using them, and they go out to the edges of dwellings, they go into creeks, they deposit them directly into the places we're very often deeply concerned about. And so you find these products out there. So what we did is we borrowed these products, we didn't buy them. We borrowed them from the California Tobacco Control Program. We placed them out into the landscape in a seated situation, where we had a quadrat, and we placed them into the quadrat and carefully noted and counted just where they were, and we noted the numbers, types, volume, et cetera. Then what we did is we flew over the landscape at various altitudes, 30 feet, 60 feet, 100. Producing then these images at different resolutions, because, you know, resolution is really a function of distance when it comes to these particular instruments. And then we had someone note carefully kind of what was in each quadrant of the quadrat, and then also we had another person independently count on the basis of the images. So this is a manual process, all right? And so here's an example of the landscape. It's a grassy area, which adds some challenge, which is what we wanted. And here are the results overall. So how am I doing for time?
You're great. You got it.
Okay, good. So we have on the far left-hand side, you can actually see it better up here than I can see it in front of me. So we have the ground survey. That's kind of the ultimate measure of truth. And then kind of falling down as the altitude increases, you have the fidelity to that ultimate measure of truth, with the orange representing the total, and then we separated into two categories: tobacco trash related and then other trash, right? So for this purpose, we were interested in speciating along anything tobacco related, which, as you can see, it was already very diverse, right? You had little bottles and other pieces of trash. So I think it's pretty remarkable that we were able to get as much. Look at the kind of levels of trash data. It falls off as soon as you go from 60 feet to 100 feet of the blue line, the trash data, right? The tobacco trash. So I think that's pretty remarkable. And then when you go into the quadrants, the independent little quadrants, you can see that sometimes it was remarkably well aligned. So there is some variability just given the different types of objects you would encounter, but we did find that there was sometimes great alignment up to 60 feet, and we saw very little difference between the 30 feet, the very highly resolved, and the 60 feet, which was less resolved. You'll see that there is this weird anomaly in the upper right-hand corner where the total is greater than what was really there. So there were some false positives. And so it seems like if we were to do this in the wild, this was a controlled experiment, but if we were to roll this out, that 60 feet might be good enough, and that allows us to kind of cover more space. But we might encounter false positives. We found that time of day was a big driver of things. That is, shadows could influence things. Better to have overcast than super bright dark shadows. And then being able to capture the imagery and then rerun this experiment with different practitioners is potentially a very powerful diagnostic tool. And so what we have here, I'm now shifting to kind of imagery collection to looking at machine learning. So I would say that Gary and Walter kind of covered this, so I'm going to jump to the next slide. What we find is that in-person trash surveys provide a real great measure of truth for us so that we can validate our machine learning results against those on-the-ground surveys. So we're fortunate that we're coordinating with groups like BASMA, with the Southern California, the Stormwater Monitoring Coalition, and others to give us that measure of truth. And then we can apply some of these innovations. I'm glad it looks better up there than it does in front of me. But you have different object detection algorithms. We're using TensorFlow, just as Walter and Gary mentioned. We're not using Microsoft's, we're using the kind of open off the shelf. And that was because we really wanted to be able to share without concerns for any licensing. And I may be wrong about whether that's a concern for our colleagues here. But we have different ways that machine learning is used. Just to give you kind of taking a step back about how machine learning works, is that you have some input. You need to pre-process the data into some machine-readable format. That might be taking an image and kind of breaking it down into chunks or interpreting that image. And then you produce two different data sets, one data set used for training, another data set used for testing. Then the goal is to train the model. You train the model using different annotations, and then you can save that model. Once you have that model, that algorithm sometimes is the term used, then you can take your training data set and see how well it can predict the detection of what you've already annotated, and that gives you some measure of effectiveness. So this is an example of some annotations that we did. And you have the process for taking, I'm going to skip through this in the interest of time, I'm running out of time. So that's a restatement of what we did through this particular project. And what I'm showing you here is the annotated versus detected objects. So annotated is on the right-hand side, detected is on the left in these pairs of images. Along with the confidence interval. So you have here 100% plastic is the annotated. Here you have 81% plastic confidence interval on the left versus 100% on the right, and so on. So you can see sometimes it's successful in looking at this very stochastic image of grass and things mixed in and rocks and being able to pull out the trash. we're very pleased with some of the initial results of being able to fly this. It's not perfect, of course, but just the idea that it can distinguish between trash and rocks and other things in the environment is very exciting. And with some confidence. So the project timeline that we're working on is that we're kind of coming around the bend, as it were, where we have deployed we've done one season where we've done image collection, where we've developed the algorithm. The goal now is to do a little bit more image collection with the goal of annotating it and running it through the machine learning algorithm, not with the goal of further developing that algorithm, but rather for detecting trash as part of a testing phase. So we're very pleased with the way things are going, and we think that the work that I've presented today, I think really is very complementary to both the street sweeping project that Greg mentioned earlier, as well as the on-land visual assessment, this being more geared towards different habitats, wetlands and rivers and creeks and streams. So thank you very much. Any questions?
Hey, Tony, on the getting to the object detection to the volumes, Walter and I have talked a little bit about this. It sounded like from what you said, the approach would be to identify what the object is and know something about how big that is. And is that the way that you would get there?
Yes, exactly. Yeah, to get some sense of if it's a cup, then we know that an average cup size is this big. And then we can make some judgments about volume.
Got it.
Yeah.
Cool.
And being able then to do the volume-based assessments on the ground and kind of match it up to what would be predicted through the machine learning algorithm is important.
Right. Cool.
So Tony, if you're applying this in the wild, what's your sense about sort of false positive versus false negative? Which do you think is a bigger problem in terms of error rates, counting sticks as trash or missing things? Which do you think is a bigger problem in terms of the problem and the ease of solving that problem?
Yeah, that's a great question, Eric. I think that I think that false positives, that is the machine learning algorithm detecting just anything as trash that might be just natural, would be probably a bigger challenge to overcome. But that's not what we're seeing. We're seeing a slight undercounting of trash in our kind of initial pass through. So what we're trying to do is to kind of get, approach from the bottom of undercounting and trying to get closer and closer to what's really there. And the way that we do that is applying additional annotations and also tweaking the parameters. There's a kind of a process that goes beyond what we can talk about here of rerunning things through a graphical processing unit to further tune the algorithm after each test. So it's not really a matter, I think, of going out and collecting new imagery, but rerunning a lot of the same test imagery through the process until we can get a greater, narrowing the gap between what is really there, that measure of truth, and what we can see from the sky. But there will be some undercounting, I think, just because it can't be seen through the image, right? And so there's kind of two levels of undercounting. One is, and that's what the example of tobacco trash, where we were just having someone count on the basis of the image versus having the machine do it. We want to see, can even a human being identify the trash?
Hi, really good presentation.
Thank you.
I'm curious, what algorithm are you using?
We're using TensorFlow, which there are different, varieties of it, and different proprietary systems take TensorFlow and add their own special sauce into it. So Microsoft, Google, Amazon have developed their versions of it. We're using a kind of non-proprietary version of it, kind of closer to the vanilla tuning. All right, thank you.
Up next, and to round out our trash and microplastic session, Ms. Diane Lin from SFEI.
So now we're going to move from pieces of trash that we can see from a drone to tiny pieces of trash that we might need a microscope to see. And so I'm really excited to talk about our project monitoring microplastic in the San Francisco Bay. This is really a first of its kind type of study for microplastic where we're doing a comprehensive regional study. And it's $1 million project that's largely funded by the Gordon and Betty Moore Foundation and included the collaboration of a lot of groups of people. So I just want to acknowledge some of my primary co-authors at SFEI, UC Davis, Five Gyres, and University of Toronto. And we're really excited to work with Chelsea Rockman, who's a professor at University of Toronto in this project because she's a leading world expert on this topic. Microplastics is a hot topic. If you haven't noticed, it's being detected everywhere, not only in the Pacific garbage patch, but also in remote areas that we wouldn't expect, like the deep oceans. And the public is concerned about the microplastic that is being detected everywhere, and this is prompting action at the local, state, and federal level. So microplastics are small pieces of trash that are smaller than the definition of trash at the 5 millimeter. And they're essentially the detritus of modern day society where 350 million tons of plastic are produced annually. And you might recognize these symbols underneath plastic containers that represent the different types of plastic and whether it can be recycled. Similarly, microplastic can be identified based on the type of plastic, and we try to use that to link that with potential sources of the microplastic. And we're concerned about microplastic because organisms that ingest or are exposed to the microplastic, it can create physical blockage, or the microplastic can be a vector for contaminants, either contaminants sorbed from the environment or chemicals that are added to the plastic to give it its chemical properties, such as flame retardants. And even though microplastic is a new science, so we don't yet know what the ecological impacts of microplastic is, but meanwhile, we know that microplastic is only going to keep increasing, and once it's in the environment, it's logistically impossible to remove. We can't just pick them up. And so we're concerned about microplastic, especially in areas that tend to accumulate contaminants, like the San Francisco Bay. And so 3 years ago, SFEI and our partners at Five Gyres embarked on an ambitious study to do the first comprehensive regional study of microplastic. This is a $1 million project funded mostly by the Gordon and Betty Moore Foundation. And from the outset, the project was designed so that science could inform pollution prevention actions. Our team leaders are my colleagues at SFEI, Becky Sutton and Meg Sadlak, Carolyn Box at Five Gyres, and Chelsea Rockman at the University of Toronto, who is, as I mentioned before, a leading expert in the field. In our San Francisco Bay study, we wanted to sample different matrices to do a very comprehensive study. We collected samples from the Bay's surface water, fish, sediment, as well as surface water in the adjacent oceans. And to understand how the plastic is entering into the Bay, we also sampled wastewater and stormwater. So I'm going to briefly highlight some key preliminary findings that we're finding from our Bay water as well as pollution pathways monitoring. And for the full results, I'll talk about more about that later of where you can get that. Our surface water samples are collected using a manta trawl where a net is pulled over the water surface so that we're collecting water particles that are floating on the surface. and those samples are rinsed and into a sample jar and shipped to the lab for laboratory analysis. We collected samples throughout the bay and adjacent oceans, which are national marine sanctuaries, and we wanted to compare differences between bay versus sanctuary, dry versus wet season, as well as look at in-bay regional variations. The samples are shipped to the University of Toronto, where they are analyzed. The analysis involves trained staff who pick out particles that look like plastic. And each of the particles are characterized based on their color, their shape, and then measured for their dimensions. And so at this step, the count is of microparticles. And then a subset of those microparticles are further analyzed to confirm whether they are plastic using FTIR or Raman spectroscopy. And using that analysis, we can estimate a subset of the microparticles to be microplastic. Based on our analysis, most of the microparticles counted were plastic, with the exception of fibers, where dyes that are embedded in the fiber often interfered with the spectroscopy, and so we couldn't tell what type of plastic it was, but we could confirm that most of the particles were either anthropogenic or plastic. And did I mention that this process is really challenging? Each of our samples took about 30 hours of labor to analyze, and given we collected over 300 samples, it represented thousands of hours of work. Over 20 undergrad and graduate students did the work over the year to do this sampling, and so we're really grateful for all of the work that they put into this. And currently there are methods being developed to try to automate this process. But Chelsea found that for our samples, those automated software wasn't robust enough for counting and confirming the plastic. And so this was still the best method for our samples. So we found a lot of microplastic particles, which kind of explains why it took so long to analyze. And we saw huge variations in the abundance of microplastic. And it varied by over 3 orders of magnitude, from counts that were similar to our field blanks to counts of the million particles per kilometer squared. And so in this graph, these small circles represent less than 100,000, and these big ones are in the million particles per kilometer range. We did see a difference between wet season and dry season, and this was statistically significant. And we also saw greater abundance in the bay compared to the sanctuary, which was also statistically significant. And the most abundant type of fibers that we measured were fibers followed by fragments and foam particles. And a majority of the fibers were confirmed to be plastic. Now, to understand how the microplastic is entering the bay, we also sampled wastewater and stormwater. I wanted to mention that we sampled at 8 facilities for wastewater, and for stormwater, we sampled 12 watersheds. In our microplastic, we found microplastic to be really abundant in stormwater, and about half of the particles in stormwater were black rubber fragments that look like they could come from black tires. And the most abundant type of particles we saw were fragments followed by fibers. And this was in contrast to wastewater, where most of the most abundant type of particles was fibers. And this makes sense, considering that laundry is a source, could be a source of these fibers to wastewater. Now, when we take our measurements from our wastewater sampling and our stormwater sampling and extrapolate it out to the whole bay, we found that the stormwater load is 200 times that of wastewater in terms of microplastic loading into the bay. And this was a really interesting finding to us, because most of the research and efforts have focused on wastewater and focusing on microfibers that are in wastewater. And so this has really shifted our focus so that our next steps are to look more closely at stormwater, develop a conceptual model of what are the sources and pathways of microplastic to stormwater in the bay. So each of our particles are described based on their morphology, size, polymer, and color. And all of our data is going to be publicly available. And so we're trying to develop a standard vocabulary to share this data. And currently there aren't standard methods. And this is really important so that we can compare our study results with other studies globally. And I just want to mention this is one of the challenges with microplastic is that there aren't standard methods, not only for the data reporting, but also for the field sampling and the laboratory analysis. And so all of the methods that we've been developing in the study, as well as our lessons learned, we're working to make sure that, working with others to make sure that that supports the standardization that is being developed for microplastic monitoring. So that's a brief summary of the science portion of our project. The second portion of our project is to link science to solutions. I mentioned before that from the outset, our project was designed to inform pollution prevention action and to inform policy. And so this is a part of the project that is led by our partners at 5 Gyres. We convened a committee, a policy committee of stakeholders from various groups, including industry, government, foundation, and environmental groups working on pollution prevention efforts. Got them into a room in 2 meetings, presented them with our preliminary data results, and they used the data as a basis for discussion on policy management and worked to prioritize 10 recommendations for next steps. And so I'm going to briefly mention 5 of them. The group recommended a better understanding of stormwater based on our new finding that stormwater is an important load. And maybe in hindsight, when I listened to the trash presentation, maybe this isn't a surprise, but we didn't have any data to back this up. And so this was really a big shift in our focus. There's also a lot of efforts currently in terms of trying to reduce microfiber as well as reduce single-use plastics from food packaging. And so based on the abundance of fibers, fragments, and foam that we're seeing in different matrices in the bay, the group recommended supporting and joining these efforts in terms of the discussion. And as my co-session presenters and Tony, Walter, and Gary presented, there's a lot of trash efforts being done in parallel with microplastic, and better collaboration and coordination is recommended. So one example is at SFEI, our microplastic and trash project, both data sets will be uploaded to the same platform on CDIN. Last year, the California legislature passed a bill that requires the Ocean Protection Council to develop a management strategy for microplastic. And so this last recommendation I'm going to mention is to develop a Bay Area-focused management strategy for microplastic. Key messages, in case you spaced out at any moment. All my points are in this slide. Microplastic is everywhere. We found microplastic in almost all of our samples. And we're concerned about the microplastic that we're detecting because of their abundance and potential impacts on organisms. And it's challenging. Not only are there not standard methods that make it challenging, but just the laboratory analysis, like I mentioned before, is very time-consuming. Our San Francisco Bay study, where we did a comprehensive regional study of microplastic to understand its sources and pathways, is really the first of its kind. And an important finding that we found is that stormwater loading of microplastic is really important. And the science to policy framework that we developed, where from the outset we had a plan for delivering our science to discussions for developing policy, can be copied elsewhere. All of our results will be available in October. We have different communication strategies, including hosting a symposium, website, report, fact sheet, all of which will be publicly available, and we will also be uploading our data. With that, thank you, and I want to thank my collaborators as well as our funders. Any questions? Go ahead, Gary.
Wow, gosh, first, Diana, this is great. You're doing this work. It seems incredibly important, if although slightly depressing. And it actually makes, these litter problems we're working on seem fairly trivial in comparison for the challenges that we face to deal with them. The first time this came on my radar was just a couple of months ago when I heard an NPR story about detection of plastics at the top of the Pyrenees. Maybe those were one of the articles that you had up there. But I'm curious, in development of this conceptual model, so you found that stormwater is important, being that it's not only in the water, but it's also seems ubiquitous, floating in the air around us, and we're breathing it. Do you have any intuitive sense yet as to the relative importance of atmospheric deposition to the bay relative to coming from stormwater?
Yeah, that's a really good question. We didn't analyze air, but I guess we don't have data for that. And so the short answer is we don't, and that's a really big data gap that we want to try to address.
Zach Bradford, League to Save Lake Tahoe. We are currently working with Desert Research Institute on a similar study in Lake Tahoe, and we have a unique opportunity because we don't have we don't have treated wastewater going into Tahoe. So we're hoping to be able to differentiate whether we are having atmospheric deposition of fibers, at least, in the lake. So I'm definitely interested in talking more. But additional question, when you're looking at your protocols, were you able to find whether you could differentiate any bioplastics? Were you able to separate that out at all with any of the analysis?
So with the Raman spectroscopy, Chelsea has developed a library of different polymers, and so in some cases we can identify the types of plastic, and including bioplastics.
Hello, I think in the beginning, one of the matrices you said you looked at was fish.
Mm-hmm.
Could you talk a little bit about those results, what your findings were, and when those results might be available on CEDN?
Yep. So we collected fish samples throughout the bay. We collected anchovies and top smelt and analyzed I'm trying to figure out how I can be tall enough for this. Okay. So we analyzed microplastic in the guts of the fish, and we did detect microplastic in 99% of them. And all of our data will be available in October. But anyways, if you're interested, I can, I have a poster and stuff that I could share with you.
Hi. I was wondering what the resolution on these methods are, like what the method detection limit is, and if people who haven't studied this as in depth, if you have a sense of what the impact thresholds are for organisms of the bay or other perhaps impact thresholds I'm not thinking of.
Yeah, super good question. So there aren't standard methods, and so I think we're still, there's no defined method of figuring out what the method detection limit is. Data quality was really important to us from the outset of the study, and so we did collect field blanks and field duplicates to try to understand kind of what is the background contamination. And this is so new that a lot of studies don't even collect field blanks. And the problem with microplastic is that the contamination can be very sporadic. It's not like your typical contaminant, and so we're still trying to figure out how to just kind of how to estimate that baseline background contamination that's possible. And so I don't have a very clear answer, but we're trying to figure that out. Yes, so I guess for our field blanks, we did analyze them, and so we do detect a certain level of microparticles in the sample, so we would use that as kind of our background. It's different for each matrices because it requires different processing, and the lab can have different levels of cleanliness in terms of having, and so a lot of things can affect that, and so we would want to collect that blank for each type of matrices and each type of sample that you're analyzing. And in terms of the ecological impact, that's also a super good question. There's still not enough science out there, but we're still concerned, even as I mentioned before, because levels are only increasing, and so it seems like it would be more like a matter of time before we might meet those thresholds, depending on what when we have that data available.
I thought it was really interesting that you found that the majority of microplastics in the bay were fibers, but then when you compared stormwater to wastewater, it sounds like stormwater, which had provided the vast majority of microplastics, fibers are actually in the minority of what you found. So where do you think all those fibers are coming from that are found in the bay?
I think the wastewater could be a source, and as well as air deposition. We were also intrigued to find about those rubber fragments, but rubber tends to sink. And so I am just processing the sediment data right now, and so that could be a reservoir for those particles that we aren't seeing in the bay surface water samples.
Thanks.
Hi, I had two questions. One, I think it's fascinating that you were mentioning that you were going through and identifying the different types of plastics in the constituents you were finding, because then you'd be able to tell, is this from medical grade trash or is it from takeout food service containers? And that really helps for source control, right? Full disclosure, I work for a wastewater agency, so my first question is that data going to come out when all the data comes out in October? Just kind of breaking down, 5% of it was medical, 40% was food containers. Maybe it's the opposite. And then second of all, has there been any discussion by the financiers of possibly doing like pilot studies of source control for the microfibers? Like having wastewater dischargers, if you went in a sewer shed and had them use those kind of devices that have been developed for washing machines to really contain the microfibers that get, introduced into the sewer system, that maybe that could have a drastic reduction in the discharge versus trying to have wastewater plants. There's been some talk about, can we redo our wastewater infrastructure to catch microfibers? And as I'm sure you know, that is exceedingly complicated, if not impossible. So just interested in whether there might be investments in source control on the microfiber side.
Mm-hmm.
Thanks.
Let's see. So the first question was on
the plastic identification.
Yes. So all of our data will be available, and so we'll have that breakdown in terms of like from our analysis, what percentage was polypropylene, how much was polyethylene. In terms of we can try to link those with potential sources of like this type of plastic is used a lot in water bottles, but the plastic doesn't really say like I came from a certain water bottle and stuff like that. So that would be hard to do. And then in terms of microfiber reduction, yes, I totally agree. It would be prohibitively expensive to remove microfibers at the wastewater plant level. There is a lot of research trying to happen, like trying to figure out at what point would be effective in terms of removing microfibers, like in terms of the personal machine, within the laundry, with a filter and different stages, what the best intervention point is.
With that brings us to our first break. So I encourage you all to get up and stretch your legs. Be back in your seats at 11. We have a special mystery presenter at 11 that's replacing Jim Penny, who's on the program, so he couldn't make it. going to get started. And surprise, our mystery guest is Greg Gearhart.
Good morning. So we had a late bailout, and I volunteered, or was voluntold, to jump in and fill the gap. So I apologize in advance. I threw these slides together really quickly. It's an amalgam of other talks I do, but it was inspired by some work I've been doing the last 6 months. And I'm going to fly through the slides because I have way too many to cover, but these slides will be made available. There's a lot of links and a lot of things on them. So this is about how water data is a really cool scientific and technology-based thing, but it really, at the end of the day, from our perspective, it's part of a government service. And it's part of a government service or a history of services that have essentially led to racial inequity throughout the country and even in California. So these red line districts and what have you that establish some of the basis for which nowadays are, if you line up where our treatment plants are, if you line up where the industrial sites are, where the air deposition is happening, it tends to line up very closely with old areas of the communities that were essentially created in a way that encouraged more concentration of people with non-white backgrounds and non-English speaking backgrounds. So there's a lot of work to try to undo some of this, and this is a bit of an explanation for where the Cal EPA and the water boards are trying to go in this water data world, which is actually a really important interface. So this slide's kind of busy. I'm just going to, again, these slides are available, but Cal EPA has a cohort. It's year 2 of our cohort for this thing called the Government Alliance on Race and Equity. It's a national network. And so this is the year 2. Year 1 was made up of planning activities. Year 2 is about implementing, and there's some early actions here. The principles of this are really to try to make a commitment for achieving racial equity throughout the work we do. And this is, again, the concept is that all the government services, when they stack up together, they essentially represent the government together. We all think of our agencies as different, but really the health, the education, the corrections, the justice, the environment, the whatever part of the government interface in that community stacks up to be one, essentially, face of government. So we need to figure out how to work together to undo some of that stuff. So the priority actions, we're looking at some demographic data for our human resources at Cal, the workforce stuff. There's really 3 areas of action that we're taking. One is on workforce. One is on recruitment and promotion workforce. One is on workforce, the rest of the workforce, and building capacity and training. And then the third area is on language accessibility. So with that in mind, we're working on deploying some early actions associated with the recruitment, and we're looking at the workforce data sets, and I'll go through those really quickly. So these data sets are available. They were turned into machine readable about 3 weeks ago. With the help of Cal HER, we now have the whole state of California's workforce by these kinds of parameters. So this is a busy slide. Again, you have access to it, but you can filter, and this is a really beta Power BI visualization I made, but essentially you can look at classes of workers. So you can say all the managers and supervisors, all the people in legal, all the people in architectural and engineering classes, and you can also filter by classes, and you can filter by agency, and you have 7 years of data here. So it's actually pretty interesting when you start thinking about, I don't have what California looks like. I know people always want to see a comparison, but the reality is this is just fascinating data to look at by itself. It speaks its own volume. So this is a slice of, what did I do here? Water board data, all employees. And then as you go through, here's water board, all legal. So it's mostly white. Gender is about 70-30 maybe. And then here's the administrative services category. So it starts to look more like California on the racial identity, but the gender's significantly skewed towards females. So again, the point is we have to start thinking about these things. I don't really want to make that the point of the presentation, but it's a foundation. I'm starting with that so that then I can talk about what work we're trying to do to engage communities differently with our water data. So the first thing to understand is that open data is a big part of this principle. So we're trying to make all the data open and accessible, and just putting data on a website doesn't make it open and accessible. So this is being driven by statute in California. We have AB 1755 that was adopted a couple of years, 3 years ago or so. We're now coming up with the deadline September 1 to publish all of our open water data in California. 3 state agencies named. There's also, the Water Board adopted a resolution to support that. The State Board has principles that sort of dictate how we're going to do better data management and how we're going to achieve better transparency through open data publication of our data sets. So both of these are available in links. One of the directives of the resolution was for my office to work with the other offices to evaluate the data readiness for open data publication, the data management, how do we improve data workflows and data flows themselves throughout the organization. And so to do that, you guys know what open data is. So to do that, we did a bunch of interviews. We interviewed every part of the State Water Board organization, a little bit of the regional board interface, but just that alone was originally, it's a list of 135 people to talk to. So we got to about 100 with the help of Rosic, and Rafa really led the charge in my shop, but we ended up talking to over 100 people. We gained a lot of really interesting insights. We wanted to slice at different levels of managers, executives, staff, programs. We wanted to hit every major program area, every division. So we talked to budgets, we talked to the MPDS, we talked to the whatever folks. So we're still out there doing a couple more interviews, but we're basically done. And so we gained insights. We learned about the inventory so that when we said we're ready to publish our open data, these 30 data sets are ready. The rest of the 150 or so are going to take some work to get ready. So we needed to have an idea of what the work ahead of us was. So that was the inventory. We also gleaned some really low-hanging fruit opportunities of what we can do differently and better to make our water data both more useful to us and our program data more useful to us, but more importantly to the public. So this is a data viz of the interviews, just kind of fun to look at, but it's broken down by the divisions and offices and the percent that we've talked to and that we didn't. This is old, so it's been updated, but I just kept the same slide. So again, one of the really interesting insights that Rosic helped develop was the connectivity of our databases to our fee. We're a fee-based organization. We're like 90-something%, I think, fee-based organization, as you heard Joaquin say yesterday. So the importance of our databases for fees, the connection is many of those fee regulatory measures or regulatory devices say things like how many acres of disturbed land are you disturbing, or how many head of cattle do you have at your confined animal facility, or all sorts of data elements. And so we had to build a robust data system throughout the organization to support each one of those important fee pieces. And so where those tendrils touch our databases, we actually have high quality data. We have program knowledge from executives down to staff that are like very well informed on what that data element is, how to improve the data quality. And so the message to me was one of hope. If we can do that for fees, maybe we can do it for other things that are important too. We also found that there's a lot of mandatory reporting. There's a lot of data sets that sort of live in strange places, like PCs and spreadsheets and probably even manual data sets. And then we just learned a lot of interesting things, and we're going to write this up and make it available pretty soon. So a data viz on the fees and how they connect to our different databases. And eventually we'd like to put this together with the actual budget. Wouldn't that be cool to see like which database produces the most amount of money at the Water Board, which data elements are associated with which funding sources and things like that. So there's a lot of room to go with this. There's our enterprise architecture for the Water Board. So this is the problem statement. We have somewhat arbitrary boxes and tuna cans up there, but this is really this is the world. This is an updated version of this. So we have 120 some odd enterprise applications. Probably about up here, there's maybe like 30 core databases that are applications that store important, really, really vital stuff. But we need to fix the data flow between them. So we're trying to improve the data flows using open data and some approaches you've heard me talk about. But this is basically the data lifecycle from top to bottom. We're trying to improve the data flow at every level and improve the data quality and speed it up so that you actually have feedback loops and encourage better data quality collection, better methods, new methods come in, but you also have new needs for visualization. So this is really that life cycle. And the interface that's really important to me is that open data one. So stage 3 is publishing it, because until you do that, nobody quite knows what's in the database, and nobody quite knows what the problems are and what's the first one to fix. So this idea of making flat files and automating the publication of our data is super, super important to the future life of our data. So we're trying to build capacity too at the water boards using data literacy as sort of like the key word. We have a pilot training program that includes a component of an online assessment and content delivery, but we also are designing some classes at different levels, including workshops with data scientists on R, Python, JavaScript library, like whatever the issues are, artificial intelligence. We're going to try to bring these topics in workshop fashion and deploy them to staff that are interested and available. So I'm going to show you some screenshots from our online tool. This is a product called Tuva. We found them a couple years ago. We're working with them to expand this. They are now part of a nationwide Department of Education initiative that is putting data literacy tools in all the schools. This is really what they started, but this is an interactive site. So essentially, we gave them some of our data. They created some of these interactive platform areas with our data, and then they ask questions about it. So you see, for example, the question is asking something about that data. The person answers it based on their knowledge. You're going to be able to assess different things like their basic understanding of survey design, their basic understandings of statistics that are involved with some of the questions and answers. Plotting, data visualization, literacy is being assessed here too. And the idea is that then you can deliver content that's aimed at that particular area for that group. And you can deploy this quickly for large teams that are working on projects too. So we're about to roll out, we're on phase 1 of this. We have a larger phase coming in the next year. These are just more screenshots. So at the end of the day, we hope to make ourselves accountable via our performance report. It's our history. We've been doing this for 10 years. Right now, it's focused on a lot of outputs and outcomes and jargon that isn't really as accessible to people, let alone the people in the communities that we serve that are probably the most deserving of our attention. And so we're trying to make improvements to the performance report. So this is one of the examples. It's a really bad screenshot I made, but you're actually seeing it first for anyone in the public. The next year's performance report is going to be in Power BI. It's open data, and we're piloting some of these areas like inspections. So you can actually see where the inspection was done, under which program type, at what date, who was the inspector in some cases maybe. So this starts to really provide granular data that could geospatially line up with some of those areas where the communities that we want to have different kinds of engagement activities with. So this is the inspection card. This is a look at our enforcement resources. So again, you start to see some really interesting information about where the enforcement resources are done when you line that up with the enforcement activities, the priorities of the different enforcement initiatives around the state. This is one way to start looking at the data too. Near-term projects, I'm going to continue working on, this is about 30% of my job now is on race and equity work, which is super interesting and fascinating, and it dovetails really nicely with the rest of OEMA's mission, which is making water data accessible to everyone. So we built a team to look at some data science elements, and we actually also sought out some data science teammates from national and state cohorts. So we're building up these capacities right now. I showed you that Power BI of the CalHR data set. That was actually something I did in my spare time. And we hope to get more people doing actually better work because I'm not a data scientist. One of the cool things that we're working on is Latin American indigenous language speaker data gathering so that people who are speaking indigenous languages from different parts of Latin America, Central American, Mixtec and Zapotec areas and what have you, they've brought their language and they really are in islands of accessibility. So we're trying to build a privacy-sensitive data map that would allow somebody or anyone in California government who wants to know if they're trying to reach a certain community, where would they have to find these people or what kinds of language accessibility tools would they have to build for those communities. So we're also looking at more red line data sets and libraries. This is a shot from that hackathon that I mentioned yesterday in Stockton. It was a water hackathon. This is the junior high team, Girls Who Code, and they were a winner, and they were awesome. We're going to do that again. Their next topic is harmful algal blooms, and so I'm going to be trying to bring in some extra help from people who want to work on engaging the communities around Stockton. This is run by Restore the Delta. I have the link on the bottom, and they will be running it again, so we're helping them. Here's some more links. The race and equity links are interesting. The national one has lots of resources. There's really good videos out there on systemic racism, what it is, how to understand what the red line issue was and government's role in sort of creating some of these underserved parts of our world. And then the performance report and the other things. The GitHub site has all sorts of things, including work from yesterday's Datathon. So that's it. I'll leave you with a quote from Alexander von Humboldt, one of my favorite data scientists. If you've never read about Alexander von Humboldt, you should definitely go find his book of, what was his book was something about nature. And then there's a new book interpreting his life called Inventing Nature. And he really set the stage for Darwin and the others. So he's become a bit of a hero of mine. So I'm open for questions. Any questions?
Greg, you got a pretty good overview of these sort of disparate types of data that we're trying to use together. What do you see as the primary difficulties between using the different tuna cans together for interoperability between them? Just as an example, in looking, I remember digging into the eRIMS data set up there, the water rights database. I remember digging into that and finding that while there were locations of withdrawal points in streams, everything was coded based on a water right ID, which reflects basically the objective of the creation of that data set. But for using that data set to support modeling efforts, well, it wasn't as useful anymore because I didn't actually know exactly where that water was being withdrawn. Are there similar types of difficulties that you encounter in trying to use them?
Yeah, each one of these databases was built in its own schema or model, if you will, and it was built at a time when relating everything to everything was really the most important thing, or being able to relate everything to everything, so you could have a water right ID associated with a point of diversion, associated with a beneficial use, associated with other data elements, responsible parties, all sorts of things. So it was built in this sort of data model that mimics CWIX, but it also wasn't really ever activated as a data ecosystem. So a lot of your problem that you're describing has to do with the fact that folks didn't really use it much for a while. They're using it more now, but in the beginning, a lot of those data elements that were anticipated weren't even occupied, or the data quality was really poor. A lot of the reported amounts of use, for example, if you added up, it exceeded the annual rainfall by like 1,000 or something like that, right? So there was just a lot of data quality problems that we hope to improve by making flat files and accessible eRIMS data. But that data model problem is common, and we've actually, we beat our heads against the wall for a few years about how do you go back and enforce better data models on existing databases. And we're looking at WADE and WAMDAM and some of the work that Adil talked about yesterday, as well as some of the work in Australia with Peter Taylor and Cicero gave us some references of how they used idealized data models to now drive data towards. So hopefully we would have a more interoperable ecosystem in the future, because we're going to take things like regulatory data, inspections. Everyone in our building does inspections, but they probably have a different database and a different schema they use to track them. But at the end of the day, they're inspections that we do. So if we can build an ideal data model for like regulatory data and observations data and fiscal data, for example, then the database structure itself isn't as important, because we're going to work on transforming the data up into the idealized models. So that's kind of where we're thinking right now.
Hallelujah.
Any other questions? Yeah.
I'm wondering, is there one person who really understands all of these data systems that are available through Cal EPA, that if you have any question about where the data is, how you can get it, help you navigate through the different people that you need to go through? Is there any one person who really understands the system that you can just, anyone can go to and get help? No?
No. Can you build us a bot that does that, though? No, honestly, so Walter's got a new job. It's enterprise data manager or something like that at Caltrans. The Department of Transportation is wise to do that. I don't think the boards and departments in this building are thinking about assigning one person within each agency, let alone at the agency level. But I think for us to sort of get at what the point of my talk was about, of being better service providers to the communities in California, that's one of the most important jobs, is like a data engagement wizard or some sort of cool title like that. And then they get to know all this stuff, and they get to also push internally for publication of high-value data sets. But it doesn't exist right now. In the meantime, call Rafa. Any other questions? Yeah.
This is in regards to reaching out to a diverse set of people to pull them in and have them looking at what's going on and get everybody involved. My background's in molecular biology and genetics, and human development and development from conception to death of all model organisms. One thing that I was interested in was that women, if you're looking to pull women into the scientific side of it, they develop three-dimensional thinking more strongly in their 20s. What happened to me was somebody from Berkeley came to me when I was doing well in college and said, let's talk about what you're doing, and pulled me in, which changed my life, really. I wouldn't have known. My dad's a scientist, but still, there was nobody but saying, wow, you're so good in chemistry. So looking at people after they're in high school, after when they're showing signs in early college, and having maybe working through the schools to reach out to those people and go into science and be advocates and leaders in their families, communities, groups, might be an avenue to start reaching out, looking at the when people develop certain skills is as important as reaching out. If you told me at 15 that this was the degree I was going to get, I'd have laughed, really.
Well, I'm glad you're here. And thank you for that. I don't even know what I can add other than just reinforce that sometimes sideways engagement at different levels of education is really important. And we found with this hackathon in Stockton, for example, that the connections to the community colleges there, I mean, all the really excited data science, water people I've run into in the last couple of years have pretty much come through a community college system. And so, there is a lot of transformation that happens later in life. So I applaud that and thank you for speaking up. I think I'm over time. So I want to thank my funders, you. So bye.
Thanks, Greg, for that last minute, but great presentation. Next up, we have Dr. Christine Lee from the NASA Jet Propulsion Laboratory.
I also have a short person challenge there. Hi, thanks for having me. So you'll see that the title of my talk is a little bit different from what's actually listed in the program. And that's because I wanted to talk about the entire project that covers not just turbidity, but other water quality parameters as well. We were selected for an award about 1.5 years ago through NASA to try and improve the utility of different types of remote sensing data on enabling water quality monitoring, water resources management, focusing on California's water systems. And so we have been working rigorously towards that, and I'm happy to share some of those results with you today. And so here is the obligatory NASA Earth Science fleet of all of the different Earth Science satellites that we have currently orbiting the Earth. There's over 25 of them, and of those 25, about 17 of those spaceborne sensors can be used to better understand different types of water cycle variables. These satellites are put into space to help us understand Earth system science and to advance our knowledge of how the water cycle is changing. So looking at meteorology, but also looking at land use and other parameters as well. And so one of the challenges in trying to leverage remote sensing information lies in the fact that these systems are designed to acquire data on a global scale. And so they're designed to be able to cover the Earth at a certain temporal resolution. Depending on what parameter you're focused on, there are different types of resolutions that we're concerned with, such as spatial or spectral sensitivity and so forth. So through the combination of airborne and satellite remote sensing, we can get a better understanding of how water cycle processes are changing on a global scale. But of course, water resources management decisions are not always conducted at that scale. It's conducted at a much more localized regional level. And so many of these decisions rely upon ground-based observations, modeling to help inform decision-making at those scales. And so the question is, how do we combine these data sets and leverage the in situ networks and also leverage the remote sensing to build an enhanced water quality monitoring program? So similar to what I was just saying, a lot of these remote sensing systems are designed for different types of parameters, but we still feel that we can make a substantive contribution to water quality monitoring by leveraging them. And so, for example, a lot of the parameters that we can resolve using satellite data might be designed to study open oceans. And the trade-off there is that we might not get the spatial resolution that's needed to look at smaller inland water bodies, resolve coasts. And another really popular or commonly used platform is the Landsat series, which is considered a land imager. And so some of the trades there are that we might not get the spectral resolution or the sensitivity that we need to really resolve aspects of the water column. But by looking at a suite of these instruments, we could still develop water quality parameters that could be potentially useful for improved monitoring. And so the project that we've set out to do is really one of trying to increase accessibility and also see where remote sensing data could be used to support water quality monitoring, and then to demonstrate those utilities by partnering with different decision makers and agencies and define use cases with them. And so we're working with a variety of partners, several in academia, so UC Merced, Erin Hester's a co-investigator on that program, and you'll hear from her next. We're also working with Oregon State University, but a couple of our key partners are the Metropolitan Water District and the California Department of Water Resources. And we continue to have additional conversations to try and expand that kind of partnership group. And I also wanted to mention 34 North, who we've been working with as a way of getting our data archived and available more broadly through the Bay Delta Live portal. As I mentioned, we're focused on California's water systems. So the 3 different sites that we're focused on in this project currently are the San Francisco Bay and Delta, Lake Oroville, and San Luis Reservoir, as we've noted up there. Okay, so these are the 3 water quality parameters that we're currently focusing on for this project. They are turbidity, chlorophyll, and water surface temperature. We picked them because they exist at kind of this perfect intersection between being able to be reasonably resolved using satellite and airborne remote sensing, as well as being management relevant. And so some of the different types of management decisions that we're trying to tie these data with include managing for minimizing smelt entrainment, improving delta smelt habitat, looking at export of phytoplankton and the actions that control that, as well as precursors for harmful algal blooms to minimize public health risk. And then lastly, looking at thermal risk of these endemic species. And so just a brief overview of some of the principles behind our methods. And so the way that we measure ocean color or water quality information is by looking at optical properties of the water column near the surface. And these are governed by what we call inherent optical properties. And so these are parameters that you can actually collect if you were to go out on a boat or install instrumentation on a buoy. These are measurements that you can take while out in the field. And the actual amount of absorption and backscatter that occurs in that optical water column is dependent on the parameters that are in there. So for example, looking at the amount of sediments in that water column might change those properties, looking at dissolved organic matter, algal particles, and so forth. And then from the satellite or airborne sensor, we can then derive remote sensing reflectance from the air. And so by relating these two different measures of remote sensing reflectance, we can then begin to develop these algorithms for estimating things like turbidity, chlorophyll, turbidity and chlorophyll. Temperature is a little bit different. And depending on what your water body looks like, you might find that whatever is dominating that water column at a particular area can be resolved by looking at different remote sensing reflectances. And so in an area that might be dominated by chlorophyll, you can actually see that response in the reflectance spectra, as you can see here. And so by looking at different pieces of information across these spectra, we can begin to derive information from those and infer these water quality properties. And so turbidity is the first parameter that I wanted to share some results with over the delta. And so one of the key elements of the project are seeing how well the remote sensing derived measurements of these water quality properties relate to ground-based measurements, because ultimately we want to show how well these algorithms perform relative to what the management-based standard is. And so what we do here is we take the satellite-derived estimate of, for example, turbidity. We extract those pixels those pixels that are over the stations using the station lat longs, and we're getting data from CDEC. So all of the turbidity data that are available through CDEC. And then we also aggregate the turbidity data from stations, and then we do a direct match of a comparison, and we have so far been looking at regressions across the delta. And so I know this might be hard to read, but this table is just to kind of summarize some of the key differences between the two different types of data sets. And so when you're looking at the water quality stations, you're primarily working with point data. You might have on the order of 100 stations that are distributed throughout the San Francisco Bay and Delta, which is actually considered very well instrumented. But it is meant to represent, over 5,600 square miles of that system. But it also has a very high temporal resolution, so taking data every 15 minutes. On the flip side, when you're looking at remote sensing data, for example, with Sentinel-2 or with Landsat, you're getting an acquisition every 4 days or maybe every 2 weeks. And so in comparison to the 15-minute aggregation, you'll see we counted up about 55 clear day incidences between 2016 and 2018. Instead of point data, you're looking at pixels. So an average over, for example, 20 meters by 20 meters. And then instead of 63 to 100 stations, we're now looking at 36 million pixels or points that you could potentially use to better understand the water quality conditions of that particular acquisition. And so this is what it looks like when you dump all of the data over 3 years, comparing the satellite-based turbidity on the y-axis and the CDEC turbidity values on the x-axis. I put the horizontal and vertical bars just to kind of show where the kind of most relevant NTU values are for the delta smelt, so at 12 NTU and at 80 NTU. But I was actually very encouraged by this, even though it might kind of look like a mess to everybody else, because it showed us that there was at least an order of magnitude, there was a reasonable estimate that we could derive from the satellite data in comparison to what we were seeing on the ground. And so we started to divide up and try and understand what would be causing the scatter in that previous plot. And so one of the first things that we did was look at these relationships by station. I know this is also hard to see, but here's a sampling of stations. In the middle is the map of which stations were selected for these different panels. Again, was very encouraged to see that they were actually hovering pretty close to the one-to-one line. But you'll see that there is quite a bit of site-to-site variability over this 3-year period when comparing the satellite results to the CDEC results. And so we can continue to try and understand this. And one of the goals of being able to understand this is so that we can then say, when we're delivering the satellite data to 34 North to be archived on Bay Delta Live, we can actually provide more information of, when the data could be applied for certain uses, what are the kind of constraints around that and limitations around that. As I mentioned, we're also looking at chlorophyll A. And so the example that I showed here is showing the change in chlorophyll extent in 2017 as it matched up with the different public advisories that were put out, that were put out by DWR to warn the public that it was risky to swim or to go out into San Luis Reservoir. And one of the kind of key takeaways from looking at this was that you actually see an onset of an expanded bloom, or the onset of a bloom occurring prior to when the notifications started going out. So can we work with DWR to see if some of these satellite data could be used to support some of their advisories and other updates and notifications around this issue? And so we've been talking with DWR to establish just that. And also beginning conversations for Oroville as well. This is just to mention that we have a proposal out to also look at harmful algal blooms in Southern California reservoirs in partnership with MWD and EPA. Still waiting to hear from that, but if funded, this would be really neat because we would be not only enabling earlier detection of harmful algal blooms, but the UCLA component would allow us to actually do on-site point of detection of toxic species that are present using a deployable flow cytometer that also leverages some machine learning to detect those harmful species. So this is the last product that I'll mention. So we're also, of course, looking at water surface temperature. This has a lot of implications for thermal stress on different fish species. Not just in the Delta, but in other water bodies in the State Water Project as well. And the two spaceborne instruments that we're looking at for this are Landsat 8, which is satellite, and EcoStress, which is an instrument on the International Space Station. And we're looking to see, of course, how these water surface temperature measurements line up with the CDEC temperature measurements, and as well as trying to understand whether they can be used for assessing ecosystem restoration outcomes and export control actions. And so here are some of the early results from comparing Landsat 8 to the CDEC and bulk temperature measurements, as well as looking at the 5-year record from Landsat 8 and looking at a time series. And so so we want to continue to dig into these data to see if we can now drive better understanding of what's happening within the systems. I saw a paper that was published pretty recently that did a really nice job characterizing the upper thermal tolerance of the Delta smelt, silverside, and an invasive bass, and showing that the silverside and bass had a much broader kind of range for thermal tolerance than the Delta smelt. And so kind of the next set of figures and analyses that we would like to do is to actually produce maps of those, that thermal safety margin that corresponds with those 3 species as well. So here's just a quick snapshot, one from winter, one from summer, and you can see that in that right panel figure that there are a lot of areas where in the kind of yellow to red, which is approaching the maximum thermal tolerance of the Delta smelt. I mentioned EcoStress, which is an instrument on board the International Space Station, which is actually sampling any given point at different times of day. And this will allow us to do a better characterization of what we're measuring as surface temperature versus what's happening in the bulk temperature, which is what CDEC is getting at. Okay, so as I said, this is all underpinned by the fact that we want to try and build a platform that is an enabling platform that can then allow more people who are interested and could be benefited from using remote sensing data to access those data easily. And so I'm happy to take questions if I can, while this is playing, if I can get it to play. And so this is just one example of the dashboard functionalities that 34 North is building using remote sensing data. And so one of the final deliverables of our project is to have all of these data sets archived on Bay Delta Live, but also to establish that mechanism for them to continue automating the production of all of these data sets as well. And so this is a dashboard that matches up the satellite data to the CDEX stations. But if you're familiar with Bay Delta Live, they have an entire kind of suite of different water quality products and other types of water data that are available there. That was probably mine. So thank you, and I'm happy to take any questions.
Thanks, Christine. Can you talk a little bit about the spatial and temporal resolution issue? So, we're looking at, changing species distributions at the statewide level, and what we really need in temperature is sort of the ability to look at the smaller creeks and streams at a daily time step to get, moving averages. And so that's been really one of the limitations and has driven us to use modeling air surface temperature and translating to water surface because of those spatial and temporal limitations.
Yes, so that is one of those are the trades that are made early on in designing some of these satellites, is that depending on what it is that you want to focus on, we have to trade off sometimes on the spatial side, sometimes on the temporal side. But we do actually have an opportunity to provide input into kind of the next generation of NASA satellites that are in development. And one of them is called the Surface Biology and Geology Designated Observable. It's a NASA speak for, anyway. And so that is actually slated to be one of the next NASA Earth science missions to be formulated, developed, and built and launched in the next, optimistically, 7 years. And it does have a thermal component to it. And so if you'd like to provide that level of feedback on the needs as far as the spatial requirements that are needed, as well as the temporal requirements that are needed, we can actually, it's the perfect time to feed that back into that design process. But we're aware of the constraints.
Thanks, Christine. That was really neat. I'm wondering if some of the scatter that you're seeing is due to scale differences between what you're measuring with the satellite and what you're measuring on the ground. Scale differences between.
Oh,
I mean, are you possibly
yes.
Is some of that scatter possibly due to just smaller scale heterogeneity in the measurement that you couldn't possibly avoid with the water samples on the ground?
Yes, so it's important to stress that these are not the same types of measurements.
Yeah.
One is an average over a pixel, and one is obviously a point measurement. We're also hypothesizing that another issue is the fact that a lot of these stations are really close to land.
Mm-hmm.
And so you get an effect that is due to being close to land, whether it's scatter from the land directly itself, or if we're actually selecting pixels that somehow are mixed pixels that are intersecting with land. And so those are all issues that we need to look into further.
Because all else being equal, you might come to the conclusion that, gosh, the satellite measurement could be a better measurement of the turbidity in the water than
Well,
scoop sample.
our messaging is such that we're complementary
Okay.
with the point data. But depending on what your application is, one may be suited more appropriately than the other.
Yeah.
Thank you. All right, well, my info is up there in case you want to follow up. Thank you.
Next up, we have Aaron Hestier from UC Merced. Oh. There we go.
Helping the short people comments. Right. Thank you, Dr. Lee, for that presentation. That was excellent. And I would like to point out to the community here, for those of you who are aware of some of the hyperspectral remote sensing that's been going on in the Delta for the last decade, led primarily by UC Davis, the SBG, this Surface Biology and Geology mission that Christine mentioned, will be a hyperspectral type Landsat. So if you're interested in those applications more broadly, Dr. Lee is the applications point of contact for NASA. So please get in touch with her beyond just temperature if that's of interest to you. So we're all very excited for that development. So I stand between yourselves and lunch and myself and lunch, so I will try to be quick. And I will preface this by saying I am not a geochemist and I am not a mercury expert. So I will do my best to answer questions about the mercury side of this. I am a remote sensing expert, so grill away if you'd like on that. So this project that I'm about to describe was recently funded by the California Department of Fish and Wildlife under the Proposition 1 funds. And we have several colleagues who've been thinking a lot about this, including a group of folks from the California Water Science Center and several scientists from the Menlo Park Center as well. And the basic premise here is that we are going to try to help develop optical proxies for mercury in the water column to help enable more efficient and cost-effective monitoring to complement the regional monitoring program in their efforts in developing and TMDL and managing mercury in the Delta. So some of you have seen these, wow, this is like, that's much better, okay. Some of you have seen these warnings out there in the Delta about eating fish in the Delta and advisories against doing so. A lot of fish around sport waters contain mercury. However, in the Delta, people who are sport fishing are disproportionately consuming those fish compared to other places in the state. And indeed, it's estimated that these people are actually taking in more than the daily recommended EPA dose for mercury. And many of these households that are consuming this fish come from disadvantaged communities and disproportionately have women of childbearing age or children in the house who are potentially consuming these high levels of mercury. So the Delta is a place where we want to start to really focus some of our efforts in having well-informed advisories so the public can make good decisions about fish consumption. So methyl mercury in particular is of concern when we're starting to think about developing these advisories and managing for mercury in the system. Methyl mercury has a bioaccumulation factor that is incredibly high, meaning it moves up through the food web. And we've been using largemouth bass as an indicator for methyl mercury in California surface waters. The two scatter plots on the top here show the the methyl mercury concentration in fish flesh, and it shows that it correlates relatively well to the aqueous methyl mercury. And so fish tissue is considered one of the main monitoring mechanisms for methyl mercury in the system. And these lower sets of scatter plots come from a paper that shows that juvenile largemouth bass and silverside fish mercury concentrations correlate very well with the bass concentration. So what we're seeing is that these are good indicators of where mercury is entering the food web. There's also been some concern that some of our attempts to restore wetlands around the bay and delta may be increasing mercury transport and potentially serving as production for methyl mercury in these systems. So what we're seeing on the left here is an interpolation of the sediment concentrations of total mercury from Alviso Slough down in the bay. And this study showed that as you restore a wetland and you start to get some of those nice channels that you'd like in a wetland, that scour also may remobilize some of these legacy mercury that occur in the sediments. And if this occurs in a wetland, these wetlands may have some of the biological conditions necessary to methylate that mercury and really amplify it in the food chain. This is unpublished data from my colleague Mark Marvin de Pasquale that shows that we have much higher rates of methylmercury in wetlands relative to some other systems from the South Bay. However, data on the effects of wetland restoration are limited because measuring mercury is difficult. There's also evidence that spatially the concentrations of mercury around California and around the Delta are not consistent. And there are some observations that there's been some areas of persistent low mercury relative to others in the Delta, but we don't fully understand what these transport mechanisms are. And if we're going to get to a place where we can fully understand what the spatial and temporal patterns of mercury are so that we can create those well-informed advisories for the public as well as start to effectively manage mercury in the system and understand how to restore our wetlands in an effective way, we need to start thinking about developing cost-effective monitoring technologies that's going to help improve our understanding of where mercury is, how it's being produced, and where it's going. So there's been a lot of work done, a lot of that led by the USGS at the California Water Science Center to conduct high-frequency monitoring. And these new high-frequency sensors create both temporally and spatially detailed water quality data, and many of these are underpinned by optics. So what you're seeing here in the middle is one of these buoys that you can deploy that creates very high-frequency 15-minute data, as Dr. Lee alluded to, for a range of non-mercury water quality metrics that we all have been using and talking about with the CDEN and other data sets. You can take these same instruments and you can deploy them on a boat with a flow-through system so that you can get very high spatial resolution transect mapping of surface water quality. You don't get the temporal resolve, but you get that spatial resolve over the course of a cruise. We then can use satellite observations to fill in these gaps that we have from the point high continuous frequency sites and those very detailed spatial transects to help us give that overview, that picture of high spatial information. So what we're looking at here is a map of total suspended solids concentrations estimated in the Delta. This is from the summer of 2015, where the French Space Agency deorbited one of their operational satellites into a lower orbit and acquired images of the Delta every 5 days at a 10-meter resolution. So this is an interesting experimental data set for us to start to understand what high temporal frequency, high spatial resolution remote sensing can do to start to fill in some of those gaps. So I'm just going to take you through a time series, watching how the total suspended solids concentration progresses and moves up and down the lower estuary through the course of the summer. So Dr. Lee gave a really nice overview of how we get to water quality from space, and so I won't belabor this point too much. But essentially, what we're taking is the remote sensing signal. So these are the apparent optical properties. This is the radiance and reflectance that is emitted from the water surface. And we are then linking those to the inherent optical properties, either through those models, the BB over A plus B that Christine showed, or through machine learning techniques and other statistical approaches. And then we can back out what the physical biogeochemical properties are. So we're estimating backscattering from the remote sensing signal, and then we're using that to get to total suspended solids. So this is a nice image from the Venetian Lagoon that has kind of everything you'd want in one system. So it's a pretty image to show both what the suspended sediments in the system might look like, the dissolved organic substances that cause absorption like organic matter, algal activity which both absorbs and scatters in the water column, as well as shallow waters which can create reflectance due to the benthos. Now, when we get to these physical and biogeochemical properties from the inherent and optical properties, often these transfer coefficients to get there are regionally and temporally dependent. We are not yet at a state where we can do this globally with one consistent algorithm. And so working at this regional level to a level of accuracy that matters for a given end use case is where we are still with the community. And so thinking about those transfer coefficients, here's an image of Mercury, not quite from space, but from an airplane. And so what we have done here, this is work led by Cedric Fichot, who at the time was a postdoc at JPL. And the JPL flew this very high quality sensor called the PRISM sensor, which is a nice experimental sensor for us to begin to develop these algorithms over the San Francisco Bay Delta. And they took this relationship that they developed from in situ measurements between filter passing methyl mercury on the x-axis, on the y-axis, and dissolved organic carbon measured from point measurements and then analyzed subsequently in a laboratory. And they took that model and applied it to the remote sensing imagery using a regionally dependent transfer model to create our first remote sensing image of filter passing methyl mercury. This isn't from space yet, but hopefully one day we'll get there. So if we start thinking about these relationships, in order to get to that mercury from space, what we really need to do is we really need to start thinking about these relationships between mercury and other non-mercury water quality metrics. So what we are seeing here are two scatter plots. The first on the left is many samples, about 355 samples, collected over a variety of different seasons and different years from April 2005 to June 2011. And this is across many different environments in the San Francisco Bay and Delta. So these are lentic environments, wetland environments, open water environments. There's some relationship going on between these constituents, but it is not quite as simple as just a linear model. If we consider only the open water sites in this, we start to see a much more straightforward relationship, although we can certainly talk details about log-log transforms and how we might want to model that more intelligently. So encouragingly, if we take a look at this figure again on the left, what we're looking at is, again, on the y-axis, the filter passing methyl mercury concentration. And on the y-axis, we're looking at absorbance at 254 nanometers. This is an optical proxy for dissolved organic carbon. And very encouragingly, that A means that it's an absorption term, which means that it's more directly linkable in that remote sensing model that we're working with from a physics perspective. And you get a straight up linear relationship with a much higher R squared. So we're starting to think that this might be feasible. Now, we're also interested in the total mercury that's evident in the water column as well. This is the filter passing total mercury on the y-axis on our figure on the right. And we see that there is a linear relationship there too. Furthermore, we are also interested in particulate mercury. And there is some evidence that it might make sense to actually think about measuring mercury from a gravimetric perspective rather than a volumetric perspective, because you're actually saying how much of the particulates are mercury, which might give you some more indication about what's going on in the food web and how that's bioaccumulating. This is data, again, taken from that Alviso Slough site, that restoration site in the San Francisco Bay, where we are seeing the red dots are the upper location in the slough, and the blue dots are the lower location in the slough. And this is made, these measurements are made across many different days over the course of a year, across different seasons. And what we see is a very strong linear relationship between both the particulate total mercury concentration and the particulate methyl mercury concentration in the water column, and the total suspended solids in the water column. And the mercury is highest when you have low total suspended solids. Basically, when conditions are quiescent, we're seeing when we have the most particulate mercury in the system. So these relationships between different mercury species and different water quality concentrations can be predictive, but obviously there is a lot of variation. Each one of those very kind of simplistic regression models that I showed you had different coefficients, it had different performances, and while they were robust across, a large range of conditions, there's a lot of work to go to really start to model what this is going to look like. And so this gets to what we're starting to do in this project. We're going to co-locate 4 continuous high-frequency monitoring sites at 4 regional monitoring program stations in the Delta, where we will begin to make these better quality predictive relationships between the optical remote sensing, as measured from both in situ sensors, hyperspectral drone sensors, we can talk about that another time, and satellite overpasses to, again, improve those remote sensing products that Christine's project is starting to develop the workflows for. And then we can start to also develop those those better predictive models that are more sophisticated than just a regression between both our particulate and our filter passing methyl mercury and total mercury, and the non-mercury water quality measurements that we're making from these high-frequency instruments. So things like total suspended solids, but also optical backscattering, which is measured in the instruments and is much more relatable to the remote sensing. Dissolved organic carbon, measured in the laboratory, but also measured through fluorescence dissolved organic matter sensors, which is, again, or absorbance, which is much more related to that remote sensing mechanism. In addition to those high-frequency continuous monitoring stations, we will go out and we will do full tidal cycle sampling events where we will actually measure over the course of an entire tidal cycle how these relationships vary, and we will be doing these spatial transects with matchups with the satellite data. So we're going to build this very big data set in order to truly capture the range of variation so that we can make a more predictive and robust model that will enable us to have optical proxies for mercury in the Delta. So in order to tackle this challenge, we're going to use optical sensing. This can provide rapid, low-cost monitoring technology that's going to really strengthen the rigorous regional monitoring program. This isn't going to replace it. We call these proxies, and we believe they will be proxies. So these high-quality sampling programs need to continue to really make sure that we're in compliance with TMDLs, but we hope that these technologies will help fill in the gaps and provide a first-order estimate of what surface mercury is doing in the water column. And again, we really hope that by mapping this mercury, we're going to start to tackle some of those science questions around transport and production, and ultimately serve many of the disadvantaged communities that rely on this information to make informed decisions about their fish consumption. With that, I will take any questions, or if you want to take off for lunch, I can just hang out and answer questions while you all eat.
I'm curious, how do your 2 variables that are explaining the mercury, the total dissolved solids and the total organic carbon, how did those relate to one another? Are they also linearly related in a positive trend, or are they opposite?
There is a whole bunch of covariation between all of these variables, both the suspended and the dissolved matter. And then the one factor that I didn't bring into this that we're also going to be looking at is chlorophyll production, because that determines some of the organic matter concentration and particulate organic matter concentration, but not all of it. And they are probably also important for part of the mercury methyl production. So it is a much more complex linear problem, or a nonlinear multivariate modeling problem than I've painted with some pretty regressions. So yes, and fortunately we have the biogeochemists and the geochemists on our team, mostly at USGS, who are going to help us tackle those issues.
Cool, thanks.
Hi, my name is LaDonna Williams, and it's good to see your project actually focus on disadvantaged communities. In the past, we had been working on fish consumption in our area here. We're in Vallejo, so between Vallejo, San Francisco area, on the advisories. And then we worked with another organization on testing the fish. But what we noticed is the fish that they targeted was not fish that African Americans ate. So I was just wondering, are you set on the type of fish that you guys do test, and are you open to adding additional species or fish to that list?
So, excellent question. This is beyond my expertise, so I will give you a half answer. I'm a scientist and I'm a remote sensing scientist, so I'm not actually in charge of those fish monitoring programs. However, there are several people here who are involved in the regional monitoring program who can probably speak up to that if anybody is here who wants to raise their hand. However, I think the evidence is that basically, based on those first sets of graphs that I showed, that what we see in that indicator species, the bass, is reflected when they test other fish species. And so they feel like it's a pretty good indicator across many species in the system. But certainly from a human health perspective and really targeting food sources, I'm sure quite a lot of work will be done. We're focused on the fish. We're trying to develop these sensors that you can just put in the water to directly get an idea of the concentration. But that is certainly an area of concern because ultimately we're doing this for fish, wildlife, and human health. So, I'm definitely interested in hearing if anybody knows more about that.
Yeah, I can say a few words about that. Hi, LaDonna. I don't know if you remember me from the Fish Mercury project back around 10 or 15 years ago. We worked together on that one. Yeah, I'm the lead for fish monitoring for the Bay RMP and the Delta RMP. And in the Bay RMP, we have the funding to look at a variety of species, and we work closely with OEHA, the Office of Environmental and Health Hazard Assessment, to provide data to add more species to the advisory for the Bay. For the Delta RMP, the budget is a little leaner, and so we're focused on just basically one species, the largemouth bass, because it's a great mercury indicator, and we don't have the funds to look at a variety of species throughout the Delta. I'd like to catch up with you and hear about what you've been up to in the past decade or so, and we can talk more. Yes, Jay Davis. Yeah.
Thank you, Jay.
So with that, lunchtime. Again, there's several restaurants listed in the program on page 4, I believe, kind of by food type. So please be back by 1:25. We're going to start promptly at 1:30, starting our ecological flows portion of the symposium. Thank you.
Okay, I'll just go talk to them. Because the other thing is the thesis.
I know the contracting small pieces. Got a table out there.
Yeah, I'll find them. I'll help them. I'll figure out how to get registered.
Okay, welcome. We're going to get started here. So welcome to the afternoon session. I am not Nick, but Nick had to run do something else, so I'm going to moderate the afternoon. So we're excited with the agenda as usual, and the first one on the panel on the agenda is the ecological flows panel, and it's going to be really interesting and well coordinated. And actually, I don't really have to do anything because I think Eric Stein's going to do most of my work for me. Waiting for Eric to come back, but we have. Oh, that's the next one, the panel. So the first speaker is actually Jacob Katz, and he is from Cal Trout. And Jacob, are you here? All right. Does anyone have any questions? Or feedback? People enjoying this event? All right, well, we'll follow up with some sort of official feedback form. But Eric, did you see Jacob Katz outside by any chance? You're right. I was going to get started at 1:25, and you're right. Nick did say 1:30, didn't he? Boy, that was a big expectation to just sit there for 5 minutes. Yeah. I think you're right. Another one? No, I'm done. I'm done doing that. Although so yesterday's Datathon, a quick download from what I know is that every team made progress, and every team sort of like made a little bit of different progress. So if you didn't go up and look at the boards, you should try to do that before you leave. There'll also be a follow-up. We're going to post sort of a summary of each team's progress. But in particular, I noticed that the CCR team, wherever its stuff is, Consumer Confidence Report, which really needs to be renamed something like, how's my drinking water and where's it come from, or something like that. That project made a lot of progress from what I could see. They literally developed a data schema that might work, and I think I even saw a demonstration of an app. So that was pretty cool. The source water, where's my source water come from? That is the most complex question you could probably ask in California from a data structure standpoint. And I think they made progress, but it's going to need a lot of iterating. There are some examples, and I put them on the GitHub site for each one of these projects. Anything I could find that was kind of like it. So on the what we're calling CCR in quotes, there's a company called Varuna that makes us interactive CCR, and they were going to try to participate, but they were overcommitted this time. So there are other examples of people out there trying to do the same thing. We will make progress. On the source water one, there is an article that I saw that summarized for Southern California where the water came from, for which part of Southern California you were a consumer of water. So it literally mapped out Colorado River water consumers, State Water Project water consumers, all the way back up, in some cases, I think, to the reservoirs. So that was the inspiration for, hey, if somebody can write a article about that for Southern California, maybe we can build the data structure so that the rest of the state could have the same level of, and that's a pretty high granular report, if I remember correctly. It doesn't get down to pumping water station, neighborhood kind of zone granularity, but there's a lot of work to do on that one. It's really cool that they made progress. The trash one, you heard a lot about the trash one, but another pitch is that in October, we're gonna do the trash data dive again, so. Jacob Katz. Usually, this isn't an issue on the 1:30 speakers are usually there. Let's flip it around. Can we do the panel first? Eric, you good with that? Allie said, I'm helping kick it off. I know, but she can't make, she's doing something in a parallel world. She can't be here.
I know, because you double booked her.
I know.
I mean,
Oh, Jacob's here.
okay.
Oh, okay.
All right.
Back to plan A.
I was going to have to pretend to be you. Come on.
Jacob Katz. Here he is. I'm Greg.
Hi, Greg. Thank you so much. Apologies to everybody for that. Sometimes, you think you give an hour to it, it's going to be extra, and you use your whole cushion right up. Yep. All right. Slides. That's me. Really pleased to be here. Thanks. It's great to feel like there really is not just a water community here in California, but a water family. That we might not all know each other, but increasingly I really feel that there's a common set of objectives, a common tool set that we're discovering together about how to unlock a whole nother set of outcomes. Realizing that the past binaries aren't necessarily true. That we can find ways, supported by rigorous science, supported by refreshing and politically potent coalitions, to create a new solution set. And in that way, this talk is going to be a little window into some of those epiphanies from an ecological perspective. I'm asking you guys to, take off your boots and come out barefoot into the puddles, because that's what this is really about. We're gonna talk about the power of puddles for a little while. And believe me, I'm as surprised as anyone else when to hear these words coming out of my mouth, that puddles have incredible power. What do I mean? Well, let's take a little journey. Let's figure it out, right? So here we are in Sacramento. In the Sac Valley, as we know, today is one of the great mosaics of agricultural production, right? The Central Valley as a whole, not just a bread basket, but the fruit and nut basket, this incredible, intensely farmed landscape with vibrant agricultural rural communities, right? But once that same landscape was a mosaic of wetlands. Really, the Central Valley can be thought of as a bathtub, as this incredible dynamic landscape that was represented and really is defined by its wetlands, right? And they were not always in the same place every year. There were different kinds, whether it's emergent marsh, whether you're talking about flood basins of tules that were 14 feet tall and literally, 100,000 acres. Trying to imagine what it would be like to go through a landscape like that, where Fremont, with his men crossing the little valley where 580 goes now, right, out past like Livermore, right? That was all tules. And they got lost out there, and they standing on the saddles of their horses, now where it's all auto dealerships and new condos, standing on the saddle of their horses, they couldn't even see the top of what is now called Fremont Peak. Just right there. That's a little valley. You start to think about the size of these wetlands that were right here in Yolo across the river in Sutter. This was an incredible, dynamic, wet landscape, right? The very names of the valley counties, right? Before they were counties, they were flood basins. Colusa, Sacramento, Yolo, right? These actually define the Sacramento itself. And what's a flood basin? A flood basin were these low-lying, shallow areas adjacent to the river that every spring, every winter, as the rivers swole with either rain or snow melt, the water would spill over those natural levees and fill these ephemeral lakes. Sometimes they weren't so ephemeral. Sometimes the valley was water from Red Bluff to Fresno, from the foothills to the foothills, an inland sea, right? But generally, it was a wet place. And the development of this place can really get summed up with a single word. It's not reclamation, a word I've always had problems with. I don't know what, I think that we're doing the reclaiming now. But drainage, where water used to spread and slow, it now, whether it's on the roof of this building or the impermeable street outside or any orchard or any farm field, parking lot at Safeway, the bypass itself, right? All engineered to drain as rapidly as possible. That is where we're starting to get into this idea of what is a puddle, What place does the puddle have on the landscape and as part of this incredible system? So ubiquitous drainage, right? We've lost 95% of our wetlands, and this incredible assemblage of fish that were adapted here in California, 129 different kinds, adapted to the patterns of water flowing across this diverse landscape. They have felt that alteration, right? Over 3/4 of those fish species are now on a pretty sharp trajectory towards extinction. That's much greater impact than a cursory look at the California Endangered Species Act or the Endangered Species Act would actually give you. But when you dig in, you see that there's a universal theme. Our native critters can no longer recognize the river systems that they evolved in, that they're adapted to. Their keys, honed by eons of natural selection and evolution, no longer fit the landscape's locks. We can do something about that. So out of what is a very bleak conservation assessment, the first of its kind, comes a real hope. A hope that if we can pivot towards process, if we can start to understand the underlying causes of environmental degradation, of aquatic ecosystem collapse, we have a chance of actually remedying them. And we're in the valley. Let's talk about Chinook, right? This was once the most diverse run of Chinook, still is the most diverse run of Chinook salmon on Earth. 4 distinct different runs of fish. Fish named for the season in which they come out of the salt and into fresh water, right? But all of those, save one, are facing extinction. That other, the fall run, is what the entire commercial fishery is dependent on, but it is in turn dependent on hatcheries. So we have a large effect of that landscape scale alteration on these iconic fish that have an outsized effect on California's economy, in that water passed from where it's more abundant in the north to where it's needed in the south is really the fuel of the 5th largest economy on Earth. And one of the chief impediments to moving that water around is the now ubiquitous ecosystem collapse, epitomized by this plight of fish, of Chinook. So a little story. I'm probably rambling on. What am I doing on time? Do you know?
5 minutes.
I have 5 minutes, great. So my really good friend and colleague, Carson Jeffries, did his master's with Peter Moyle down on the Cosumnes River, the last undammed river system to drain into the Delta. And he found a really remarkable thing there, which was that in one of the last remnants of floodplain left in the valley, when compared to the river channel on the left, he caged fish in both of those environments and came up with a very iconic picture, one that all of you have seen before, but one that is worth repeating because it's a window into not the past, but our future. This is what a Sacramento salmon should look like as a juvenile. And it looks like that because it's been exposed to a functioning aquatic environment, a floodplain that actually has the capacity to cycle energy from the sun into plant matter, into a microbial food web, into bugs, into fish, birds up there. A very simple food web, but one that's really important and one that happens ultimately in puddles, in wetlands. And so the work that I've been in the midst of for the last about decade or so was to look at how that same food web might be managed, might be mimicked on this intensely farmed agricultural wetland that now represents the Central Valley. Yes, we want to restore anywhere we can functioning small natural habitats, but we must recognize that here in the Central Valley and really globally, the human footprint and human management is ubiquitous, and that if we don't find ways to welcome the wild back into the matrix, if we don't find ways to make our working agricultural rangeland, timberlands more beneficial to native species, that we don't have the tools to succeed as conservationists. This is This is a necessary expansion. And so initially, what did we do? We went into the Yolo bypass on Nags Ranch, just across the river from here. Flooded rice fields after harvest to mimic that natural floodplain process, right? And the fish grew exceptionally. I mean, we were essentially asking people to give us Chinook to put them in a mud puddle. You can imagine that the reception was a little chilly. These pictures helped a lot. But I think this next experiment, which we did in the winter of 2016, really encapsulates the story, right? So we took the same idea of floating pens. In the lower left there, you see a plastic mesh 2 by 2 by 4 foot pen, in each of which is 10 tagged fish, electronically tagged juvenile salmon. The same setup was put just on the other side of the levee in Tule Canal, and then just on the other side of Tule Canal in the flooded rice fields out on Nags Ranch. And the picture you might come to expect at this point, those on the floodplain turned into what we call floodplain fatties, growing much, much quicker than those in the river. But why is critical. So 700% greater growth in just 3 weeks. That's phenomenal and has an incredible impact on the rest of that fish's life. But why that is super important. So on the right, you have a beaker of water representing the density of invertebrate life in the Sacramento River. The middle is the canal, which was 600 times more bug biomass than the Sac River. That seemed like amazing, right? But then you have the floodplain, 150 times more. That's 15,000% greater access to energy, to food, to the basis of life, to biomass. That's a fundamentally different system. And we have been denying our fish that food resource with our levees and canals and diversion. We separate the river channel where the fish are from the floodplain where the food is made. One of the fundamental reasons that water on the floodplain makes that food is the residence time of water. In blue, you see the Sac River, the water's turning over in that location where the cage is every couple seconds. It's about a half a minute in the canal, but on the floodplain, it's several days. Historically, I was talking about those, this mosaic of wetlands. It would have been months of inundation. What does that mean? That means that is the time needed for sunlight stored as plant matter, right? That's what plants are. They're batteries. They're storing that solar energy. You need that time of breaking that detritus down so that microbes can turn it into bugs, and bugs can then be turned into biomass. That's the fuel, the engine of productivity that once allowed the Sacramento Valley or the Central Valley to have 2 million Chinook. Also, equally important, of course, is the fact that algae floating in that water is harvesting winter sunlight and turning that also into food. So you have two different mechanisms: breaking down summer sunlight stored as plant matter and capturing winter sunlight with algae. But the key here is that in a river, there's very little surface area caught between two rip-rapped steep banks to harvest that sunlight. The moment that water spreads and slows, you have a physical environment that's really able to harvest that energy, right? And so we're talking about, it's not rocket science, but it's physics, right? We're talking about energy and biomass. With cutting off over 95% of our wetlands, we've substantially reduced the energy that flows into our aquatic ecosystem. With 5% of our wetlands, it should come as no surprise. With 5% of the energy that we have 5% of our endangered fish stocks. That is the system we built, it's a system we designed, and we have the capacity to improve it, right? So sunlight makes sugar, right? Sugar is broken down by microbes to make bugs, bugs make fish. Floodplains are essentially the solar cells for that aquatic experiment. Both summer and winter's solar energy is captured out there on that floodplain surface. And without it, we're running out of energy, right? So critically, though, it doesn't happen instantaneously. It takes time, right? Making fish takes time. And that is absolutely critical for many of you that are working in floodplain restoration now. because the current crop of design plans that we tend to be working with are about getting floodplains wet and much less about keeping them wet. And the benefit really happens as a function of time, of inundation. So frequency and inundation duration are absolutely key. And this is just a good way to, might you be able to press play on that? It'd be down in the bottom left. We can just go out on this one. Because this is the making of a floodplain fatty. If you take a picture of a fish on a daily basis in one of these pools, this is what happens. It doesn't take a lot of time, but it does take time. And so this general idea that residence time needs to be incorporated into the way we manage water, that, rivers, I think up until this point, there's been a general understanding that, salmon belonged in the river and the river belonged in its banks. Neither of those things is true, and a central tenet to that is that where possible, increasing the residence time, the flow time of water across the landscape is a good thing. And that will apply on valley floor floodplains, it'll apply in mountain meadows, it'll apply in estuarine environments, that we really have to think about bringing duration into our calculations. So I think I'm out of time. Thank you.
Do we have any questions?
None. Awesome.
Is your research in lakes at all? Are you
Can you repeat the question?
The question was, are we working in lakes? And the answer is no, that we aren't specifically. What's really important to note, though, is if you study lakes, right, limnology, often called the queen of sciences, I think you'll open up your limnology textbook, as Charles Goldman at UC Davis always put it out in front, and the first chapter is going to talk about how residence time is the basis of productivity. What I'm talking about is not scientific breakthroughs. It's just the fact that we haven't been thinking about it in the context of river management, and the interface between water and landscape. So yeah, we're not working in lakes right now, but the same ideas do hold in those environments.
Hang on. Microphone, sorry.
Hello. So the smolt out migration period, is it different for smolts in the floodplain versus the river and canal? Meaning, like, do they both migrate out at the same time, or is there a delay for the fish on the floodplain and out migrating to the ocean?
Do we need to repeat that? No, not now. Okay. So timing is an incredibly important aspect of diversity. But really what we're looking for is a diverse landscape that then can support diverse life histories, diverse behaviors of these fish. That includes the timing. What having floodplain habitat up in the upper basin, in the Sutter, in the Yolo, what that means is as fish are out migrating out, they're taking more time in different locations, and they're expanding that portfolio of outmigration timing. That's the basis of resiliency. What we have right now is a system where, for the most part, the outmigration is hatchery influenced. And when we open our hatchery doors, when we let those hatchery fish go, if we hit the jackpot, if it's a big water year, if the wind's blowing out in the Gulf of the Farallones and there's upwelling and a lot of food there, you can get a really big return. If not, you get very little. What we're looking for is a more resilient system where you have more diversity of timing, you have more diversity of life history, you have fish in different places in the landscape taking advantage of different patterns. And so what we see the floodplain as is, it doesn't matter if you're a hatchery fish or a wild fish. When that fish has access to the food webs and has enough time to take advantage and to acclimate that, what we're doing is making sure that all our eggs don't end up in one basket, that we're broadening that portfolio. Right now, out-migration timings are, I think, far too narrow, and that one of the most important ways to broaden them is to broaden the physical conditions in the valley.
Thanks, Jake. Great talk, really inspiring. I'd have heard of this ancient, wetlands, and you explained it so simply and well. It was the clearest presentation I've seen on it. Is there a co-benefit possibility, or is this what I'm saying could be a totally dumb idea, but around groundwater recharge and flooding, fallowing agriculture, flooding that landscape, and allowing it to be a place where the ecosystem could recover and also recharge the aquifer?
Yeah, a fantastic question, and you're really putting, I think, your finger on one of the great potential, which is multiple benefits, which is realizing that we don't have the luxury any longer to manage a system for a single species or a single constituency, that we can't pit flood protection against ecological function against water delivery. And it just so happens that the floodplain is the nexus for that, because not only can those floodplains be the places where you suggest that when water slows down and spreads out, it also sinks in. But the same time we have this ecological process I was talking about, and we're relieving the flood pressure on the system. So our bypasses exist as pressure release valves to make sure that when the water is coming up within the river system, right down on I Street, right? When you're looking up 17 feet at a cresting river, you want to make sure that the water goes over Fremont Weir and into Yolo bypass so that the majority of water is bypassed around the city of Sacramento. So flood protection, water security, water, floodplain recharge in places where the underlying aquifer and soil types permit it. Ecological function, agricultural sustainability, all of those things come into contact, overlap in a suite of multiple benefits on the floodplain. I was talking about puddles. The other thing, we hear levees all the time. What's a levee? It's a pile of dirt, right? It's a pile of dirt next to a stream, a ditch. Those piles of dirt interact maybe 4 of the primary challenges facing humanity, right? Ecosystem function, like I was just talking about. Flood protection in a time of ever more severe storms under climate change. The capacity to recharge our aquifers, which is probably the most important aspect of drought resiliency, also a major, and really a functioning economy, because it's only if we can figure out and unravel these ecological, it's a mess now, right? But if we can start to see that functioning river systems equal more fish, and more fish equal a more secure water supply, then you're getting at that fundamental economic issue as well. So there's a lot of potential on the floodplain.
All right, well, thank you very much, Jacob. So that was a great segue to the next panel. And just as an interlude, I'll mention that 3 years ago, we hosted a water data challenge. And the winning, this was the White House Council on Environmental Quality one. The winning entry was Flow West, who designed a data optimization pilot project that would take groundwater elevation data, fish in the river system data, and reservoir release and temperature data, and try to figure out when might be the most optimal time to release and flood floodplains. So it was a pretty cool project, and I think they've taken it and turned it into multiple versions of production. So there is hope. I think there's even an AI element to this now. So really exciting stuff, so thanks. Our next panel is going to be moderated by Eric Stein. Eric Stein works at Southern California Coastal Water Research Project. Been a long-time colleague and partner in trying to help solve problems here. So honored to be standing in for Allie Dunn today. Kicking this off to Eric. I do want to sort of put a real quick context on the value of a project like this, and you'll hear the details of it. But This is truly a partnership that has the potential to address many, many California water resource challenges based on the kinds of data and the science and the regulatory and the non-regulatory engagement that's going to be forthcoming. So I'm super excited about this project. It has also sort of formed under the Monitoring Council as a work group, but you'll hear a little bit more about it right now. So do you want to introduce the panelists? Okay, thanks.
Thanks, Greg. And thanks, Jacob. Great setup for this panel. So this is our panel on ecological flows, and I am not Allie Dunn, obviously, but I'm happy to be standing in for her. The way we're going to structure this panel is really building on some of what Jacob talked about, which is some of the opportunity and the project that Greg alluded to, which is work that we've been doing over the last couple of years to try to think about how to optimize some of those flow issues that Jacob was talking about to balance the competing uses of water for ecological purposes and other purposes. So the way we're going to structure this is we have a series of short presentations, about 10 minutes each, that will take up kind of the first half of this time block and give some context on why we're pursuing this environmental flows framework project, what it is, why we're pursuing it, what we hope to get out of it. And then we have about a half hour allotted at the end where we'll have all the speakers up here for some Q&A and some dialogue with the group about pretty much anything you want to talk about relative to this project. So that's the kind of way we'll structure it. So with that, I'm looking for, there's Dan. So Dan Schultz is going to be our first speaker from the State Water Resources Control Board, and he'll go ahead and kick us off.
Dan, am I on the right slide?
No, it was the one with the snowy setting. You just flashed by.
I did?
Yeah.
Correction? It was a bad
It should have been the first one.
I think they're out of order. And?
Yeah. I got a little thing here.
Sorry about that. Rookie.
Good afternoon, and thanks for having me here. My name is Dan Schultz, and I am a program manager for State Water Board Division of Water Rights, and I oversee the cannabis section. And today I'm going to just kind of provide a general overview of the Water Board's authorities and some efforts that we are undertaking and have taken related to protection of public trust resources and in-stream flows. So in general, I'll go ahead and cover some general background of the State Water Board authorities, some definitions, and then we'll go into some of the efforts that we're working on. So in general, as a little background, the State Water Board's mission is to preserve, enhance, and restore the quality of California's water resources and drinking water for the protection of the environment, public health, and all beneficial uses, and to ensure proper water resource allocation and efficient use for the benefit of present and future generations. We have dual authorities. We have both water allocation and also water quality protection authorities to provide a comprehensive protection of California's waters. And basically, these together, we look at beneficial uses, water quality objectives, and anti-degradation, as well as the protection of public trust resources. And we also serve a balancing role between water allocated to the environment and for human consumption and use. So some quick, just general definitions. There's two different definitions, essentially, of beneficial uses of water. We'll go ahead and start with the water rights. And the way I like to think about this is that when you take water out of a stream, these are the beneficial uses you're putting that water towards. These include things like domestic uses, irrigation, as well as municipal fish and wildlife preservation, and along with frost protection and a number of others. And these are established through the California Code of Regulations, the beneficial uses you can use water for. There's also beneficial uses of water associated with more of the water quality control planning or this policy for water quality control development. And these look at more at what are we protecting the water that's in the stream to be used for. So they are established typically through a basin plan setting activities. And these are looking at things usually more towards the in-stream flow uses, but also can include some water extraction uses as well, as you can see in this list. But some more general examples are things like water contact for recreation to make sure that the water's clean enough for people to recreate in and swim in, cold and warm water fish habitat, spawning habitat, ag supply, sport fishing, and those types of uses. So we also have public trust authorities, and the State Water Board is responsible for protecting the public trust, which includes commerce, navigation, recreation, and habitat for fish and wildlife. And in general, the public trust is the uses of water or the uses of our resources for the benefit of the people of the state, versus more for an individual or other type of use. And so whenever we do go through our planning and allocating of water resources, we always need to take these into consideration, and we also have authority to take public trust actions as well. So today, most of our focus is going to be on discussing some of the ecological flow criteria development and establishing what types of flows are needed in the streams for the maximum benefit of aquatic resources. And so I wanted to touch a little bit on the State Water Board's role within that. So there's two different components. There's the flow criteria, which flow criteria does not have a regulatory effect. And it identifies basically the range of flows needed, in-stream flows needed for aquatic dependent species availability. What the State Water Board's role is that we balance the in-stream flow uses with the other beneficial uses, which we discuss mainly on the water rights side, which are what we're using the water for, to develop flow objectives. Or environmental flow objectives. The flow objectives do have a regulatory effect. The purpose is to balance the public trust resources and other beneficial uses. And it's the balanced amount of water that is established to ecologically sustainably meet all needs in the watershed, which include human consumption and use. And those are typically established either through a policy or a regulation, or can also be done through basin plan activities. So now I just wanted to quickly just kind of provide some context for the rest of the presentations in the panel, go over a couple items actions that we've taken in the past that were related to establishing in-stream flows. In 2011, the board adopted the Russian River Frost Protection Regulations. These basically established minimum thresholds to be developed in the Russian River watershed to ensure that frost protection was not stranding or causing mortality of salmonids. Basically, the way that works is when it's a cold day, all the pumps kick on at once, and people that have diversion straight in the stream and some that are closely connected to the stream with wells, we're dewatering the stream and causing fish mortality and fish kills. The second one is the policy for maintaining in-stream flows in Northern California coastal streams. This one was looked at as more of establishing conditions that people need to meet to ensure that water is available for diversion in the in-stream flow policy area. So it's not going back in time, it's more looking for future permits and how we manage allocating more water at this time. In 2017, there was the cannabis cultivation policy, which is principles and guidelines for cannabis cultivation, and this was based off the more recent legislation and the proposition adopted by the state to develop requirements to ensure that the diversion of water and discharge of waste related to cannabis cultivation do not negatively impact in-stream flows. So in this situation, there are very specific diversion rules and in-stream flow requirements associated with cannabis cultivation for the extraction of surface water, and also potentially requirements that would extend the groundwater in certain circumstances. And then the last one on here is the Bay Delta Plan update for the Lower San Joaquin River and Southern Delta. This one went into effect in February of this year, and this established some water quality objectives for the Lower San Joaquin and Southern Delta. And we also, during the drought in 2014 and 2015, we also took some emergency drought actions, and that included an emergency regulation for the curtailment of diversions in Mule Deer and Antelope Creek, tributaries to the Sacramento River. So basically, this established minimum flows that needed to be in stream and also some post flows during the spring into early summer to support migration of spring run up into their holding habitat and eventually spawning habitat, and also extended to sometimes outside of the spring to looking at the in-stream flows needed for steelhead passage as well. In 2015 and 2016, we adopted a regulation for water conservation and additional water use information in in 4 priority tributaries in the Russian River. That was Green Valley, Dutch Bill Creek, Mill Creek, and Mark West Creek. And this one was more targeted at the use. So the main, among other things, we had the statewide conservation regulations for that regulated how people should use their water, like don't water your sidewalks, no washing of cars, all of those. But they only extended really to surface water and to municipal water supplies. In the Russian River, a lot of the issues actually come from groundwater extractions, and so we extended those rules to groundwater extractions as well. And we also developed a requirement that prohibited the irrigation of ornamental turf or grass lawns. And a second part of that was there's a lack of information in these areas because of all the groundwater diversions and not as much information supporting how much they're taking where they are. And so we included informational order authority to collect that information from landowners so that we could have a better idea if we needed to take actions moving forward in those watersheds. So now kind of moving forward to some things we're working on right now. I wanted to touch on 2 directives we got through the California Water Action Plan. The California Water Action Plan in general was developed to meet 3 broad objectives: more reliable water supplies, the restoration of important species and habitat, and a more resilient, sustainably managed water resource system. There was carved out in there was Action 4, which was to protect and restore important ecosystems. And within that, there was a sub-action, which was to enhance flow and stream statewide. And it's targeting 5 stream systems that we're working on right now in collaboration with California Department of Fish and Wildlife. And they are, if I can get them all right, Shasta River, the Mark West Creek tributary to the Russian, Mill Creek tributary to the Sacramento, Ventura River, and the South Fork Eel River. And then more recently, in April of 2019, Governor Newsom signed Executive Order N-10-19, which directs the Natural Resource Agency, Environmental Protection Agency, Food and Agriculture, in consultation with Department of Finance, to prepare a water resilience portfolio that meets the needs of California's communities, economy, and environment through the 21st century. So this is a new activity that we're looking at this point moving forward. And I'm sure you'll hear more about that over the coming years. So going back to some of the stuff that feeds off of what we were just discussing, efforts under development, we're currently working on the Sacramento Delta update to the Bay Delta Plan. As I mentioned, the California Water Action Plan efforts are underway in all 5 tributaries. And then we're also working on cannabis cultivation policy updates. The way that the legislation was passed was that we were developed interim and long-term requirements. We've developed the interim requirements, and we're moving towards long-term, which will be focused primarily on regional in-stream flow requirements for cannabis cultivation. And then we're also working with a number of the panelists that you'll see following me on the development of the California Environmental Flows Framework and Regional Flow Criteria Methodology. And we're doing that through, we're the primary funder of this effort through a contract with UC Davis. So I also quickly wanted to mention one of our ongoing working groups, where a lot of this is, we have a lot of conversations in this group, and it's a new group. It's California Environmental Flows Work Group under the Water Quality Monitoring Council. The mission is to advance the science of ecological flow assessment and its application for supporting management decisions aimed at balancing natural resource needs with consumptive water uses to establish environmental flows. So this group is really looking at developing the science to take the next step forward for the regulatory step of developing the environmental flow objectives. I just wanted to put up here in case people are interested. It meets quarterly in November, February, May, and August on the second Tuesday of each month from 9 to 3:30. And I'm one of the co-chairs along with Robert Holmes with the California Department of Fish and Wildlife, and that's our contact info if you want to follow up with any information. And you can also sign up for the LIRIS list. I don't know how many of you have signed up for them, but they're pretty simple. In the top right corner of all our websites, you'll see a subscribe button. Click on that, go to the Water Board's box or link that will take you to the Water Board's LIRIS list. If you scroll down, you want to enter your information at the top, then you'll scroll down to the General Interest tab, and you'll find under the under Monitoring Council work groups, the California Environmental Flows work group. And then you have to go all the way back up to the top to subscribe. And that's all I have for now. I'm sure we'll hold questions for after, I assume. Thank you.
Yeah, thanks. Yeah, I think we'll hold the questions since we have the half hour for the panel at the end. And as Greg alluded to, and Dan in his final slide, this is definitely a great collaboration between the Water Board and Department of Fish and Wildlife, as well as all the technical partners. So with that, I'd like to introduce Amber Villalobos, and there she is, representing the Department of Fish and Wildlife, who's going to give you the perspective from the other co-lead state agency on this effort.
So does everybody in here really love policy? 10 years ago, I didn't think I would ever love policy, but I actually really enjoy the stuff. So as Eric introduced me, my name is Amber Villalobos. I'm one of the senior environmental scientists at the California Department of Fish and Wildlife. I work for the in-stream flow program, where we evaluate streams and we will develop in-stream flow criteria for fish and wildlife needs. But also in the audience, I kind of want to point out that I have a couple of my colleagues, my team in the back there, if I can get them to stand up, because all the work that I do, these guys are like the backbone of things that I do in the office. So I just kind of wanted to thank them. Oh, wrong way. Whew. So as far as an overview of the presentation, I'm going to cover very briefly some of the state policies and mandates, the Department in-stream flow program, in-stream flow studies, as well as some of the new tools and benefits of those tools that have been developed by members of the panel that we're really grateful for, and and just some of the benefits that we see using those new tools. So most of the policies that actually Dan already mentioned, they also apply to the Department of Fish and Wildlife. We do to also have a public trust responsibility that says that all the public trust resources, fish and wildlife being one of them, are held in trust for the state of California, and that they need to be preserved and protected for current and future generations. Another driver of why we create in-stream flow policy, or I shouldn't say policy, in-stream flow criteria, is the Public Resources Code 10,000, also known as 10,000 through 10,005. That's a code where it was recognized that fish and wildlife are important for the state's economy. And so under that code, the department director was basically told that the department needs to develop in-stream flow criteria for streams that are important for the resources, and then present them to the State Water Board for their consideration in the appropriate water rights process. Another code is Fish and Game Code, is 1602, which is also referred to as the Lake and Stream Bed Alteration Agreements. And for those, if there's going to be a project which is going to divert or obstruct stream flow, a project proponent will notify the department, provide a summary of what they plan to do, and then the department will go in, evaluate it, and provide measures to protect the fish and wildlife resources. Dan mentioned the California Water Action Plan, which we identified 5 streams that were critical habitat for fish and wildlife resources. So I won't get into much of that since Dan already covered it. And then most recently is the Water Resilience Portfolio, which the governor directed the agencies to get more creative with water management and develop more information on how we can protect our communities as well as our resources. And Governor Newsom recognized that we have some species that are on the verge of going extinct, and it's important that we need to do more to protect these species because we don't want them to end up similar to like the photos up here that I have. On the far right is the California grizzly bear, which is now extinct, and he's eating a salmonid. In the middle is the thick-tailed chub, which Jacob Katz provided a good introduction and background. So the thick-tailed chub used to inhabit the areas of the Central Valley, but with all the anthropogenic changes, that fish has now gone extinct. And then just for cuteness factor, there's some western pond turtles on the other side, which are a species of concern. Okay. So as far as the department goes with in-stream flow criteria creation, historically and currently we had two different kinds of studies. Well, I'd say previously we had one type of study which was really labor intensive. It took a lot of resources to develop. We needed a lot of expertise to develop them. We spent a lot of boots on the ground times to develop this information. And it was scientifically defensible. It was highly needed information, but it was just took a really long time to get this information together. Currently, we're developing a new rapid approach using the tools that the group has developed to create a faster way to go through and create ecological flow regimes. And I have a couple slides that go over information, but I'm not going into too much depth because the other presenters are going to present on it. But these are kind of one of the key tools that we're using for the rapid approach, that we could not actually create this rapid approach without these tools. So we're very grateful to have them. So the first one is the Natural Flows database. TNC, along with USGS, collaborated together and evaluated streams throughout California and created this system to provide monthly stream flows for many segments throughout the state. So before, when you're going through and trying to create unimpaired flow or natural flows, it was time intensive, it was practitioner dependent on the information you would get, and a lot of times you couldn't really get people to agree. So this is one tool that's providing consistent base information for us to know what kind of water flow would we expect in that stream given an average year, a dry year, a wet year. What might we anticipate without any diversions or human changes to the landscape? Another tool is the functional flows documentation and calculator that provides some key information about timing, magnitude, and duration of flows that we'd want to occur in a natural system. In the past, components of this were implemented in odd ways, but with this new information, it's presented in a consistent manner, and it's actually a tool that can be applied throughout the state. So what this means for the rapid approach is we have consistent base information, we have some consistent tools. This means that the department can develop this much needed information in a much faster way. We need fewer resources. We could create criteria with or without site access potentially, which is a great time saver and cost saver for the department and for the state. We can create criteria on a broad scale or a fine scale. The picture up on the screen, it is shape of a watershed, and you can see that on this particular example, we've created potential criteria for 42 different portions of the stream, and it could have been more extensive, it could have been less extensive, but it was just an example that we wanted to provide. And this information could be developed instead of on years, it could be developed in weeks. So again, we're very happy to be part of this collaborative group, and we're very thankful for the members of the panel moving forward, creating this information, and if you have any questions about the department's in-stream flow studies, either our past ones or our new approach under development, my contact information is up there, as well as our in-stream flow program website. So you can reach out to me, you can take a look on the website, and we have a designated person to contact. But we look forward to any comments or answering any questions that you might have. All right, thanks.
Super. Okay, great. And so that I think hopefully now you have with the Dan and Amber's talk a good background on kind of some of the policy drivers. And so our next three talks are going to focus on some of the technical tools that have been alluded to by the first two speakers and get into more detail and some of the tools and data that are driving the formation of the tools that Amber alluded to. So I'd like to introduce Sarah Yarnell, who will be our next speaker from UC Davis. She's going to give you an overview of the California Environmental Flows Framework.
Thanks. Happy to be here. So you've heard a little bit about the collaboration that's been going on, the Technical Flows Working Group under the Water Quality Monitoring Council that Dan talked about. And in general, this group is working towards developing the California Environmental Flows Framework. And I'm going to give a brief overview about that, and then the next couple speakers are going to talk a little bit more in detail about some of the tools you've heard to that Amber has alluded to and Dan has alluded to. Hold on a second here. Okay. So just to give a super broad overview, we know how impaired the water is across the state of California. There's been a lot of, recent studies that have sort of quantified this, but in general, most everybody who's here and anybody who works in water recognizes the fact that the impacts on our streams and rivers throughout the state are pretty substantial. In general, the types of patterns that we see are depleted flows in wintertime. Peak flows do not necessarily pass down the rivers and streams anymore. They're often kept back in dams, held back for water supply or flood control. So we see a depletion of winter flows. And then as flow deliveries happen in the summer, we see an augmentation of summer flows. And so what this does then is essentially decrease the amount of variability that we have in a lot of our rivers throughout the state, in different portions of the state and throughout the year. And this decrease in variability goes directly against what a lot of the natural flow regimes that our native species have evolved to. So a lot of what Jacob alluded to in the beginning was this idea of if we're trying to put functionality back into our river systems and create multiple benefits, how best can we go about doing that? And one of the premises behind the approach that we're taking is this idea of restoring seasonality to a lot of our flow regimes in the best that we can. Additionally, as you've heard from both Amber and Dan, from a policy perspective, California is a huge, diverse state. We have incredibly different watershed systems from the very north of the state down to dry ephemeral streams in the southern part of the state. And we have a huge diversity of water uses throughout the state, both in terms of human consumptive use, in terms of economy, agriculture. And so the management needs vary quite a lot across the entire state. In addition, we have multiple agencies, not just the two state agencies that you heard from today. There are federal agencies with water responsibility, U.S. Forest Service, BLM. They participate in the relicensing of hydropower dams. We have local water groups, local water districts. And so there's a complexity in terms of uses and people who are using water throughout the state. And there's really a lack of coordination among a lot of these different agencies. There's not necessarily good sharing of data a lot of the times between these different agencies, and multiple groups can be working on individual watersheds. And this really creates inefficiencies and a lot of redundancy in the way that we approach how we deal with trying to determine and balance water uses within watersheds. So there was really a need within the state to get some of these groups to start talking to each other and come up with a more coordinated framework for how we should go about approaching water management within the state in a way to try to attempt to balance these multiple objectives, bring the science together to understand ecological flow criteria, and try to make some progress moving forward with that. So this technical working group that Dan has alluded to has sort of essentially started the development of the California Environmental Flows Framework. We call this CEF for short, because you need an acronym for everything, of course. And essentially what CEF is the idea that within that framework, we're going to focus first on the science and the best available science. In particular, we're going to focus on the ecology of the systems and the natural hydrology or altered hydrology of the systems to better understand what the ecological needs are within that system and set ecological flow criteria based on the initial needs of the system first. And this is where the science really comes into play. And so most of the folks that you'll be hearing from the next couple talks, like myself included, are the science experts that are trying to help then inform the policy. Once we come up with these ecological flow criteria, then we sort of pass off to our policy and agency partners, where then there becomes some guidance or discussion about how best to go about balancing these different multiple objectives. Things like water availability, water demand, how do we go about really figuring out what flows are needed and what flows can be retained within a system for the ecological functioning in addition to providing water supply. And the reason these decisions are outside of the box is that these are really social and policy decisions that we as a community need to develop. Science can help inform those decisions, but at the end of the day, it's a regulatory, policy-based decision on how we're going to manage our streams. And so we explicitly recognize that in the framework by providing a science-based, informed set of decision-making tools and data at the front end, and some guidance for considerations that stakeholder groups, agencies, nonprofits, local water users together can consider and talk about as they make their final ecological flow recommendations. Okay, so here's a little bit more detailed view of what SWRCB is. In essence, it's a two-tiered approach with the science. And again, the science is sort of the box on your left, and then the policy boxes are on the right. So we have a two-tiered approach. The first approach, the first tier, you're going to hear a little bit more about, but essentially it's a statewide functional flows-based approach to establishing flow criteria for every stream in the state. It's a single methodology that's based on reference flow conditions, building off of the natural flows database and our understanding of what natural ecological systems in California would need. This methodology and set of tools provides you with a starting point for what your ecological flow criteria could be. In many cases, this may be adequate for a particular watershed or a particular water user group, or it might need further refinement. For example, if it's a heavily managed system and there's not enough water to provide those full ecological flow criteria, you then might move down into a more detailed local or regional scale, a tier 2 framework, where you bring more data to bear. You might do more modeling to really balance those needs or better understand the flow limitations within your watershed to help you refine those flow criteria to come up with a final set of ecological flow criteria that then can go on to the social decision of how to manage and allocate for those flows, which is outside the box. And as I've said, all of this is inherently based on the functional flows approach. So Jacob alluded to this beautifully this morning with the early afternoon with the first talk. And the idea of a functional flow is we want to focus on those key components of the hydrograph that give us the most ecological bang for our buck. So California is a highly seasonal location. We get our rain in the winter and we don't get rain in the summer. We have a bigger drought every single summer than the East Coast has ever seen. We don't get rain for 3 to 6 months. Our native species are totally evolved to this. And so when we change the hydrologic system to lose this seasonal variability, you're essentially taking away the advantage from our native species and providing an advantage, like making it more advantageous for the non-native species to come and invade the system. So the first thing we want to do is to try to pull back from that and acknowledge the fact that we want to reintroduce seasonality into these flow regimes. And in particular, we might focus on 4 key components here in California that are broadly applicable across the whole state. The first one is those peak winter floods. Exactly like what Jacob talked about, you need high flows to go through and scour sediment, redistribute sediment, reconnect to the floodplain, flood out into the overview areas, give that floodplain habitat out there, and really do the work, the ecological work of the ecosystem. When at all possible, we want to retain at least 1 or 2 of those flows within the system every year. The second key component is the spring snowmelt recession. So all streams, even down in Southern California where Eric lives, and they're very flashy, there is a transition from the wet season to the dry season. And this transition does not happen overnight. You don't just magically shut off a valve and say, it's not raining anymore, all the water is gone from the streams. That's not what happens in nature. There's a gradual draining that happens through all the watersheds, that happens during springtime. And this is a very, very predictable time of year that all of our native species are cued into. If you take those cues away, the fish then may or may not have an out-migration flow. They may or may not have spawning timing or cues that are given to them. And so we really want to be able to keep this flow transition, gradual flow transition, happening within the system where possible. The summer base flows, of course, California streams do go to low flow at summer, and artificially keeping rivers high is creating habitat for non-native species. It is okay to let the rivers go to lower flow in summer. Some of my fishy friends don't like it when I say that, but that's what the system was evolved to. We should have decreased flows in the summer in California relative to higher flows in the winter. And then the last bit is the fall seasonal pulse. This is the cue to begin and re-wet that season again for the species. So salmon are cued to look for this fall pulse to migrate upstream. And again, if you remove this cue from the system, you're sort of limiting the ability of these native species to function in their life history stages as they've evolved. And so the tier 1 steps of SEF then essentially allow for this type of functional flows approach to be put into place. So Belle's going to talk a little bit about the stream classification, but based on where you are in the state, collectively the larger group has put together a stream classification to talk about what type of stream you're in. Am I in a snowmelt dominated stream or a rainfall dominated stream or some type of mixed stream? Based on that, you can explore reference hydrology for your stream. We have a set of gauges across the state, roughly 223 reference gauges that can be used to look at natural reference flow conditions for different parts of the state. With this information, you can evaluate the local reference hydrology for your stream class and get a sense of what those natural patterns and timings and relative magnitudes might be for your system. You can then go through and evaluate some actual functional flow metrics. So the bottom line when you're developing ecological flow criteria is I might say to somebody, hey, you need to put down a flood flow. But what they're gonna ask me is how much and when and how long. So we have to be able to put numbers, discrete quantifiable numbers on these flow recommendations or metrics, flow metrics. What is the magnitude? When should this flow be released? And how often or how long should this flow be released for? So there's a way to quantify and calculate those functional flow metrics on this reference hydrology that provides actual numeric bounds for the targets you should be shooting toward. You can also then look at your local stream gauge. This is predictive flow modeling that's being completed up right now as we're sort of talking. Hopefully later this summer, this data will be appended to the natural flows database that TNC has. And again, this will be predicted functional flow metrics for every stream reach in the state. What are the bounds of those actual numbers for those functional flows that you might want to start looking at for your flow criteria? And then finally, then you can assess your actual local hydrology with what those functional flow metrics or flow criteria are to determine where you might be doing well in your system or where you might need to consider alterations or changes to the watershed management in that system in order to achieve those criteria. We'll talk a little bit about this, I think, in one of the next talks, but there's the functional flows calculator is at eflows.ucdavis.edu. This is where you can go in, look at the reference hydrology across the state, and actually pull out those reference functional flow metrics to give you a sense of what your ecological flow criteria might be. And then you've seen this, Amber alluded to it as well, but this is the natural flows database from TNC at rivers.codefornature.org. And this again provides monthly predicted modeled flows for every stream reach in the state, and we will be augmenting this website with those additional functional flow metrics for every stream reach in the state, modeled functional flow metrics for every stream reach in the state later this summer. So then if at some point you feel that you've got these ecological flow criteria for your stream reach, they are somehow not potentially doable, not potentially specific enough for the species of interest you might be looking at, you may then choose to go into a tier 2 guidance framework and refine those ecological flow criteria for more specific needs within your system. And in this case now, we're not prescribing a method per se, but simply providing guidance on the types of considerations that stakeholders, agencies, and groups that come together with this should be considering. In particular, you might be looking at your specific species of interest and management objectives within a particular watershed that you might want to take into account, like I really do care about salmon and it's really all about salmon, and so I want to manage for salmon, and you acknowledge that, and that might be a focus for where you might refine your criteria. You'll be characterizing, potentially, you would want to characterize more of your local data. Perhaps you have more detailed flow data than what is provided on the websites, and that gives you a more accurate picture for your location. You would want to bring that information to bear. You might be looking at a more detailed environmental flow method. Maybe you'd like to look really specifically more at those summer base flows and determine, okay, what's the absolute minimum flow I can get by with where I'm retaining connectivity in the system? And you might go out and do a little bit of field work to augment and collect additional data to refine that summer flow criteria, for example. And you may look at flow ecology relationships more traditionally like an Aloha approach or something like that, where again, you're trying to limit alterations to the system that might affect the ecology in general. And so all of these considerations then are inherent within the tier 2 section of the framework, and essentially provide a place for stakeholders to come together, talk about the same data in the same place, in the same manner, so that they can hopefully come to collective conclusions about how to manage their watershed. Oh, and here's just a little bit more detail about the steps and the data considerations you might go through for that tier 2. The working group is going to continue to be meeting. As Dan mentioned, we meet quarterly. talk about this stuff. There's a lot of different case studies actually that are going on throughout the state, which is great to hear about where things are working, not working, considerations people might have. And so at least myself personally have been really appreciating the value of having a lot of different policy and stakeholders come and talk about this type of work. And the overall goal of this is to come up with essentially a framework and guidance documents and data and tools for everyone in the state to sort of be able to hopefully make progress towards a more managed and balanced system in terms of their local watersheds. This information's for the larger framework is currently being housed at cef.ucdavis.edu. You can go there. You can contact me directly or pretty much anybody else that's going to be talking today, since we're all working so closely together on this. And at that point, I'll stop and take any additional questions. That's quick. Oh, questions at the end, that's right.
Thanks, Sarah. Okay, so our last two speakers, next speaker is Julie Zimmerman from the Nature Conservancy. So you've heard a little bit about the natural flows database. So Julie's going to tell us more about that. And then we'll finish up with Blaise Lane telling us about all the cool tools you heard about. And then you'll have time to pepper all of the speakers with all your questions.
Thank you. So I've had a nice setup on the natural flows database. We've heard about it in a couple talks already. So back several years ago, the Nature Conservancy, Jeanette Howard and Kurt Klossmeyer and me had been talking with USGS, Darren Carlisle, Larry Brown, Jason May, and Ted Grantham at Berkeley about setting environmental flow recommendations and realizing that one thing we were really lacking is a hydrologic foundation for the state. In most places, we didn't know what natural flows would have been. And if you don't know what natural flows are, there's no way to know what expected patterns of alteration might be or what ecological flows might be. And we've done some other work that's related where we've looked at the stream gauge network and found that 86% of streams in California are poorly gauged. So you really can't rely on just gauge locations if you want to have a good sense of hydrology. So we embarked on a big modeling project to try to predict unimpaired or natural flows for all streams and rivers in the state, gauged and ungauged. And the first step to this was to identify reference gauges. So we ended up identifying 250 reference gauges statewide in a 3-step process, or step 1, 1, and 1, as it shows here. So the first one is we did an initial screen by looking at places where there was low hydrologic disturbance and low disturbance to land use and had at least 20 years of data. And that was published in 2010 and came up with 146 gauges. Our second step in the analysis was to look at places that passed the first hydrologic and land use screen but had less than 20 years of record, and that yielded an additional 45 gauges. And then our third step was to look at gauges that may not be referenced for their whole period of record. So there might be places where you have gauge data for 10 years that was referenced and then a dam went in or something, and then you have a change after that. And so we ended up taking partial periods of record for gauges that were considered reference for part of the time and got another 59 gauges. And then once we had all of these reference gauges, we decided to use a machine learning approach to see if we could predict their flows using data that we could collect for all of these sites. So we ended up collecting climate data that included precipitation and temperature and runoff, and then a lot of GIS-derived variables from the Gauges 2 database from USGS, so that included things like topography and soils and geology, and put it all in a database. That was the first step. And then the second step was to try to predict monthly mean flows, minimum flows, and maximum flows for all those gauge locations. So we trained the model on the reference gauge sites and then also tested it and developed a model that we felt worked pretty well. And then we used that model to predict unimpaired flows at gauge locations as well as ungauged sites. And at those gauge locations, you have observed data and then the predicted natural flows, and you can do some comparisons. So to do this, we have a paper that I can share with you that goes into the detail, but we broke up the state into 3 regions: xeric, interior mountains, and coastal mountains. We calculated 3 monthly statistics: mean flows, maximum flows, and minimum flows for the period 1950 to 2015. We had 113 static physical watershed characteristics. These were all derived through GIS, and then 39 climate metrics. And it ended up with a whole lot of models. And we we used a random forest approach to calculate the mean as well as the 10th and 90th percentile for each of these metrics for each month. So we have a 80% prediction interval around each of these values. So, good, you can see it better than I can. It's just like a white screen right here. So when you go to the Natural Flows database, this is what you'll see. You can go here online, you can read a little bit about the science, you can download data directly using the API, or you can use the map tool where you can do some visualizations and click on individual stream reaches. And this is what it looks like if you go to the map tool. So we predicted flows everywhere on the NHD Plus National Hydrography dataset. There's 2 colors to the stream reaches. There's blue streams, which are places where we don't have gauge data, so those just give you predictions of natural flows. And then the purple stream reaches are places where we have predictions of natural flows, but we also have stream gauge data. So if you click on a blue one, you'll get something that looks like this, which shows it's a visualization that shows the mean monthly flows for dry years across all years. Well, actually, it's now for the average year, and then wet years. And that's for the entire period of record, 1950 to 2015. And then on one of the purple segments, it'll also give you a line that shows what the observed values are for that same time period. You can also, on the bar on the right there, you can select stream reaches, multiple ones, you can select months, you can select certain year values, and you can download all the data directly and do your own visualizations. Or we also have a couple Tableau sites where you can go in for gauge locations and look at this for different well, you can play with the sliders and look at different years to get into more detail. So this just shows one of those Tableau sites for the mean monthly flows, and this is the Sacramento River at Keswick gauge. So this is downstream of Shasta, if you don't know it. And it shows the time period from October 2010 through August 2015. So the first part of that, I don't know if I can show the pointer here. Yes, okay. So this first year right here was a wet year, and the blue line, the dark blue line, shows observed flows. The dark gray shows the mean monthly flow for each of those months. This x-axis shows the month and the year, and then this is the flow. So that dark gray line is the predicted natural flow. These lighter gray lines are the 80% prediction interval around that. And then in blue is what's observed. So that first year was wet, and you can see the observed flows followed those natural patterns pretty well, even though they were higher than expected in the summer. But then when you flip to the drought from 2011 to 2015, we get a flipped hydrograph. So you have the high flows of the year occurring in July and the low flows of the year occurring in March, which is opposite from what that natural pattern would be. So these are the types of things you can start to notice when you pull out the individual data. And we looked at this and we thought, well, could we do an analysis where we looked at patterns of alteration statewide? And we published this last year. I'm going to show a few sets of these maps here. This first one shows alteration to mean monthly flows across the state. So here, the orange dots are flows that are depleted, which are lower than you would expect under natural conditions. The blue dots are inflated flows, which are higher than you would expect, and then the gray are not altered. And then the size of the dot is the magnitude of the alteration. So what the general thing that we found is that 95% of streams statewide have some alteration, that it's altered at some time, some point of the year over that period of record. but most places don't have only depletion or only inflation. Most of them are inflated sometimes and depleted at other times. So these are the same maps here, but this top set are the 1-day maximum flow for the year, and then the bottom set is the 1-day minimum flow for the year. So what we did is we took the highest maximum across the years, or the lowest minimum, so that we could get the 1 day. And we found that maximum flows are most often depleted, whereas minimum flows are most often inflated statewide. So what that says is that we've done a really good job of moving water around just like the water infrastructure was supposed to do. We've taken it from the wet times of the year and moved it to the dry times of the year, and from the wet parts of the state and moved it to the dry parts of the state. So for our next steps for the natural flows database, we want to improve somewhat on our visualizations and try to put some more detail in there. We have some of our staff at TNC in-house working on that right now. We also have been working with AT&T and then some of our own staff to incorporate some new code to update the database over time. So right now it ends at 2015, but we're writing code so that it can pull the climate data every time it's available per month and just update the database so that it won't end there, but it'll go on in perpetuity. And then the final thing that we're working on is the functional flow metric prediction. So we're using a modified version of this approach to model the functional flow metrics at that same resolution. So for the same stream reaches that you'll see on the web tool, and we're adding that to the database, and that will probably be sometime this fall, summer or fall. Okay, that's all. Thanks, Eric.
Okay, great. And so all of these tools and data will be available through the various websites that the various speakers have alluded to. So our final speaker, before we get to the panel discussion, is Belize Lane from Utah State, and she's going to share some of the other cool tools.
Well, I realized we don't have a slide on. Okay. This slide has tried to pop up several times, so I know you've all been desperately waiting to hear more about it. So we've been talking about flow and hydrology, and fundamentally, this is a water conference after all, so I promise to stay on topic. But I want to come back to what Jacob was saying earlier a little bit and talk about the landscape. So here, if we take water and we pour more water into this channel, we're going to see it start to spill out onto the floodplain. You can already see that kind of happening now, or up onto these bars. If this channel were much more confined and steeper, if you had the same discharge running through it, different things would probably be happening, right? It'd be moving its way downstream, maybe mobilizing sediment more rapidly, not necessarily spreading out. So we just want to acknowledge that the geomorphic setting is also really relevant. And like CDFW and Amber was talking about, we have some really resource-intensive, really valuable tools for trying to understand the geomorphic setting of the landscape and how that's going to affect the hydraulic conditions, but we're trying to develop, in line with these flow methods, some more regionally applicable rapid methods for understanding what's going on with our rivers. So we've developed this geomorphic classification, or we are in the process at the statewide scale, and the idea here is just like with the functional flows calculator and the natural flows database, where you can go into any stream reach in the state and say, what does my natural flow regime look like? And understand the months, what we think the natural monthly flow pattern is, or the timing of the spring snowmelt recession. Similarly, we are developing a classification to be able to understand the physical, or to our best ability, the physical habitat setting that the water is moving through at any location throughout the state. So this classification essentially classifies physical habitat. So we're talking about the sediment composition, the width, the depth, how that varies longitudinally downstream, and how it varies laterally up into the banks. And we'll talk a little bit more about that in a standardized, rapid, scientifically defensible approach that accounts for the inherent uncertainty in trying to get this at the reach scale.
So the hope is that this will enable access to geomorphic information for thousands of miles of streams across the state. Just out of curiosity, how many of you are familiar with SWAMP's PHAB data set? Yeah, so the idea is to sort of build on that and expand on the geomorphic data that we're collecting to make sure that it's ecologically and geomorphically relevant at the state scale, and then distribute that information across the stream network. So why is this important? Well, we want to be able to refine our ecological outcomes. I think Jacob did a great job of talking about when you're in these floodplain systems, there's going to be particular species or life stages that are important. We care about our salmon. We care about making food on the floodplains. Maybe you wouldn't care about those as much if you were in a different geomorphic setting where that's not really as relevant. So we can start to prioritize our ecological outcomes, which is an important part of Tier 2 of SEF. Also, the environmental flows methods. There may be certain methods that are much more or less relevant depending on what geomorphic setting you're in. So some of these entirely flow-based methods like Aloha may not be appropriate when you're in a really unique or highly variable geomorphic setting where it might make more sense to use a higher resolution hydraulic modeling approach, for instance, or temperature information or something like that. So this is just showing the functional flows framework, right? The idea is there are these hypotheses about these components of the flow regime that are affecting your ecological outcomes, but we're just saying that those hypotheses may be modulated by what channel setting you're in. Also, we can use this information to constrain the flow criteria by channel type. So again, you release this flow, it's going to do really different things, whether these high winter floods are going to do very different things when you're in this wide, shallow, meandering system versus this deeply entrenched channel. So it may be, we're talking about these functional flow boxes, these components, which is the natural ranges of those functional flow metrics. It might be that a smaller subset of that full natural range for that stream type is actually going to be achieving the function that you're interested in. So taking the time to think about what are the functions and should we make those boxes smaller than the full possible range to account for what it is we're trying to achieve. Also, this is going to be helpful for upscaling site-specific information. We can't go and survey all of this sediment, slope, all this information at every streamage in the state yet. And so in the meantime, we're trying to use this information to generate synthetic terrains using this modeling tool that we're developing called River Builder. And you can see a cool example here. We're basically generating synthetic terrain and playing around with different flow scenarios in these different channel configurations and playing with slope and sediment composition and all of these features to think about how that's going to affect aquatic species habitat needs across the state. So how does this work? Well, it's pretty simple. It's kind of like the hydrologic classification that we didn't have time to talk about. So similar idea. You go into the field and you survey a bunch of stuff. You get things related to your channel cross-section, your slope, sediment composition, all this. We throw it all in these statistical analyses to pull out sets of sites that we expect to have similar channel characteristics. And then we're using state-of-the-art machine learning techniques to extend that information about those different channel types that we've identified in a region to the rest of the landscape at the NHD segment scale. I think eventually at the 200-meter scale. And that's using publicly available geospatial data related to, well, basically everything we could find for the state of California that could possibly affect your reach scale geomorphic setting. So in order to balance capturing the full range of regional geomorphic variability with detailed information within a reach that you would expect to influence your aquatic species and your ecological outcomes, we did a tiered approach to selecting sites. So first we looked across the state and we split up the landscape, these stream reaches, based on valley confinement, sediment supply, contributing area, and slope, all of which were extracted from geospatial databases, mostly topography. And then we binned the landscape and tried to survey across different combinations of all of those in the hopes of capturing a range of the reach scale channel settings we were seeing. And then we went into these settings and again calculated a whole bunch of stuff, mostly just using pretty low-tech equipment, just measuring tape and surveying level and a bunch of undergrads, and collected a bunch of data that essentially is what is in the PHAB database, and then some additional information to start to get at the sub-reach scale variability and look at how depth and width and channel width vary longitudinally and co-vary to better capture the hydraulic patterns and habitat that we expect to see. So then what does a suitable classification look like? We have all of these sites that we've gone in and surveyed. The next step is basically to go through and interpret the statistics, use them as a tool, but also go through mindfully with a bunch of geomorphologists and try to understand, well, what are we really distinguishing here? Unconfined from confined valley settings, high topographic or low topographic variability, high slope, sediment composition, and eventually you have to draw some line. This is an example of one type of clustering approach, but this was based on a whole bunch of different tools. You draw some line and you say, okay, these are similar, they're all in one channel type. These are different in order to have a minimum number of channel types, but still be really capturing these important features. So we've spent a lot of time on that. And as of now, with the combination of swamp data and all of our survey data, we have over 600 sites that have been surveyed across 6 regions in California, which you can see here. We started with the Sacramento and the South Park Eel, which is that really black area in here. And now we'll have 8 regions in total, all of the areas that are lit up here. And so 2 of them are completed, and then 6 hopefully will be completed by 2020. But right now it's a work in progress. There's a lot of people out in the field probably as we speak. So it's been a big data collection campaign and getting all of the protocols very scientifically defensible and the ability to train different regions that are working with us. Right now we have groups from Humboldt State, Southern California Coastal Water Resources, Monterey State, UC Davis, all of these folks who are working with us to help go out and collect the data. So it's a lot of really smart scientists involved in this process. And just an example, so this is the classification of the Sacramento River Basin. You can't really see much of this, but there's, I think it's 10 channel types. So they're, again, distinguished across those attributes that I mentioned, boulder bedrock. So you end up seeing there's these really unconfined streams down in the valley, and then you get into more of these confined settings, and the sediment composition kind of varies. And this was all predicted at that really fine scale. This is an example for the South Fork eel. Almost all of the channel types here are much more confined, coarser sediment. You have that really high relief coast range topography, high sediment load. And finally, I just want to talk about, so this has been a huge effort, and we've put a lot of work in, but there's really, even though 600 sites sounds like a lot, there's a lot more work to be done. There's still a lot of uncertainty in the prediction of your channel setting at locations that have not been surveyed. So we're really interested in getting support from other folks in California to help increase the coverage of these sites and reduce uncertainty in our classification. And it's really fun, you get to go do that. So a couple options that I want to throw out there. One is ground truthing the classification. So going out to some site, any site now will have a prediction of what channel type you're in. Going out to that site and just looking at we'll have a database showing, if you're in channel 1, it should look something like this. If you're in this other channel type, it should look more like this. And just saying, does this make sense? Do you feel like you agree with the predicted channel type? We're also developing some heuristic tools. So this basically walks you through and you say, what is the valley setting? Am I confined or unconfined? And then you walk through this tree and it says, okay, if I'm confined, well, what's my sediment composition? And eventually you would assign a site to a certain class. And we can go back and use that to ground truth our prediction. Similarly, we've developed an app that is available, or we can make available, called the California Geomorphic Classification Field Survey app. And this is all of the information that our crews are actually going out in the field and collecting. So you can bring an iPad or whatever and walk through each of the steps. We have very detailed protocols and really go in and collect data for an entire site. And this can either be broad site selection, where you just are somewhere collecting bugs and you say, we're going to go do the geomorphic survey as well, or targeted site selection if you're in a region and you think the current classification doesn't sufficiently capture some channel type and you want to make sure it's accounted for, or some other reason. So there's a lot of opportunities there to help improve the classification effort. And yeah, I'll stop there for now. Thank you.
Great, thanks. And then I'm going to invite all of our panelists back up, but just to follow up on what Belle was saying on that last part. We're really excited about this idea of the citizen science and something like maybe like an iNaturalist type of app where people can verify the classifications, and so really engage all the watershed groups around the state that can help us build on some of these tools over time. So with that, I think I have about 15 or 20 minutes left, or about. Yep. So what I'd like to do is invite all of our speakers back up, and then we have time for sort of an open discussion. What we try to do is provide kind of a broad overview of the policy drivers, what the environmental flows framework is, and then some of the specific tools that are being developed to support development of these ecological flow criteria around the state. And so now we have some time for some general question and answer. Yeah. Are those mics all on? 50. Okay. All right, so we'll open it up. I have some prompts, but I'm guessing there's lots of questions out there, so we'll start with the audience.
Thank you. Thanks for all the talks. I had a few questions kind of related to how you're looking to manage this, where we're going with policy and management. And the first thing that the only thing I can think of, I guess, in terms of managing flow is pulses from dams, better water management. So when you look at, let's say, a river system like the Carmel River, where you've had so much drawdown of the aquifer, and you're combining that with this seasonality, this lack of seasonality, how do you manage that, restoring the groundwater while also trying to get that, balance those flows again? And then on top of that, I'm just kind of curious if you've thought about, the other technological tools for managing, like mini hydro or things like that, you can kind of get into the system. So.
Dan, you want to answer the policy?
Okay, I'll do the science. Dan's going to do the policy. Okay, perfect. Okay, so from a more scientific perspective, okay, I don't have to hold it down. Sorry, he told me to push the button. Just once. Okay, so the way that I would look at the functional flows approach is it can be bottom down or bottom up or top down. So if I'm in a dam, I might be adding and building up flows to get to my functional flows. If I'm in a diversion setting, which is what you're describing in the Carmel, then I'm limiting diversions. And I'm coming from a top down to say, yes, you can take here, but no, you can't take here during this time. And the connection with the groundwater is huge, of course, as we know. That's one of the aspects that several of us we've been talking about. How does this mesh with Sigma and the new relations there? But again, the idea is that the flow criteria sort of provide bounds, which you ideally do not want to go above, and ideally you do not want to go below. So the application of it then makes it very simple in a lot of different places, right? And it can be used in a lot of different ways. And a lot of the rivers might have 3 of the 4 that are naturally happening, and maybe you're really concerned about one. Or if I'm in a fully regulated system like below Shasta, then you're really trying to manage across the whole flow regime. So that's the science side.
Sorry, I just wanted to add something to the science side. I think the other piece of this is the 2 tiers. So tier 1 with the functional flow metrics based on unregulated flow is meant to apply everywhere and be broadly ecologically protective. But there's going to be places where you either don't want to meet it, or you can't meet it, or you want to refine it, or whatever. And then that would bump you into a tier 2 process where you would come up with another methodology, which we're going to provide guidance on how to do that, to come up with a different set of functional flow metrics, or the different values around that. And the important part, though, about going into a tier 2 process is that you have to have management objectives. So there has to be a reason, not just like, I don't feel like meeting these, but like, what am I trying to achieve in this place? And select your methodology based on those objectives.
And then from a policy standpoint, you picked a tough one, groundwater and surface water impacts. A lot of times when we start to look at that from policy, we're going to start looking at a more robust analysis of surface water, groundwater interaction through modeling and those type components to get at how the two are interplaying and where different impacts are occurring during different times of year to help mitigate some of those impacts. From a coordination effort, you could look at it a couple different ways depending on how you want to approach the situation. You could look at these are the minimum flow targets we're looking to achieve in stream. And if they're not being achieved because of groundwater extractions, then that would go kind of more over into the Sustainable Groundwater Management Act as targets that they're trying to hit as far as balancing the losing reaches. If it's more the other way, then really it's looking at how do we make sure that we're providing those high flows during the winter to restore the groundwater table. If it's more of a short-term impact versus a long-term impact. So it depends exactly what the situation is. In some of our efforts that we're undertaking for the California Water Action Plan, we are looking at more of that more detailed modeling effort of the surface water and groundwater modeling to try to get at some of those impacts.
That was a wonderful presentation all the way around. I think the Belize, Sarah, Julie, the level of progress and the science that's driving that as far as understanding how things worked, how the landscape functioned, is absolutely the basis for moving forward, for making informed policy decisions. And I think it's wonderful to see what the last 5 years have brought. There's this place that we've touched on, which is, I think you did a good job, Baylis, in talking about the geomorphic context being absolutely necessary in talking about flow. The impact of that flow is going to be very, very different depending on not just the channel classification and not just what it was once on the landscape, but what it is. And that gap between what we think it functioned as to how it functions now, this idea of tier 2 that you were just putting in, Julie, seems absolutely critical. Maybe a larger context for that is this word flow. So often I still hear flow and you could substitute volume of water. Increasingly, you could hear volume of water at a certain space at a certain time. That's helpful, but we all talked about pattern and how that pattern might actually be more important than the volume itself, and trying to broaden that out, trying to really get at that translation between the volume of water being put in the stream, but what the impacts are and how that is really at the very core of all three of the models that you guys are putting forward. So it's not so much a question, although I do have a couple, like how, Baylis, does your model deal with the fact that with the built environment, so with a Central Valley, a Sacramento that looks nothing like the unconfined geomorphic channels that it once was, or there's more subtle ways. You can look about the Yuba, right? So the Yuba is still an alteration, but it's an alteration that happened at a landscape level over, well over a century ago, over decades, that fundamentally has changed the way the water flows, those patterns, what's possible. So the reason I'm bringing that stuff up is because that's where the challenge is. That's where the people are. That's where the water demands are. And if we don't make that stuff transparent now, I fear that we could end up at loggerheads again, where we have environmentalists saying we need this kind of flow here, and you're saying people on the other side that are using that water saying that's insane, and then not being able to bridge it. So it seems like we have the context to bridge that, but maybe I know it was too much talk, but maybe you guys could just pick a piece of that makes sense, because I know you're all thinking about that idea of what flow actually is.
So maybe I can translate that into a couple of questions for the panel and see if I capture that, Jacob. It seems like one of the questions is sort of how to set expectations given sort of the sort of systemic changes on the landscape and unpredictable future changes. So how do you set reasonable expectations? Seemed like one of the questions you're asking. And then the related question is then how do you balance that? Balance those expectations with some of the other demands on these highly constrained landscapes. So maybe that's a couple of questions that were embedded in there.
I guess maybe I should start by just putting a few caveats on my recent presentation, which is that we're trying to classify the current setting of relatively, in huge air quotes, relatively unaltered channels. So we have not yet gotten into the super highly altered Central Valley systems. And we're trying to say at a regional scale, for instance, if you're looking, and this is another example of a method that may be more or less useful depending on what region or what setting you're in. So in the South Fork Yale watershed, there's definitely been channel alteration, but fundamentally we can try to understand, are you in a pool riffle system or a cascade or this wide kind of meandering system that has some floodplain pockets? Whereas we're not yet at the point of being able to understand what the current geomorphic setting is in some of those more lowland, heavily altered systems. Go ahead, Dan.
Yeah, and I would add, so that's kind of the next step in the process is right now we've identified kind of what the expected geomorphic setting would be under more natural conditions. The second step is to evaluate what if the current geomorphic setting is functioning that way, or if it's gone through alteration. In that case, can it be, if we add flow back into the equation, what was the driver of that alteration? Can it be restored back towards its natural function geomorphic setting? Or have we now pushed it so far that we have to manage that as a different channel type altogether? So we're looking at different options to try to get at some of that. We're looking at whether or not we can use some of the LiDAR. There's supposed to be a better survey of LiDAR coming out soon. A lot of the more impactful areas that we find where we have more significant geomorphic change from human causes is in the lower land areas, where hopefully we can get better information from either aerial photos or efforts through aerial photography, satellite imagery, or through LiDAR to start to develop what the current setting of that geomorphic channel is so that we can get at that change. The second component is whether or not, as I mentioned, touched on a little bit, whether or not flow is the answer, whether you just we can use flow to restore the functioning of that ecosystem, whether we also need to couple that with restoration activities for, like if it's something simple to pick low-hanging fruit, if it's a levee system, and we're trying to operate within that levee, that's going to be very difficult. So trying to look at restoration to open up portions of that levee to create some floodplain habitat and stuff like that in combination with flow.
But the channel types they're based on what we're seeing over hundreds of sites that we're surveying. So they are going to reflect some of the major current alterations that we've seen. And I think that's important to keep track of. And the idea, again, is to focus on what would the flows do in these channel settings. And then we can start to play around with what happens when you start to actually tweak the landscape or start to prioritize where you want to put those flows.
Yeah.
Oh, and I also, really fast, sorry, think that this is another plug for the citizen science effort, because if we go in and people are going out to sites and they're saying this looks nothing like what the predicted channel type is, we might start to see patterns in what is driving some of these alterations and where they occur on the landscape, and use that to inform our modeling tools to better predict what we're seeing currently.
Okay.
You're going to get everybody jumping in on this one, Jacob. I don't disagree with anything that Dan and Belle said. I think I would just go a step up and say that to me, the Central Valley is not a natural setting anymore. It hasn't been in a long time, and therefore this tool may just not be applicable to that one, and that's okay. The idea behind this is that we want a suite of tools that we can put together in our toolbox. This is exactly what Tier 2 is about, is to be able to come in and say, okay, I'm in this incredibly highly managed system. I'm in Northern California, I'm up there in the Northern Central Valley, and there's no way we're gonna knock down every single levee and tell the farmers that they can't farm so we can restore that. We get that, that's totally understandable. Our management objectives then in Tier 2 might be to figure out, can we meet any of the functions that we know we want to happen based on our knowledge and state of the science. And that's okay. I think that's perfectly fine. A lot of the geomorphic classification that Belle's been doing has a lot of place in the areas that are partially modified. My personal opinion is it's not applicable to the Central Valley. That's okay. Instead, we should be looking at models that are there. We should be looking at the more detailed data we have, and we should be looking into potentially different sets of tools that might say, is there somewhere on this landscape that we could restore more than just one function? Or can we do multiple objectives? And we still have those goals and those functions and processes as the goal that we're shooting for, but the tools we use to get there and the methods and decisions we make to get to that might just be a different set. And so I just sort of want to throw that out there as sort of a slightly different perspective.
Yeah, I completely agree. And that hierarchical framework then allows you to sort of walk through and prioritize your resources effectively and say, okay, we have tools that we can get at these systems relatively well with. Let's start with that and then focus on getting that high resolution terrain and systems where we really need it and we don't have that information or this isn't relevant.
Okay, so we're gonna have to wrap up. So Julie, I'm gonna give you 30 seconds to have the final word.
I get the last word.
Yeah.
So this whole set of tools is statewide, and 86% of streams are poorly gauged. Even fewer of those have flow recommendations on them. So this is meant to say, let's have a baseline so that we have a flow recommendation everywhere. And most places, we don't know what our management objectives would be. We haven't done that work. And so this would apply, Tier 1 would apply. In the Central Valley, we've battled that out in a lot of places, and we're still working on flow. We're still working on the objectives, and I've done a lot of work on that. And I think that's where we have to go. I totally agree with Sarah that Tier 1 wouldn't apply there. But we should have the processes where we say, these are what our objectives are. This is what we're trying to achieve for these places. Let's look at the trade-offs in a Tier 2 context. And that footprint would just, go over the Central Valley, and you wouldn't do Tier 1 in most places there.
Okay, great. So as we wrap up this panel, clearly a lot of work's been done, but this is still a work in progress. So Dan in his opening talk gave you some web links that you can, and the LIRIS listserv and opportunities for continued engagement. So if you're interested in this topic, you can go to the various websites and sign up for lists and stay engaged in this process because it's still ongoing. So with that, I'd like to thank all of our panelists and all of you for some stimulating discussion. And do you have any announcements before we go to break? Or? No. I'll turn it back over to Greg and then give our panelists a round of applause.
So just a reminder that as you're leaving, put your plastic name tag in the reuse box down by the building entrance. And don't leave too early, though, because stay around after the break. We've got not only a really good presentation, but the rollout of the status report. So, and those who make it to the very end might get a sticker or two. So just trying to keep them around. Anything else? All right, so 15-minute break. So according to that clock, it's 25 or 35 after, but it's probably more like 32 after in reality.
Also, the visitors' badges, drop those off at security.
Okay, we're going to get started here. Grab a seat when you can, please. All right, thank you, everyone. So we are in the end stretch. So our next set of speakers is going to take us home, starting off with a really cool tool developed and going to be talked about by Dory Bellin from our Division of Water Quality. She works in the GAMMA program, and that stands for Groundwater Ambient Monitoring and Assessment. Thank you. It's late in the day. I think I can even remember SWAMP at this point. So anyway, Dory Bellin, thank you for coming, and have at it.
Right. Hello, everybody. You made it. You'll get a sticker. All right, so as you said, I'm Dory Bellin. I'm a geologist for the GAMMA program. GAMMA stands for Groundwater Ambient Monitoring Assessment. We've been in existence since about 2001, started with legislation to start a statewide comprehensive groundwater quality monitoring program in the state. We didn't have one, and we needed a baseline of water quality. We also wanted to look at any anthropogenic effects to groundwater. This is the resource used for 40% of our public water supplies, for whether you're using a public water source or a domestic well. We also wanted to look at trends. So we look at some low detections for a lot of organic chemicals. And USGS is our technical lead for this program. They work very hard on assessing the groundwater quality throughout the state. Our main goals are to improve the statewide comprehensive groundwater quality monitoring and make this information available to the public and all of our customers. So in the past, making this stuff available to the public, we worked really hard to be in person to a lot of these stakeholders throughout the state. Our study units started off 35 of them, plus more that we're doing now. We worked hard to create a lot of reports, hard copy. We had Lyris lists. We worked with our IT department. But today, we actually can do a little bit better. And since we have new groundbreaking applications and tools, the staff within GAMMA can create a lot of these tools that we can make for our public to access this information. And I'll be showing you some of those today. This lets us share this data really quickly with everyone throughout the state, and it gives us a lot of ways to interact with that information. So the GAMMA program collects data in a lot of different ways. We have our actually own sampling, like I mentioned, with USGS. We've done sampling in the past with our own staff at the Water Board for domestic wells, and through Lawrence Livermore National Laboratories with our special studies project, where we did a lot of groundwater age dating, noble gas, and nitrate studies. We also have an information system where we bring all this data together. We bring data, groundwater data from the Division of Drinking Water, USGS's NWIS, Department of Water Resources, pesticide regulation, other cleanup programs and groundwater studies, and we let all of this data talk to one another so people can actually visualize this data, query it, download it, and use it for their own use. This is currently available, has been for about the past 10, 12 years, and hopefully a lot of you are familiar with the fact that you can access this groundwater data, not just from our GAMMA program, but through a lot of other groundwater data systems out there. Now we have these great tools that we can use. Staff like myself can create tools. It removes the IT kind of link or that time frame that we would need. It lets the scientists that work closely with this program and its data to create the tools and keeping that message consistent throughout. This was, I think, one of the first ones created. It allows someone to go to a map of the state, click on the different study units throughout our program, the Party Basin Project, and they can see the wells that were sampled. They can get links to the reports that have been published, and they can understand how this study area kind of interacts with other boundaries in the state, like groundwater basins. This is another tool, and I'm going to show you more in real time. This lets the groundwater age dating that we did closely with Lawrence Livermore National Laboratories. This is a tool that we created that lets you look at the tritium helium age dating and relative to different levels throughout the state, so you can see where that youngest water is, the tritium-containing groundwater, to see where areas of recharge are higher than others. So this is a really great tool for whether it's a water district, recharge programs and projects, or simple research projects. Other data can be added to this frame, like soils data, more predicted tritium levels from different depths throughout the groundwater resource. There we go. Some other new tools would, 1,2,3-TCP trichloropropane is becoming a little bit more well-known in the news and throughout the customers, water customers in the state. This is a story map that we have developed that allows someone to go to the tool, enter in their address, and they can actually see how many wells that have been in excess of the 1,2,3-TCP MCL within 2,000 feet of their location that they've entered into the tool. So you can get an idea if you are in proximity of a known exceedance of TCP, especially if you're a domestic well owner. So this is a really great resource. We also have another one for nitrate. So you can go here and use that tool as well. And I believe I brought that one available. Here's the TCP tool. We can use our location here. It zooms you into the location. It adds that 2,000-foot buffer. And if there were any impacted wells in that location, it would show you what those wells were and how many there were. There's also information within the story map that tells you about 1,2,3-TCP, what chemical it is, where we find it, what its MCL, maximum contaminant level, is, and then metadata that was used for that tool. Salt and nutrient management plan, that program is using prioritized basins, much like the GAMMA program throughout the state. Another web app lets you look at the status of those management plans throughout the state and links you to those reports that have been published by the regional boards. And this is something that USGS at the GAMMA program has been working really hard with. And I wanted to show you this. We have taken all of the PDFs of well completion reports in the state, and we want to digitize this information so we can now locate all of the information from the well completion reports in an attributed digitized way. And you can interact with this data to see the well completion report number, where it was located in that public land survey system. You can see when it was completed. You can see depth information about that well. And you can look at the different types of wells that are in that area. We've also have different information as you zoom in and out with this map. This shows you a heat map of where all the wells are located. And if you zoom out even more, you have a heat map with the county boundaries. So as we move along with the shallow study units with the GAMMA program Party Basin Project, we'll be completing the counties as we go across the state. So we'll have these well completion reports digitized more and more as we move across the state with our program. So we're working on a few that are really neat in progress. USGS is working very hard at a trends tool. So like I mentioned, we started sampling groundwater, the beginning of 2000, 2001. And we have a lot of data, but we want to be able to look at that trends data over time. So this trends tool is going to allow users to look at trends data, look at statistically relevant trends, statistically unrelevant trends, and be able to look at our GAMMA data through time. That should be coming, I would think, by fall or winter this year. And another big program that the GAMMA program is kind of spearheading is the source water protection project. The source water protection kind of subject requires groundwater and surface water to talk to one another. So we want to have a data hub because this data doesn't really exist in one location online. So this data hub will bring a lot of surface water, groundwater, like surface water intakes, groundwater wells, soils information, TMDL locations, all sorts of information from Clean Water Act and Safe Drinking Water Act programs. So look for that by the end of the calendar year as well. So in conclusion, just wanted to stress that these tools, mainly from SWRCB, the company that produces our GIS programs, they're a vital role to the GAMMA program. It lets scientists like myself make these applications, keeping the message intact, being able to do it in a quick manner, deliver it to our customers that need this data, and be able to improve our messaging and the communication of groundwater issues to the public.
Oh, don't leave yet. There might be questions. Any questions for Dory?
I think I have two questions. On the TCP query of the gamma, rather than a specific site or well, can I put in municipal boundaries and still get detects of the wells around that? And then my second question, maybe the first, would be who populates the TCP data within the gamma, or is that all voluntary?
So the data comes from the GAMMA program. Our information houses not only the GAMMA program data, but other programs in the state that have groundwater quality data, like Division of Drinking Water. That query is just refreshed about quarterly. So I go in and actually update that data, so any new results come into the tool. As far as adding your own information into the tool, that capability is not here. But I can provide a download for you to where you'd have identical data to that, and you'd be able to do that on your own GIS. Or I can always speak with you personally. We can always, talk about improving the tool to do what you would like to do. Any questions? Thank you.
Okay, so with that, it's our final presentation. So we are going to unveil the water quality status report. We've done this, this will be our third year that we did this. And this is essentially our best attempt to gather up partners who are telling really good stories about water quality, known trends or insights, or demonstrating good data science tools to go to places that haven't been gone before with the data and the water. And every year we expand that a little bit. So how many partners did we have this year? We had 12 partners this year. And we use the SWRCB story map. And so in a minute, I'll introduce Michelle, and she'll go through introducing the partners that are here to help tell the story. But I really love the fact that this gets bigger and better each year. We've got a drinking water story, at least one or two in there. We've got a groundwater story in there. We continue to expand this. This could even at some point include those ecological flow kind of stories, because really when you say water quality, it's really everything. It's the water resources. So we welcome people who have ideas for next year's status report. And eventually what we'd like to do is have, instead of this be just a collective lift and a let's tell a story, let's start building some systemic things. So what would be the best performance measures and outcome measures for water quality storytelling in California? So we're starting to showcase what are the options and what's the art of possible. And the goal with this project is to eventually start building some systemic things that just could tell the story along the year too. It doesn't have to be an unveiling every year. So with that, thank you teams and everyone who partnered on this, and especially to Michelle Tang, who did a lot of wrangling of people and data to make sure that this thing got in on time. So Michelle, thank you very much, and take it over.
All right, thanks, Greg. Before we start, though, I'd like to just take a minute and see if the people who are here today, the partners who contributed to the water quality status report, would you mind actually coming down and sitting in these seats, if you don't mind? I think it might be easier. And we also might have time for a quick question and answer session at the end. So it might just be easier to have everybody out here. Everybody seats? Awesome. Great, we filled it up. Okay, well, hello everybody. My name is Michelle Tang. I am an environmental scientist in the Office of Information Management and Analysis at the State Water Board. And as Greg mentioned, I worked on this year's water quality status report. This is our third year doing it. We started out in 2017, and a lot has changed since then. We've learned a lot, and so I'm proud to present this year's report. So to kind of back up a little bit, what exactly is the water quality status report? Greg mentioned this already. It's really a showcase of all the different ways in which water board staff and our partners are using data, turning it into useful information, and informing decisions here at the water boards. So this year, we had a total of 12 different data visualizations or data stories that are featured in this report, all covering a range of topics, which Greg just mentioned, and submitted to us or contributed by state board staff, regional board staff, and our partners, SWRCB and SFEI. So what you see on the screen is the report. We use the ArcGIS Story Maps platform, which I believe Joel Kramer and Gino, you guys gave your talk yesterday using the same thing. And it's a great interactive platform, which we've used for all of the editions so far, just because it does a really great job of presenting both a narrative and data together in a really interactive, engaging way. So here's just scrolling through it. It has different panels. We have different sections on the side. It's not to advertise for Esri, just putting a plug there. It's a great platform. So for the people who attended the Data Science Symposium last year and who remember last year's report, there are some similarities and also some differences this year. We stuck with the same kind of land to sea connectivity theme this year, which just kind of looks at the watershed as a whole, like holistically. The sections in the report are broken down in terms of land, streams, lakes, and the ocean and estuarine systems. And the report itself is laid out in the way where you're kind of traveling through the watershed and discovering how inputs in different parts of that watershed can flow down and affect other parts of the watershed. So we kept that same theme this year because it worked really well last year. And another also similarity is that for each of the data visualizations that are featured in this report, and you can just scroll through it, and we'll have each one come up and talk a little bit about their own data visualization. But for each data story, data visualization, we uploaded the data sets to the Open Data Portal. So at the very end of the report, there's a section called Dive Deeper, and there's a link directly to the California Open Data Portal. And on there are all of the data sets from each of the different figures featured in the report. Or if we don't have the actual download file, there's a link to where you can actually go and get it. The differences in this year's report, as Greg mentioned, we were able to kind of expand the scope of the report to include not just surface water, but also groundwater, drinking water. And this is something that we actually really wanted to do since the first edition of the report. And so I'm really happy that we were able to bring that on. Dory, who just presented, she created an original brand new data visualization just for this. So thank you, Dory, for doing that. And then also another new addition this year is that we have a new section, which is a little different from last year, called Emerging Tools and Methods. And as the title implies, these just kind of highlight certain data visualizations or certain approaches, monitoring methods that are pretty emerging in a sense, and that could really change how we monitor our water quality in the future or how we analyze data in the future, really kind of focusing on the integration of data and making these really complex data sets more simple and easy to understand. So one of my favorite things about working on this report is just to see what people are working on, to hear about, how they created a certain data visualization and any challenges that they might have faced, because hearing from them, I learn a lot about data visualization too. It helps improve my work. I can keep current with trends and technology in the field. And it also, I like to create that dialogue because it helps promote a data culture within the organization and within government as a whole. So with that being said, I'll go ahead and start inviting each of the different, each person who contributed a data visualization or data story to this year's report, and give them maybe like 5 minutes or so just to kind of talk about whatever interests them or whatever their process for creating that data visualization, what they learned for it, or whatever else they want to talk about. So I'll go ahead and the first person's story.
Deja vu. Okay, so saying what the status of California's groundwater is kind of difficult in one data interaction, but I decided maybe one great way to show the status of groundwater quality in California was to give you the most common constituents found in exceedance in widespread areas of California, and then show you geostatistically, putting that analysis, applying it to California, where those predicted areas would be across the state. When you go to this story map, it's a slider story map, and I'll show you how that interaction works. On the left-hand pane, there is some narrative discussion about California's groundwater, who uses it, links to different sources that are mentioned. It explains the map, the shaded areas, and what is included in that map. It includes some work that the GAMMA program was working on within groundwater, like the needs assessment under Human Right to Water. It links to the GAMMA program, and then other information about the Division of Drinking Water. So when you first get to the story map, you'll see this slider. It looks like nothing's here. But this slider works so you can reveal data that is going to compare to other layers that are on the map. You zoom in one level, and you can start to see more detail. Now, the geostatistics that I used in this map is empirical Bayesian kriging. It does a really good job with creating multiple models, hundreds of models at the same time, to do a better job of looking at groundwater data through the data that's been imported into the tool. So that model is fit, and an output is produced, and that's what the output is on the left-hand side. This output can look very strange in some regions because the tool is applying this model to its nearest neighbors, meaning the well locations. So as these regions are produced, the model is going to continue looking for other nearest neighbors. And a lot of times what you'll find at the edge of certain zones, because this was clipped to the state's boundary, you'll see regions like this that are going to be in error because it found maybe a couple of wells in this location, and then it kept looking for nearest neighbors to continue that prediction. So when you're doing geostatistics, there is a level of quote-unquote professional judgment that you'll apply so you can make a final judgment call on what the actual prediction should be. That is what the right-hand side is. So I tried to keep the colors consistent so you can make that comparison very easily visually. But you can see some of the green, that is going to be the arsenic. And so the prediction tool created the weird kind of blob there. And then the final blob would be the one that you see on the right. The way that these were finalized was one, to be more on the conservative side. So if there is some weird details that maybe go concave or maybe go across a region, a hydrologic region that I do not think the same hydrologic and geologic conditions exist. We would either cut that off or we would expand it into a more even oval shape. A lot of times you'll have a region be defined, and these predictions are of where that chemical is in exceedance of its MCL. A lot of times a region will be defined where I don't want to make a final region because it's either so small or included such a small number of wells that I don't feel that it meets the expectations of this map. And this map being, these are where we consistently find these chemicals above the MCL in these regions. If you zoom in again, you'll see some point data emerge. The point data being still consistent with the colors. You will see that we have nitrate, arsenic, total dissolved solids to show the salinity, uranium, 123 TCP, and perchlorate. The dots are not all of the dots that were used, all of the point data that was used in the geostatistical model, but it is showing you the exceedances within that point data that was used in the analysis. So you can kind of see that when the final areas were drawn, I tried to expand some of those areas to include some of those exceedances. You click on one of these regions, you'll get some basic statistics about that region, meaning the chemical, number of wells that were included in that analysis, its mean, medium, maximum, minimum detections. And you'll also get the same information when you click on a point. You'll get the name of that well, you'll get the average. Let's scoot this over. There we go. You'll get the name of that well. This is a drinking water well, the average results, and the number of sampling results that were used to define that point. The data that was used was actually all sampling points that had at least 2 or more sampling results done for that well. So you can go in and you can investigate how those final regions were made and look and to see where those consistent exceedances for each chemical and what wells those were throughout the map. Any questions? Thank you.
Thank you, Dora. All right, we're going to just reserve all questions for the end, and we'll have everybody up here to take your questions. So next person, Bryn.
Gotcha. So the first thing that I realized upon hearing Dory's talk is that I needed Dory at my lab because we're so far behind the curve with these visualizations that we just don't really have the capabilities in our lab. So one of the things that Michelle had asked me to speak about was what are the challenges that we face when doing data visualizations, and basically it's a skill set that needs to be fostered. And working with University of California, Davis, I don't have funding to hire a position, that can do that kind of work, but we rely pretty heavily on Michelle to help us out. And so my figures are actually quite mundane compared to a lot of what you're probably going to see today, but the message is still there. And the program we work with, the Stream Pollution Trends Program, is a statewide contaminant and toxicity monitoring program for sediments. And we have a 10-year data set, and it's a pretty spectacular data set that's pretty heavily used by a lot of different groups in the state, and it's got a lot of stories that can be mined. And I feel like with these the right kind of visualizations, I feel like it would be easier for these stories to pop out. The things that I can see in my brain, I have a hard time translating to pictures and maps and things like that. But what we did is with our toxicity work. We're looking at these sediment samples all through the state, and we're measuring these toxicity responses in organisms. And so we're working with really basic sort of blunt instruments, canary in a coal mine kind of tools. And 1 in 5 of our samples is significantly toxic. So we have dead amphipods in our samples, and these dead amphipods actually relate pretty directly to environmental impacts in the field. There's lots of studies that relate laboratory toxicity work to environmental surveys. So we know that there's impacts of beneficial uses, and it's pretty clear from our data set. And what we're doing is we're looking at trends based on land use. And so increased land uses in our watersheds, increased urban land use in our watersheds is really clearly related to increased incidence of toxicity. So I have some basic figures here that show our, will this open on the right if I click on it, or is it just the way it is? It's just the way it is. So the toxicity in urban land use, when we have increased urban land use, we have increased incidences of toxicity. And a lot of the incidents of toxicity we have in the state are related to insecticides, particularly the pyrethroid insecticides, plus some more newer classes of insecticides, the neonicotinoids, phenylpyrazoles, the types of things that people are applying to the backs of their pets to control fleas and ticks. These are the things we're seeing in a lot of our urban watersheds, and we're measuring these chemicals in our spot samples at the bases of these watersheds. So increased urban land use, increased incidence of toxicity. We measure pyrethroid toxicity in terms of pyrethroid toxic units. So this is the potential of additive pyrethroids to contribute to the toxicity we're seeing. We're seeing a significant increase over the last 10 years of pyrethroid magnitude, number of detections, as well as the toxic units, measured as toxic units. So that's what the box plot is right here. And this pyrethroid use is also significantly related to the urban land use. So as you look at the land use in a watershed at a 5-kilometer scale from one of our sites, you can pretty clearly see a slow increase in these numbers of toxic units as you increase this urban land use. Spot's a really complex data set. There's a lot more analytes that we measure besides pyrethroids and fipronils. There's many layers of land use that we can examine. As I mentioned, we currently lack the expertise, but we're hoping to expand that for the future. And the way I envision this happening is much like what Greg said just a minute ago. We'd like to have this sort of just be live on a website, and as we get updates to all of these data, which are happening year-round, we could just be constantly feeding into the latest trend figures, and anybody can check the trend at any given moment on the map in their area. So based on land use, based on chemical, and based on organism.
Thank you, Brandon. Just to kind of add on to that, we are in SWAMP and in OWIMA really starting to take a crack at a lot of the spot data and creating those interactive dynamic data visualizations. So that's perhaps something that you'll see in next year's report. So the next person, I'd like to invite Dr. Dewitt Tedesse.
Okay, thank you, Michelle. So what I will do is I'll tell you a little bit about the data set and try to demonstrate the dashboard. So this data set was downloaded from, as you said, from Open Data Portal. We do have a large data set for toxicity. Toxicity is the primary water indicator which many water quality practitioners are using. So we do have a large data set. So I downloaded that one and put it into toxic site and not toxic site. So the data ranged from 2001 to 2018. So as you can see in this dashboard, I have to be a little bit what I can see. So the dashboard itself is have several segments. If you see from the top, you see the various filters, starting from the matrix, organism name programs, and so on. And what happened? Okay. And there are two maps, and there are two graphics. So whichever way you filter, you will end up having the same information. You can filter from the top rows, or you can filter from the maps and from the graphic as well. So if just for demonstration purpose, so by the way, these are about 28,000 toxicity tests throughout California, ranging from 2001 to 2018. So there are about, if you see the left hand, the California map itself, the whole thing, so all the circles you can see are about 2,800. And you can select either from the counties or the specific monitoring locations. So I'll start off with showing the first county here. So if you choose Alameda County, so these are all the monitoring locations. So I come here and magnify it so that you can see how many there are there. Okay. I don't want it to go there. Okay, here they are. These are all the monitoring locations from 2001 to 2018. So from this, if you want to select one monitoring locations, you see here, when I was choosing Alameda County, this number of the graphics have changed, if you have noticed that one. So if you want to choose one monitoring location, so you come here and list. Here you go. Now, if you see here, you see this monitoring location have 88 measures. Within the circle, there are slices that represent each monitoring test. So if you pick this one, this is just one test for 2013. If you want to look at all toxic sites in this site, it is all this one. So you can see 11 of them in this one. There are tables if you want to look at it. It will give you the details of the table right there. So you see when I'm hovering, you see the survival rate, the species tested, the monitoring locations, the program who collected it, etc. So these all data sets have like around 28, 29 programs have contributed to this data set since 2001. So that's it.
All right, thank you, Dwayne. Our next, I think, okay, so one of our partners, contributors, Dr. Lansley, he wasn't able to make it today, but I encourage you to check out his data visualization. It's actually a data story on the Elk River and the adoption of the sediment TMDL in 2016. And it's a really cool data story that combines historical photographs, aerial imagery, sediment, or not sediment, land slide risk data, as well as sediment load data. And it's just a really awesome data story that I encourage you all to kind of go in and look at yourselves. Next up, we have Alicia Wenzel. Oh, and this is Lance's data story, just a preview, but here we go.
Hello, thank you for staying. So I work for the Central Valley Water Board in the SWAMP program. I don't think we need to go through that. So my data story it's a pretty simple map. My program has had a monitoring program since about 2007 where we go out each summer to monitor swimming holes and recreational rivers to look at whether it's safe for people to swim out there. We saw this as kind of a data gap for our inland water bodies. And kind of one of the things that I've heard a lot the last couple of days is, one of the problems with our data is we write reports or something like that, but knowing where it was safe to swim last summer isn't actually always useful for people. So this was an effort that we went through to just try to get our data out there much more quickly. So this is a map for the Lower American River. let me zoom here. So for those of you that aren't local, American River flows into the Sacramento River just northwest of where we are. So we're in downtown Sacramento. Since January of 2018, we've been out monitoring weekly at 9 sites on the Lower American River, as well as 2 sites on Steelhead Creek, which is actually a constructed channel that flows into the Sacramento just upstream. And there's been a lot of focus recently because of some trash and debris cleanup efforts. I can't take credit for this. I was lucky to have some really fantastic scientific aides. That's how we've been able to do this, who've since moved on to new opportunities. So they kind of figured out how we could come up with a system so that we could easily input our data and have it show up on this map. So we had crews out sampling this morning. So those samples would be processed in our lab this afternoon, and the new results will be posted on the map tomorrow afternoon. So the colors on the map are kind of reflective of the statewide bacteria objectives. So sites in green are currently meeting the objectives. Sites in yellow mean the average concentration is above the geometric mean concentration of 100. And then sites in red are above the 320 statistical threshold value. So you can see, for instance, Discovery Park, which is a very popular park just up here, is currently red from our data last week. So if you click on one of the sites, you get this pop-up window so you can see a photo of the site, get more information. It'll tell you what the most recent result was, so that was 816. And if you scroll down, you can also see results from the last 4 weeks. And click on a link that will take you to kind of a summary spreadsheet if you want to look at all of the data we've collected since January of 2018. Like I said, it's a pretty simple but effective way for us to get our data out to the public and local agencies. We've also started doing this for some other watersheds where we're monitoring this summer. So if you go to our Central Valley Swamp website, you can look up data for stocked and urban waterways, as well as some upper portions of the San Joaquin River that are being monitored by our Fresno office.
All right, thank you, Alicia. Next up, we have Dr. Keith Bama-Gregson.
Great, thanks, Michelle. Yes, so my name's Keith, and I talked a little bit about freshwater harmful algal blooms yesterday, and I actually mentioned this map here. And so in 2016, the Water Board started a database where people could report blooms across the state, and we would start to collate and collect that data. And these are all voluntary reports, so some of them might be a person in the public who might see some green water and not be really sure what's going on there. Others are with partner agencies that have formal monitoring programs, and so they're contributing data to this. And then other data comes from water board staff and regional board staff who are responding to some of those bloom incidents themselves. And so, there we go. Yeah, it's a tableau. Yeah, so this, so each dot here shows a bloom report, and then they're color coded by the time at which that report was submitted. And so the brighter orange colors indicate reports that were recently submitted. And so you could basically look, and if you were interested in going to a particular water body and want to know if it was safe to swim there in terms of harmful algal blooms, you could see if your water body was listed here on this map, and if so, when that report was last filed. Here. Great, perfect. This is what I was looking for. So then if you hover over it, you then get the bloom report that was that's in the database. And so this shows the latitude and longitude of the bloom, the county, the type of water body, and then there's a narrative in there where our staff has basically typed up what we noticed. And so this is actually a bloom at Horseshoe Lake up in Chico that we had regional board staff out there earlier or at the end of last week's sampling, and we did detect toxins on it, and they were moderately high. They triggered our second level of warning. And so here you can kind of read about the history of reports and information there. And then this data is also on the open data portal, so you can also download it as a CSV file. And and so one of the goals we have is to try and increase the number of partners. And so we've seen that over the last couple of years. We've seen more and more people contributing reports to this. And as the word has spread about it, we try to get this information out to the media and to the public that they can submit their information here. So it's been a great way for us to start to understand where and when the blooms are happening in California. That's it.
Great, thank you, Keith. Up next, we have Dr. Jay Davis.
Thanks, Michelle. Thanks to all of you for sticking around to get your stickers. I'm the lead scientist for the swamp bioaccumulation monitoring element, and the main thing we do is monitor contaminants in fish across California. Turning data into information is one of the themes of this meeting year after year, and Laurel Firestone made a pitch for the importance of risk communication, the fact that information is power. Information empowers managers and the public to protect the environment and public health. But we tend to focus overall more on the data and generation and data side of things rather than the information side. So I wanted to do a little data story that highlights fish consumption advisories in the state. And I think they're a shining example of information that's generated to serve that role for risk communication. So the data story summarizes the whole process of generating the data and turning that into information on fish contamination. Starting with the planning process, where the water boards, US EPA, and the Office of Environmental Health Hazard Assessment, and as well as scientific organizations get together to plan how we spend the funds that we have for monitoring contaminants in fish. We've got plans for monitoring all of the major water body types in California. This map here shows a plan for long-term monitoring of mercury in lakes across the state. But we also monitor the coast and rivers and streams. And overall, we have a plan of revisiting these water bodies to meet the SWAMP goal of providing timely, high-quality information on water quality throughout the state. One of the important parts of this process in the planning stage is we get detailed input from OEHA on the data that they need to expand and update the fish consumption advisory. So they're really great partners in this. They give us really detailed input on a water body specific basis, exactly what species they need and how many fish from each species. The next step is that we go fishing. We collect thousands of fish every year. In 2017, we collected about 2,000 fish, for example. We sample more than 40 water bodies per year. Overall, the fishing team spends months out across the state from April through October, hours and hours and hours of fishing. So that's a huge effort. Then the next step is processing all the samples, the dissection and coordination with labs, and then the chemical analysis. We analyze mercury and PCBs and a few other chemicals. Overall, there are 90 different parameters. Quality assurance is a high priority, so the SWAMP goal of high quality information, we take that very seriously, and have rigorous QA. Then the next step is managing and reporting the data. And we do this, we try to do this in in a very prompt way, and we have a group, the Bioaccumulation Oversight Group, that does a review, a peer review of the data set each year, and then we've come up with an expedited way of getting the data onto the Open Data Portal, into CDN, and then also we have the Safe to Eat portal that's part of the My Water Quality website for the Monitoring Council. One of the things we did this year with the portal was we revised it, and one of the reasons I'm highlighting fish advisories is that we revised the portal to have a greater focus on the fish consumption advisories, because the advisories are really the key information that we want the public, if they look at anything, we want to make sure they look at the advisories and know how to make choices about what fish they consume from California water bodies. So it's quite a challenging task to distill this information into clear advice for the public. It's a very complex data set and a complex message that needs to be communicated. We've got a variety of species that have different patterns of accumulation. Some accumulate mercury, for example, a lot more than others. We've got a host of chemicals, and there's a need to take the information on all the chemicals and come up with an overall sort of statement on the relative risk of consuming one species or another. We've got concentrations that vary from one location to another. There's the toxicology information that's, the literature on that is constantly evolving, and it's another complex part of this that OEHA sort of interprets all of that and applies it to our data. There are different populations. Different parts of the human population have different sensitivity. So the fetus and young children are most sensitive to the developmental toxicity of mercury and PCBs. Lower IQ is one of the main outcomes if you have excessive exposure. So pregnant women and young children are the most sensitive population, and then males, adult males, and women beyond childbearing age are a less sensitive population. And then there are health benefits of consuming fish. Omega-3 fatty acids, you've probably all heard of. They're very beneficial to your health. The levels of these fatty acids vary from one species to another. So there's a lot of information to all pull together and try to communicate, and then it's a tricky message to communicate of wanting to encourage fish consumption, because consuming fish is a great source of nutrition, and there are significant health benefits, but you want to steer people away from consuming the fish with high contaminant concentrations. So you don't want to scare people away from eating fish entirely. You actually want to just help them make smart choices. But OEHA are experts at this, and they've been working at this for a long time, and they've been getting better and better at it. Overall, they've issued 110 advisories for specific water bodies across the state, as well as general advisories for where they're for water bodies that don't have site-specific advice. There's a general advisory for lakes, and there's a general statewide advisory for the coast. So the ultimate information product are these advisory posters. Aaron Hester showed this earlier. And these posters, I think, are really an elegant way of displaying this complex information. They've been refined over time. I'm not going to go through the details of it, given time constraints, but they've honed this message I've been partnering with OEHA on different studies for over 20 years, and I've seen these posters evolve and get better and better. One of the key things is that they actually test the information product with the audience. I think that's really a key to successful communication of information. There have been focus groups over the years that they've worked with to hone this message. And they've tested the message with different ethnic communities. Fish consumption is an area where these sort of racial considerations, environmental justice considerations are very important. And over the past, over the years, that kind of input has been part of the history of developing these posters. So with this data story, I wanted to focus attention on this highly evolved form of risk communication and the process that supports it, and that's my story.
Right, thank you, Jay. Quick question, is Peter in the audience? There you go.
Hi, everyone. I'm Peter. I work with Swamp IQ. Originally, when I came up with this storyboard, it was to champion the SWRCB product as sort of a PowerPoint on steroids. But judging from today's content, I don't really need to do that. But I had to tell a story, and in December, I had gone on a BioBlitz, which is a volunteer science effort where people get together and go collect as much data as they can. This was put on by Cal eDNA down in UCLA, and we were not only collecting iNaturalist data, but we were also going to collect eDNA samples. So normally on these BioBlitzes, you go out and take photographs of what you see, and they have great data sets that pop up from all over the country. So we went down to Santa Cruz to the Younger Lagoon because Cal eDNA does, they like to focus on unique natural areas. So the Younger Lagoon is certainly one of them. And one of the great things that the SWRCB product can do is sort of give you a better view of what's going on in the area you're trying to show, so you can move around in here and really explore the area. You can also do great things, inserting different data and links into your story like that. So we did that, and I go on to explain about the process, how they process eDNA down at the UCLA campus. And I did that by embedding a bunch of videos, a video playlist of exactly how they do that. And then they put up their data. This is a very useful data set with all the taxa and everything you can find out there. And I encourage you to explore this because it says a lot more than I'm telling you today. And with those data sets, a lot of people don't think they're robust, but they are getting more robust all the time. And our data science is happening outside of government and outside of academia. I can easily download a script that allowed me to check out mayfly data. I was just interested, hey, why do they call them mayflies? Sure enough, with about 20 lines of script, I was able to plot the months they came. Month number 5, that's May. And also, then quickly with the CSV file that it generated, I was able to make a quick map to show where and what month they popped up. So I really think that volunteer data science is being refined and improved all the time. Places like the Dataverse project and R Open Science are doing a lot of great work with the R community, creating software and tools. And I feel that we need to, if we're going to grow as scientists, we need to grow the community and look outside the normal places we would normally be. So thank you.
That's awesome. Thank you, Peter. So we have 2 more data visualizations. So thank you, everybody, for sticking it out towards the end. And for you, our enthusiasts, our last 2 data visualizations are our Shiny apps. So with that being said, I'll go ahead and invite David Altair.
While that's loading, before I get started, I did want to give credit to the San Diego Coastkeeper who came up with the conceptual idea for this tool. So really what I did is just kind of took their idea and implemented it in R and the Shiny package, as Michelle mentioned. So what it is an online tool, and the intent is to summarize industrial stormwater effluent data that gets reported to us here at the State Board, and then to look at that kind of in combination with some other indicators of impairment and pollution burden. So if you just come to the landing page, there's a bit of a background and some instructions on how to use the tool, but I'll just jump in to the kind of the main part of the tool is this WQI scores tab. So the tool pulls in data, kind of a more or less direct connection to the stormwater monitoring data on our open data portal, which comes from the SMARTS database, if you're familiar with that. So then if you look at the map, you can see if you just look at each point, everyone is an individual industrial site, and then the coloration is it indicates a water quality index score, which we've calculated. I'll go into a little bit more on that, but basically green is good and red is poor score. So what the score itself is from it's based on the Canadian the Canadian Water Quality Index score. You can see, so here's a little bit more information on how the calculation works, but essentially it just takes into account the frequency and the magnitude of times when sampling data is above certain thresholds. So the tool allows users to use some predefined thresholds or enter their own standards, and these can all be customized. You can kind of inspect the data and download it as you'd like. So then back onto the map, those scores get translated onto the map, and you can check out any individual site, get some more information about the site itself, and about how the score was calculated. So for instance, in this case, you can see what parameters were included at this site, and then some information about the frequency and magnitude of exceedance and the overall score. So then the other parts of this map show things like the blue lines are 303D listed water bodies, and the colored polygons come from the SWRCB work that was done by WEHA that kind of integrates a lot of different indicators of impairment and pollution burden for a particular census tract. So then with the kind of the selectors on the left here, you can sort of filter out what kind of data you'd like to show. You can select what sort of standard you'd like to apply, whether you want to use, for instance, the California Toxic Rule standards, the numeric action levels, or your custom standards. You can select what monitoring period you'd like to apply the data to, and then you can start to do a little bit of selection to do things like maybe just looking at sites that have, say, poor water quality index scores. And you can start to filter on things like those SWRCB polygons. So in this case, high scores indicate poor quality. So you might want to look at sites that have low WQI scores that also fall in polygons with poor CES scores. And then you could even do things like filtering by sites that are within a certain distance of 303D listed water bodies. So kind of the point here is that it gives a way to summarize the data kind of relatively quickly. It gives sort of a direct connection to the data, so it's kind of near real time in terms of the monitoring data that you're looking at. And it could also potentially be used for things like informing our monitoring and inspection programs to do maybe targeted enforcement of sites that have poor water quality, and maybe you can maybe look and see what sites are having kind of an outsized impact on the public health conditions or the ambient environmental quality. So I think that's just about it. I will mention that you can download the data through the tool as well, and all of the data sources are listed here, and since it is written in R, the code is available through GitHub. So I think that's it.
All right, thank you, David. And last but not least, we have Dr. Marcus Beck, who gave a great talk yesterday, a great presentation yesterday. And he's another total whiz at R, so it's great to hear him talk about data visualization. Let me reload this for you.
All right, so after seeing that last talk, I'm really glad we recently changed the name from the WQI to the SQI, so as to avoid confusion with other indices. So thank you. As Michelle mentioned, yesterday I gave a much extended, longer talk about this, where I was talking about the bigger conceptual foundation for this, and that was great. I enjoy giving those types of talks, but I'm really more excited talking about these types of dashboards. And I'm totally biased because I made this, but I think this is like a really interesting way to sort of not only address some of these large-scale issues about how do you synthesize data, but also just putting the data in the hands of the people that are actually going to use it to make decisions. So I'll give you the, I guess, the 30-second elevator speech about what this tool is all about. For those of you that weren't here yesterday, this is the Stream Quality Index. It's an index on top of other indices, so why would we want to do that? Well, first and foremost, it's a communication tool. This is something that was developed for the Southern California Stormwater Monitoring Coalition, which is a collection of folks in Southern California of regulated parties, regulators, consultant groups, anybody that's really concerned with the stormwater management down there. And they collectively monitor thousands of sites, wadable streams down there, where they're basically collecting information on the chemical parameters, physical habitat, and biological response indicators as well. And so they have all these different lines of evidence that they need to sort of understand and synthesize in a way to sort of not just look at one thing at a time, but look at collectively what all those multiple lines of evidence are really telling them about the condition of their sites. So that's really what we did with this SQI. We gave them a way to sort of look at all of those three things in a way that was actually interpretable down to these sort of meaningful categories of whether something was healthy and unimpacted or unhealthy and stressed, and every combination in between. So when you go to this website, pardon me, you get on this landing page here, and you kind of, this is sort of an overview map of everything that's going on, big picture information. You get a sort of description of what the index is all about, what it's trying to do. And just sort of in a nutshell, we're actually using just the biological indicators as our response endpoint, and modeling the likelihood of seeing an altered biological community as a function of the stressors we're seeing there, where the stressors are related to water chemistry and physical habitat. And so what you get with the SQI score is this sort of actionable narrative category of whether the biology is healthy or impacted, and whether the condition is stressed or unstressed given the stressor or the chemical and physical habitat that's observed at a site. And so a site can fall into one of these four categories. Healthy and unstressed would be the ideal scenario. Impacted and stressed would be the less than ideal scenario. But we also have these sort of oddball categories where we have, as is common with multiple lines of evidence, you can have conflicting information. So we have sites that fall into this category where the biology is healthy. In other words, the bugs are good, the algae is good, but the stressors are relatively high. And so this is what we're calling a healthy and resilient community. So that's a category a site could fall in. The converse of that is where we have a site where the biology is not so great, but the stressors that we've looked at, the water chemistry and the physical habitat, they're not a likely problem that's affecting the biology. So those are pretty low stressors. And so this is a site that's impacted by an unknown stress. And essentially, these categories are, just sort of high-level pieces of information that you can get a, first cut of what's going on with the biology, what's going on through stressors, and then if you need to take a deeper dive, then you look at the underlying data, do some follow-up analyses, and sort of really figure out what's going on. So that's the foundation of the index. And you'll see from the map, a lot of red. This is Southern California, so not a huge surprise. But you can see sort of the lay of the land, how the sites fall out. This is right now showing the overall SQI categories. You can toggle it to show, right now, again, it's showing the overall, but you can also show the biological condition. This is sort of a second layer down, what's happening with the biology. So this is showing you what's going on with the bugs, what's going on with the algae. Are both of those communities good? Are both of those communities bad? Is one of those impacted, but not the other? So you can get a sense of what's going on there. And then with the stressor condition, this is going to show you what's going on with the water chemistry and the physical habitat. So here we have, again, these sort of high-level categories of low stressors across the board in green, high stressors across the board in red, and then every combination in between of stress, like only chemistry, only habitat, or low levels of both, because the way we've designed it is sort of additive based on that. So that's great. That's a high-level thing that you can look at on the map. But where it gets, I think, really cool is I'm just going to pick something. Let's look at this site. So you click a site, and now I've selected. It says, this is my site number. This is the year it was sampled. This is the stream reach it's on. We can go to this Scores tab and see some output for that. I'm actually going to zoom this out so you can see all the pieces of information. But basically, these three categories here, these are the three SQI tallies or pieces of information you get out of this index for that site. So here's the overall condition. This is a site that's impacted by an unknown stress. So the biology is not so great. In other words, the bugs are not doing so great. So this says it's impacted for the CSCI. This is our California Stream Condition Index that looks at the macroinverts. But the stressors that are there, it's in a low stress condition. So the water chemistry we've looked at this site, the physical habitat, all those things are good based on what our models are telling us. So this is kind of an interesting case where when we look at all the pieces of information going into this site, we can get a bigger picture of what's going on as opposed to just, let me just look at the bugs, or let me just look at the algae, let me just look at the chemistry. So it's sort of putting all those things together to get a higher level picture of what's going on. I know this is terribly difficult to see, but a really cool feature of this down here, this is something that was added really recently. We actually, this piece down here adds some context to these scores. And a common critique we got from this index and a lot of indices in Southern California is that, well, everything's red. What do we do with that? Well, we can sort of give you some idea of how red are you or how green are you based on a context of what an expected biological condition could be as a function of the landscape that's around there. And so we have, if you were here last year, I gave another talk about another visualization tool called SCAPE that provides that context. It models a range of CSCI scores that you would expect as a function of the landscape. And so that's what this plot is showing you down here. So you can see that line. That's the range of expected scores you get for this location. And this point is the observed CSCI score. And this is actually not a really good example because the observed score is within the range of expectations, but we do have some examples, let me see if I can find one, where the score is outside of that expected range. And let me see, it's gotta be one. There's one. Yeah, so this is an overscoring site based on the expectations. So now we know that there's maybe something going on here because this site is doing way better than what the landscape should be doing to the biological community. And so, long story short, this is just a way to add context to those scores. It's just another layer of information that sort of cross-cuts across these different products that we've developed to help interpret the indices. So this is the high-level picture. You get the overall SQI, the biological score, and then the stressors that are affecting an individual site. Now, even though this is a communication tool that's meant to be sort of high-level and telling you what's going on, we wanted to actually preserve the underlying data and provide access to that information if someone wanted to do a deeper dive to see what's going on. So if you click on the Details tab, you get these gauges that really show you all of the components that are going into the SQI. There is an empirical model underneath the hood that relates biological response to the stressors, and the raw data that goes into that is available. So we have the CSCI score for the bugs, the ASCI score for the algae, the water chemistry parameters, the physical habitat, supplementary components for the physical habitat indices as additional information, and so on and so forth. And so we designed this in a way to be like, you know, you look at this quickly, you see colors and sort of things jump out. Some things are red, some things are green. And it's just sort of a way to do a quick assessment of which things of all of the component pieces going into this index could be the thing that's driving the stress. Maybe it's nitrogen, or maybe it's only phosphorus that's, you know, affecting the water chemistry that is then affecting the biology. So this gives you the ability to do that in a sense. And then the last piece of information is this tab called Relative Details. So that last tab was just details. These are now relative details where, again, this is the data for that particular site. These lines are the values for the multiple indices going into the SQI for that site. But now instead of just the observed values, you see where those observed values are relative to the rest of the sites in this population of sites. So we can see that, okay, this site, CSCI is not great. It's actually in the 37th percentile of CSCI scores for the entire region. So now you can actually look at it and say, well, might not be great, but how great is it compared to everything else? So this is just another sort of way to think about comparisons. And then one last thing about this, you can actually filter these by different regions. So here here's SMC, Stormwater Monitoring Coalition watersheds. You can filter by counties, regional boards, so on. So I'm going to pick regional boards just to pick on them because we're at the water boards here. I'm going to pick, let's see, Santa Ana region. Okay, and then I'm going to pick this site. I forget which site I was on, but now these relative details are filtered by this region that you've selected. Because maybe you don't want to compare it to the entire region, maybe you want to compare your scores to what's going on in your region of interest. So just another layer of detail that you can pull out from this. So that's the SQI in a nutshell. As I said yesterday, this is it's a brand new tool. We just finished it yesterday. We're sort of testing the waters now to sort of get it out there and see how people might want to use it to help them manage these sites and use this as a tool to support that. And one final plug for Open Science. All of this source code is available on GitHub, so you can have this in your home and modify it at your leisure. So with that, thank you.
All right. Thank you, Marcus, and thank you, everyone. Can we give another hand of applause for all of our contributors here? And thank you, everyone, for sticking it out to the very end. I think right now I think we have time for some questions. So we can open it up, questions for any of the panelists here, or any questions about data science, data visualization in general.
Great talks, appreciate it. And again, thanks for you sticking around too. I guess I'll preface my statement by, the governor has indicated that clean, high quality water is a human right. And, our expectation is another 5 million people in less than 10 years. So I was curious, as we go through these outreach tools, how is that increased population considered in what you look at for potential water quality, water supply? The interesting last talk, do we have population by township or something like that geospaced in to maybe indicate some of the stressors as well? So I guess that's my comment is a lot of good talks today, a lot of good outreach, but we're going to have a lot more people, and I don't see us going backward to the kumbaya days of upper river flows and stuff. So how do we get ready for the next 10 years?
Does anyone want to try to tackle that? Well, I can say one thing, which is I know that as demonstrated by some of the data visualizations here and a lot of the talks within our organization, there is definitely a recognition that in the future, even now, we'll need to start integrating a lot more different data sets. So we'll have to bring in that demographic data. And I know with the California Department of Finance, I believe, does some population kind of predictions. I don't know how far out, but something like that is something that we could use, bring in other algorithms, models, and try to predict that way and try to target and prioritize program actions based on that way. But for sure, there's definitely a need to do more data integration and working with not just water quality data, but bringing in a whole bunch of other different data sets. So I don't know if anybody wants to add to that. Bryn?
We track land use in the Stream Pollution Trends program, and just in the last 10 years, there's a land use database that gets updated every 5 years, and we see the writing on the wall with increased use of urban pesticides, residential use pesticides, the people that have their roaches sprayed every month, whether they're there or not, and water their lawns. And so a lot of this stuff is, we know the trajectory, I think. And I think if you're adding population to that, you're going to add urbanized area and you're going to just increase that pattern. So I don't know if it's communicating it to the people, to the decision makers. We know that that's happening. And one of the jobs that I find difficult as a university researcher is to communicate that to the managers at the water boards to take it to the next step, whether it's a regulatory action. We talked about, somebody mentioned pursuing hotspot, of a place that's clearly impacted. We've been monitoring similar hotspots for 15 years at my lab, and sometimes there's action and sometimes there's not. So it's a decision maker thing, I think, more than a data conveyance.
Yeah, and this is Greg, voice from behind the panel, sorry. I'll just support everything that was said and mention that a lot of tools are waiting to be built. They just need permission and resources and a directive if somebody's going to use a tool. So there's a lot of discussion amongst the different groups I'm in about predicting where the people will go or what's going to be needed to protect the resources, riparian zone, buffer, A lot of the discussions you heard today about fish and water resource management, I know there's consideration into how to prevent as much future harm as possible. But land use planning and everything, governing that kind of topic in California is really complicated. So it would take someone making the decision that they're going to use the tool and then request it. So Allie points out that the Healthy Watershed Partnership has a integrated assessment tool that also integrates population. But I think it's way more than just population. It's also just these other demographic data sets that are going to be really important to start integrating into our decision tools. Again, though, there's an infinite amount of tools. I tell people upstairs all the time of we could build probably any tool that they want as long as they give us clear instructions on how they want to use it and resources to build it. It's getting easier, though. As you've seen, one of the demonstrations of this year's status report is really the facility at which staff and other people are gaining the ability to build these tools and to integrate data. And a lot of that is the data itself is becoming more available, but a lot of it is also just the technology and the knowledge and skills of the people that you guys out there, all of you. So I would not be surprised if next year we saw more of these talks that had integrated data sets that were not related to water at all.
Speaking of the integrated data sets, what's the chance of having all these indices just on one map? We got the groundwater and stream quality index, and is it just too much data, or is there kind of a simplified version you guys could integrate so that for the general public and others, they can, instead of clicking around to the various sites, you have one portal?
I'll take a stab at that again, unless, I mean, the index conversation is really interesting. There's more and more of them coming. There's a lot already. The real challenge is to doing what you said is not so much the data and the architecture and the technology, it's more about what's the purpose. Why would you want to have the water quality index looking at that exceedance and magnitude kind of a thing next to something that might look at benthic community diversity or whatever. So as long as there was a rational reason, I think we're going to again see more and more of these options of people can flip indexes on and off. The underlying data sets, one of the really interesting things too is we're getting more expanded, it's not convergence, but we're getting more and more tools that are using the same data sets to do an index here and an index there. And pretty soon we're going to be building off of common architecture. So it's just a matter of at some point it gets too big and there's too much information to make it useful as a tool. But I do think the technology side is getting more nimble at allowing the kinds of what-if scenarios to all run and operate out of the same environment where the data is in one architecture and the scripting and the algorithms are available if you know how to use them. But this is kind of a power user group in this audience right here. We also have to interface a lot of times with people who have no sense of, they don't want a lot of knobs and dials and widgets. They really just kind of want to have somebody answer a use case question or something.
So I have just one follow-up comment to you. Your comment hits me at my core because if you saw my talk yesterday, I was kind of bashing on the old way to deliver scientific products as reports. That's, as scientists, that's how we're trained to do things. And I said, well, reports that's the old school way. Now we can use dashboards and sort of really reach a bigger audience. But the more I am sort of involved in this business of creating dashboards, I'm starting to, I see a lot of examples where I feel like the dashboard is the new report. There's more and more dashboards coming out, and it's just like, who cares? I mean, how relevant is that to what I'm doing? And the point about, do we have an index on top of another index and several other indices? I mean, I understand that completely. Why would you want to do that? And I think I say this more as a cautionary tale to this group, that when we create these things, I think it's the burden on us is to think about who and why are we creating it, and who are we going to work with to deliver what we need for them. I mean, don't just create something in isolation. Work with the people that need it, and don't just do it for yourself because it's fun to work with data. You're just a means to an end, and your product will have a greater impact if it's serving some purpose. So That's all I just want to make that, I put that out there to think about that and just not just make more dashboards.
I think there might be a simple way to go about that, and thinking about trying to have indices for each of these different areas that's sort of conveying the status is like, it's way too complicated, but maybe just having a portal to, if you click on a water body, you can find out what data sets are available or what indices are available for that water body, and then you can dig deeper into the ones of interest. So maybe doing it that way, where it's not trying to convey the information on the first level, but just saying that there are data, and that you can dig there and get more information.
I'll add too, it's Nick Martirano at the back of the back, that the Healthy Watersheds Partnership, we're working, our Sea Grant fellow Anna Holder, who's helped build this event as much as anybody, is working on revamping that portal, that area, to use a conceptual framework to get the user to ask themselves questions to figure out what they're trying to answer, and then to help point them to existing tools and provide that as kind of a resource library. And then if you can't find a tool that's helping you answer your question, then you would initiate working with that work group to help maybe build you something that would help you address those management questions. So that idea is a great one, and we're trying to address that by helping the user figure out what they're trying to answer, and then point them to the resource that maybe exist, these tools and then others.
I had a question about the talk about the fish. So there was an infographic that you said was pretty extensively focus grouped, and that seems pretty great and like something we should probably do more of. So I was wondering, can you talk a little bit more about how that worked, and is that feasible to do on more our kind of key public facing graphics like that?
Sure. The part, the focus group testing that I'm aware of goes back to something that came up earlier today when I was kind of reacquainting myself with LaDonna Williams, who, in talking about this project that was 2005 to 2007, the Fish Mercury project. And it was that project that I was mainly referring to, where we worked with a lot of community groups. We were partnering with the Department of Public Health on that, and they have done a lot of work on risk communication. There was a woman named Elise Ujihara, who's now retired, who had great relationships with a lot of these local community groups. And one of the neat things we did in that project was we funded a lot of these community groups with small grants to do risk communication in their communities. So we had them strongly engaged in this project, and so they through them we had access to a variety of different communities and people that we could draw on to be focus groups to test out different ways of designing that poster. I think there's been more work like that since that time that I haven't really been involved with, so I don't know much about it. But it, I think that this poster is a result of a long process of a lot of people thinking about the design and actually doing the testing with audiences to make sure that it works. So I definitely think that if you want to have successful communication, and it's really part of all the monitoring programs that we're trying to collect monitoring data and communicate information. You need to basically monitor how well you're communicating, and I think things like focus groups are important for that.
Oh, I just had a question for David. For that Canadian Water Quality Index formula, what is the scope and amplitude? How do you get those F values? What does that mean?
All right. So essentially, it's taking all of the monitoring data and hopefully we can pull up the formulas for that. But it's not quite as complicated as it looks. It's really just for every sample, it's looking at the threshold value for that given sample, which were defined on that other tab that I showed earlier. So then it's just it's summing up all of the number of times that samples exceeded the thresholds, and then also for the magnitude, looking at just exactly how much did it exceed the threshold by. So you can kind of see the formulas there. Not sure if that totally explains.
The scope value, what was that?
What do you mean exactly by scope?
Well, it said that F1 plus F2 plus F3 divided by 1.73, and it said scope was one of the F values. You see, so what is scope exactly?
I'm not sure that that's... there's only two F values in this one. F1 is frequency and F2 is magnitude. So then it's the overall index is 100 minus square root of F1 frequency squared plus magnitude squared.
Might have been a typo. Might have meant score.
Maybe.
Oh,
well,
sorry about that.
We're going to end on a typo. So, and that, there's a lesson there, right? We make mistakes, we iterate, we keep trying, and this has been an amazing symposium, so I want to thank everyone. I want to thank the panel that was up here in particular, because the work that went into this was a year of work, not just getting ready to write a thing. So thank you, everyone. I had a couple quick thoughts. Like for the HABs and the microbiology stuff that you saw that Alicia and Keith and others were all, and even some of the other topics, there's aggregate interests like swim. You know, we've talked a lot about new data visualizations, but maybe it's taking the ones we have and making them into better communication tools of where can you swim, and maybe swim includes where can I take my dog and throw a stick. So there's just a lot of improvement to do, so we just keep iterating, but I love the idea that people are engaged and that there's more and more capacity. I like seeing the audience this year was really diverse in terms of age and background and experience, and so thank everyone for coming today, or this and height, as Chad points out. So I agree. So it's been awesome. You guys have been great. We had the 2 parallel events. That was an experiment. So those of you who helped with that and sort of suffered through that because you had to choose which thing you wanted to do, thank you. And we want your feedback. So we'll be following up with a survey. We will also do this again next year. I think we kind of went a little bit longer than we probably should. I think this is a perfect 1.5 day event. But again, those kinds of considerations are important, and we take your feedback very seriously. So we actually added the workshops as a result of recommendations last year to add some workshops. So again, thanks everyone for coming. We have some stickers up here. Those of you on the panel, grab a little 3-pack of stickers here to make sure. There's only a few of the really special ones. So, but there's a lot of the trash ones from last year. Ironically, there's extra trash stickers. So don't let them get in the trash, please. We're also, Meredith, I don't know, should we re-announce the California Water Data Challenge is kicking off this time of year too? And so there'll be some commitment events on that. So if you go to waterchallenge.data.ca.gov, you'll arrive at the homepage for the Water Data Challenge. And the plan is to continue this kind of a style of iteration events. You never nail it, you just keep trying and working and improving. And so there'll be a series of commitments that follow up on last year's events, but there'll also be a focus on some new topics. So vulnerable communities is one of our organizing themes, and we wanted to expand that to include the water crossover element into fires and some of these other events that are in forest protection and what have you. So water is, of course, everything in California in some ways, but it's also really important to focus on what the people want more help from government on. So vulnerable communities is a theme, and look for events on that. Anything else I'm missing? Thank you, everyone. Thank you, Anna, in particular. Anna, are you still here? So Anna, yeah. Seriously, this probably wouldn't have happened without Anna's help, so thank you, Anna, and everyone else on my staff. You guys are awesome. Thanks. All right, have a great, so come on up and get a sticker.